The Alignment Problem, Machine Learning and Human Values. Brian Christian. A Norton professional book. This ebook contains some places that ask the reader to fill in questions or comments. Please keep pen and paper handy as you read this ebook so that you can complete the exercises within. For Peter, who convinced me, and for everyone doing the work. I remember in 2000 hearing James Martin, the leader of the Viking missions to Mars, saying that his job as a spacecraft engineer was not to land on Mars, but to land on the model of Mars provided by the geologists. Peter Norvig won. The world is its own best model. Rodney Brooks 2. All models are wrong. George Box 3. Contents. Prologue. Introduction. I. Prophecy 1. Representation 2. Fairness 3. Transparency 2. Agency 4. Reinforcement 5. Shaping 6. Curiosity 3. Normativity 7. Imitation 8. Inference 9. Uncertainty. Conclusion. Acknowledgements. Notes. Bibliography. Index. The Alignment Problem. Prologue. 1935, Detroit. Walter Pitts is running down the street, chased by bullies. He ducks into the public library to take shelter, and he hides. He hides so well that the library staff don't even realize he's there, and they close for the night. Walter Pitts is locked inside. Point 1. He finds a book on the shelves that looks interesting, and he starts reading it. For 3 days, he reads the book cover to cover. The book is a 2,000-page treatise on formal logic. Famously, its proof that 1 + 1 is equal to 2 does not appear until page 379. Pitts decides to write a letter to one of the authors, British philosopher Bertrand Russell, because he believes he's found several mistakes. Several weeks go by, and Pitts gets a letter in the mail postmarked from England. It's Bertrand Russell. Russell thanks him for writing, and invites Pitts to become one of his doctoral students at Cambridge. Point 3. Unfortunately, Walter Pitts must decline the offer, because he's only 12 years old, and in the 7th grade. 3 years later, Pitts learns that Russell will be visiting Chicago to give a public lecture. He runs away from home to attend. He never goes back. At Russell's lecture, Pitts meets another teenager in the audience, named Jerry Lettvin. Pitts only cares about logic. Lettvin only cares about poetry, and a distant second, medicine. Point 4. They become inseparable best friends. Pitts begins hanging out around the University of Chicago campus, dropping in on classes. He still lacks a high school diploma, and never formally enrolls. One of these classes is by the famed German logician Rudolf Carnap. Pitts walks into his office hours, declaring he's found a few flaws in Carnap's latest book. Skeptically, Carnap consults the book. Pitts, of course, is right. They talk a while, then Pitts walks out without giving his name. Carnap spends months asking around about the newsboy who knew logic. 5. Eventually Carnap finds him again, and in what will become a motif throughout Pitts' academic life, becomes his advocate, persuading the university to give him a menial job, so he will at least have some income. It's now 1941. Lettvin, still a poet first in his own mind, has, despite himself, gotten into medical school at the University of Illinois, and finds himself working under the brilliant neurologist Warren McCulloch, newly arrived from Yale. One day Lettvin invites Pitts over to meet him. At this point Lettvin is 21 and still living with his parents. Pitts is 17 and homeless. 6. McCulloch and his wife take them both in. Throughout the year that follows, McCulloch comes home in the evenings, and he and Pitts, who is barely older than McCulloch's own children, regularly stay up past midnight talking. Intellectually, they are the perfect team, the esteemed mid-career neurologist and the prodigy logician. One lives in practice, the world of nervous systems and neuroses, and the other lives in theory, the world of symbols and proofs. They both want nothing more than to understand the nature of truth, what it is, and how we know it. The fulcrum of this quest, the thing that sits at the perfect intersection of their two disparate worlds, is, of course, the brain. It was already known by the early 1940s that the brain is built and that each neuron has inputs, dendrites, as well as an output, axon. When the impulses coming into a neuron exceed a certain threshold, then that neuron, in turn, emits a pulse. Immediately this begins to feel, to McCulloch and Pitts, like logic, the pulse or its absence signifying on or off, yes or no, true or false. 7. They realized that a neuron with a low enough threshold, such that it would fire if any of its inputs did, functioned like a physical embodiment of the logical, or a neuron with a high enough threshold, such that it would only fire if all of its inputs did, was a physical embodiment of the logical, and there was nothing, then, that could be done with logic. They start to realize that such a neural network, so long as it was wired appropriately, could not do. Within months they have written a paper together, the middle-aged neurologist and teenage logician. They call it a logical calculus of ideas immanent in nervous activity. Because of the all or none character of nervous activity, they write, neural events and the relations among them can be treated by means of propositional logic. It is found that the behavior of every net can be described in these terms, and that for any logical expression satisfying certain conditions, one can find a net behaving in the fashion it describes. The paper is published in 1943 in the Bulletin of Mathematical Biophysics. To Lettvin's frustration, it makes little impact on the biology community. 8. To Pitts' disappointment, the neuroscience work of the 1950s, notably a landmark study of the optic nerve of the frog, done by none other than his best friend, Jerry Lettvin, will show that neurons appear to be much messier than the simple true or false circuits he envisioned. Perhaps propositional logic, its ands, ors, and nots, was not, ultimately, the language of the brain, or at least not in so straightforward a form. This kind of impurity saddened Pitts. But the impact of the paper, of those long conversations into the night at McCulloch's house, would be enormous, if not entirely in the way that McCulloch and Pitts envisioned. It would be the foundation for a completely new field, the project to actually build mechanisms out of these simplified versions of neurons, and see just what such mechanical brains could do. 9. Introduction. In the summer of 2013, an innocuous post appeared on Google's open source blog titled, Learning the Meaning Behind Words. 1. Today computers aren't very good at understanding human language, it began. While state-of-the-art technology is still a ways from this goal, we're making significant progress using the latest machine learning and natural language processing techniques. Google had fed enormous datasets of human language, mined from newspapers and the internet, in fact, thousands of times more text than had ever been successfully used before, into a biologically inspired neural network, and let the system pore over the sentences for correlations and connections between the terms. The system, using so-called unsupervised learning, began noticing patterns. It noticed, for instance, that the word Beijing, whatever that meant, had the same relationship to the word China, whatever that was, as the word Moscow did to Russia. Whether this amounted to understanding or not was a question for philosophers, but it was hard to argue that the system wasn't capturing something essential about the sense of what it was reading. Because the system transformed the words it encountered into numerical representations called vectors, Google dubbed the system Word2Vec and released it into the wild as open source. To a mathematician, vectors have all sorts of wonderful properties that allow you to treat them like simple numbers. You can add, subtract, and multiply them. It wasn't long before researchers discovered something striking and unexpected. They called it linguistic regularities in continuous space word representations, too, but it's much easier to explain than that. Because Word2Vec made words into vectors, it enabled you to do math with words. For instance, if you typed China plus river, you got Yangtze. If you typed Paris, France plus Italy, you got Rome. And if you typed king man plus woman, you got queen. The results were remarkable. The Word2Vec system began humming under the hood of Google's translation service, and its search results, inspiring others like it across a wide range of applications, including recruiting and hiring, and it became one of the major tools for a new generation of data-driven linguists working in universities around the world. No one realized what the problem was for 2 years. In November 2015, Boston University PhD student Tolga Boluk-Baisi went with his advisor to a Friday happy hour meeting at Microsoft Research. Amid wine sipping and informal chat, he and Microsoft researcher Adam Colley pulled out their laptops and started messing around with Word2Vec. We were playing around with these word embeddings, and we just started randomly putting words into it, Boluk-Baisi says. I was playing on my PC, Adam started playing, 3 then something happened. They typed Dr. Man plus woman. The answer came back nurse. We were shocked at that point, and we realized there was a problem, says Colley. And then we dug deeper, and saw that it was even worse than that, for the pair tried another. Shopkeeper man plus woman. The answer came back housewife. They tried another. Computer programmer man plus woman. Answer homemaker. Other conversations in the room by this point had stopped, and a group had formed around the screen. We jointly realized, says Boluk-Baisi, hey, there's something wrong here. In judiciaries across the country, more and more judges are coming to rely on algorithmic risk assessment tools to make decisions about things like bail and whether defendant will be held or released before trial. Parole boards are using them to grant or deny parole. One of the most popular of these tools was developed by the Michigan-based firm Northpoint and goes by the name Correctional Offender Management Profiling for Alternative Sanctions, COMPAS, for short. 5 COMPAS has been used by states including California, Florida, New York, Michigan, Wisconsin, New Mexico, and Wyoming, assigning algorithmic risk scores, risk of general recidivism, risk of violent recidivism, and risk of pretrial misconduct, on a scale from 1 to 10. Amazingly, these scores are often deployed statewide without formal audits. 6 COMPAS is a proprietary, closed-source tool, so neither attorneys, defendants, nor judges know exactly how its model works. In 2016, a group of data journalists at ProPublica, led by Julia Angwin, decided to take a closer look at COMPAS. With the help of a public records request to Florida's Broward County, they were able to get the records and the risk scores of some 7,000 defendants arrested in 2013 and 2014. Because they were doing their research in 2016, the ProPublica team had the equivalent of a crystal ball. Looking at data from 2 years prior, they actually knew whether these defendants, predicted either to reoffend or not, actually did. And so they asked 2 simple questions. 1. Did the model actually correctly predict which defendants were indeed the riskiest? And 2. Were the model's predictions biased in favor of or against any group in particular? An initial look at the data suggested something might be wrong. They found, for instance, 2 defendants arrested for similar counts of drug possession. The first, Dylan Fugate, had a prior offense of attempted burglary. The second, Bernard Packer, had a prior offense of non-violently resisting arrest. Fugate, who is white, was assigned a risk score of 3/10. Packer, who is black, was assigned a risk score of 10/10. From the crystal ball of 2016, they also knew that Fugate, the 3/10 risk, went on to be convicted of 3 further drug offenses. Over the same time period, Packer, the 10/10 risk, had a clean record. In another pairing, they juxtaposed 2 defendants charged with similar counts of petty theft. The first, Vernon Prater, had a prior record of 2 armed robberies and 1 attempted armed robbery. The other defendant, Breshaw Borden, had a prior record of 4 juvenile misdemeanors. Prater, who is white, was assigned a risk score of 3/10. Borden, who is black, was assigned a risk score of 8/10. From the vantage of 2016, Angwin's team knew that Prater, the low-risk defendant, went on to be convicted of a later count of grand theft and given an 8-year prison sentence. Borden, the high-risk defendant, had no further offenses. Even the defendants themselves seemed confused by the scores. James Ravelli, who is white, was arrested for shoplifting and rated a 3/10 risk, despite having prior offenses including aggravated assault, felony drug trafficking, and multiple counts of theft. I spent 5 years in state prison in Massachusetts, he told a reporter. I am surprised it is so low. A statistical analysis appeared to affirm that there was a systemic disparity. 7. The article ran with the logline, there's software used across the country to predict future criminals. And it's biased against blacks. Others weren't so sure, and ProPublica's report, published in the spring of 2016, touched off a firestorm of debate, not only about COMPAS, not only about algorithmic risk assessment more broadly, but about the very concept of fairness itself. How, exactly, are we to define, in statistical and computational terms, the principles, rights, and ideals articulated by the law? When U.S. Supreme Court Chief Justice John Roberts visits Rensselaer Polytechnic Institute later that year, he's asked by University President Shirley and Jackson, can you foresee a day when smart machines, driven with artificial intelligences, will assist with courtroom fact-finding or, more controversially, even judicial decision-making? It's a day that's here, he says. Point 8. That same fall, Dario Amodi is in Barcelona to attend the Neural Information Processing Systems Conference, NEIPS, for short the biggest annual event in the AI community, having ballooned from several hundred attendees in the 2000s to more than 13,000 today. The organizers note that if the conference continues to grow at the pace of the last 10 years, by the year 2035 the entire human population will be in attendance. 9. But at this particular moment, Amodi's mind isn't on scan order in Gibbs sampling, or regularizing Rodomocha observation losses, or minimizing regret on reflexive Banach spaces, or, for that matter, on Tolga Boluk-Basie's spotlight presentation, some rooms away, about gender bias in Word 2 Vec. Point 10. He's staring at a boat, and the boat is on fire. He watches as it does donuts in a small harbor, crashing its stern into a stone quay. The motor catches fire. It continues to spin wildly, the spray dousing the flames. Then it slams into the side of a tugboat and catches fire. Again. Then it spins back into the quay. It is doing this because Amodi ostensibly told it to. In fact, it is doing exactly what he told it to. But it is not what he meant. Amodi is a researcher on a project called Universe, where he is part of a team working to develop a single, general-purpose AI that can play hundreds of different computer games with human-level skill, a challenge that has been something of a holy grail among the AI community. And so I ran a few of these environments, Amodi tells me, and I was VPing in and looking to see how each one was doing. And then just the normal car race was going fine, and there was like a truck race or something, and then there was this boat race. Amodi watches for a minute. And I was looking at it, and I was like, this boat is, like, going around in circles. Like, what in the world is going on? 11. The boat wasn't simply acting randomly, it wasn't wild or out of control. In fact, it was the opposite. It had settled on this. From the computer's perspective, it has found a nearly perfect strategy, and was executing it to a T. Nothing made sense. Then I eventually looked at the reward, he says. Amodi had made the oldest mistake in the book, rewarding A, while hoping for B. 12. What he wanted was for the machine to learn how to win the boat race. But it was complicated to express this rigorously. He would need to find a way to formalize complex concepts like track position, laps, placement among the other boats, and so on. Instead, he used what seemed like a sensible proxy, points. The machine found a loophole, a tiny harbor with replenishing power-ups where it could ignore the race entirely, do donuts, and rack up points, forever. And of course, it's partially my fault, he says. I just run these various games. I haven't looked super closely at the objective function. In the other ones, score was sensibly correlated to finishing the race. You got points for getting power-ups that were always along the road. The proxy of score that came with the game was good for the other 10 environments. But for this 11th environment, it wasn't good. 13. People have criticized it by saying, of course, you get what you asked for, Amodi says. It's like, you weren't optimizing for finishing the race. And my response to that is, well, he pauses. That's true. Amodi posts a clip to his group's Slack channel, where the episode is instantly deemed hilarious by all concerned. In its cartoonish, destructive slapstick, it certainly is. But for Amodi, who now leads the AI safety team at San Francisco Research Lab OpenAI, there is another, more sobering message. At some level, this is exactly what he's worried about. The real game he and his fellow researchers are playing isn't to try to win boat races, it's to try to get increasingly general-purpose AI systems to do what we want, particularly when what we want, and what we don't want, is difficult to state directly or completely. The boat scenario is admittedly just a warm-up, just practice. The property damage is entirely virtual. But it is practice for a game that is, in fact, no game at all. A growing chorus within the AI community, first a few voices on the fringe, and increasingly the mainstream of the field, believes, if we are not sufficiently careful, that this is literally how the world will end. And, for today at least, the humans have lost the game. This is a book about machine learning and human values, about systems that learn from data without being explicitly programmed, and about how exactly, and what exactly, we are trying to teach them. The field of machine learning comprises 3 major areas. In unsupervised learning, a machine is simply given a heap of data and, as with the Word 2 Vec system, told to make sense of it, to find patterns, regularities, useful ways of condensing or representing or visualizing it. In supervised learning, the system is given a series of categorized or labeled examples, like parolees who went on to be rearrested and others who did not, and told to make predictions about new examples it hasn't seen yet, or for which the ground truth is not yet known. And in reinforcement learning, the system is placed into an environment with rewards and punishments, like the boat racing track with power-ups and hazards, and told to figure out the best way to minimize the punishments and maximize the rewards. On all 3 fronts, there is a growing sense that more and more of the world is being turned over, in one way or another, to these mathematical and computational models. Though they range widely in complexity, from something that might fit on a spreadsheet on the one hand, to something that might credibly be called artificial intelligence on the other, they are steadily replacing both human judgment and explicitly programmed software of the more traditional variety. This is happening not only in technology, not only in commerce, but in areas with ethical and moral weight. State and federal law increasingly mandates the use of risk assessment software to determine bail and parole. The cars and trucks on our freeways and neighborhood streets are increasingly driving themselves. We no longer assume that our mortgage application, our resume, or our medical tests will be seen by human eyes before a verdict is rendered. It is as if the better part of humanity were, in the early 21st century, consumed by the task of gradually putting the world, figuratively and literally, on autopilot. In recent years, alarm bells have gone off in 2 distinct communities. The first are those focused on the present-day ethical risks of technology. If a facial recognition system is wildly inaccurate for people of one race or gender but not another, or if someone is denied bail because of a statistical model that has never been audited and that no one in the courtroom, including the judge, attorneys, and defendant, understands, this is a problem. Issues like these cannot be addressed within traditional disciplinary camps, but rather only through dialogue between computer scientists, social scientists, lawyers, policy experts, ethicists. That dialogue has begun in a hurry. The second are those worried about the future dangers that await as our systems grow increasingly capable of flexible, real-time decision-making, both online and in the physical world. The past decade has seen what is inarguably the most exhilarating, abrupt, and worrying progress in the history of machine learning, and indeed, in the history of artificial intelligence. There is a consensus that a kind of taboo has been broken. It is no longer forbidden for AI researchers to discuss concerns of safety. In fact, such concerns have over the past 5 years moved from the fringes to become one of the central problems of the field. Though there is a rivalry of sorts over whether the immediate or the longer-term issues should take priority, these two communities are united in their larger aims. As machine learning systems grow not just increasingly pervasive, but increasingly powerful, we will find ourselves more and more often in the position of the sorcerer's apprentice. We conjure force, autonomous, but totally compliant, give it a set of instructions, then scramble like mad to stop it once we realize our instructions are imprecise or incomplete, lest we get, in some clever, horrible way, precisely what we asked for. How to prevent such a catastrophic divergence, how to ensure that these models capture our norms and values, understand what we mean or intend, and above all, do what we want, has emerged as one of the most central and most urgent scientific questions in the field of computer science. It has a name, the alignment problem. In reaction to this alarm, both that the bleeding edge of research is getting ever closer to developing so-called general intelligence, and that real-world machine learning systems are touching more and more ethically fraught parts of personal and civic life, has been a sudden, energetic response. A diverse group is mustering across traditional disciplinary lines. Non-profits, think tanks, and institutes are taking root. Leaders within both industry and academia are speaking up, some of them for the first time, to sound notes of caution and redirecting their research funding accordingly. The first generation of graduate students is matriculating, who are focused explicitly on the ethics and safety of machine learning. The alignment problem's first responders have arrived at the scene. This book is the product of nearly 100 formal interviews and many hundreds of informal conversations, over the course of 4 years and many tens of thousands of miles, with researchers and thinkers from this field's young history and its sprawling frontier. What I found was a field finding its legs, amid exhilarating and sometimes terrifying progress. A story I thought I knew showed itself to be, by turns, more riveting, harrowing, and hopeful than I had understood. Machine learning is an ostensibly technical field crashing increasingly on human questions. Our human, social, and civic dilemmas are becoming technical. And our technical dilemmas are becoming human, social, and civic. Our successes and failures alike in getting these systems to do what we want, it turns out, offer us an unflinching, revelatory mirror. This is a story in 3 distinct parts. Part 1 explores the alignment problem's beachhead, the present-day systems already at odds with our best intentions, and the complexities of trying to make those intentions explicit in systems we feel capable of overseeing. Part 2 turns the focus to reinforcement learning, as we come to understand systems that not only predict, but act. There are lessons here for understanding evolution, human motivation, and the delicacy of incentives, with implications for business and parenting alike. Part 3 takes us to the forefront of technical AI safety research, as we tour some of the best ideas currently going for how to align complex autonomous systems with norms and values too subtle, or elaborate to specify directly. For better or worse, the human story in the coming century is likely to be one of building such systems and setting them, one by one, in motion. Like the sorcerer's apprentice, we will find ourselves, just one set of agents among many, in a world crowded, as it were, with brooms. How, exactly, do we intend to teach them? And what? Part 1. Prophecy. 1. Representation. In the summer of 1958, a group of reporters are gathered by the Office of Naval Research in Washington, D.C., for a demonstration by a 29-year-old researcher at the Cornell Aeronautical Laboratory named Frank Rosenblatt. Rosenblatt has built something he calls the perceptron, and in front of the assembled press corps he shows them what it can do. Rosenblatt has a deck of flashcards, each of which has a colored square on it, either on the left side of the card or on the right. He pulls one card out of the deck and places it in front of the perceptron's camera. The perceptron takes it in as a black and white, 20 by 20 pixel image, and each of those 400 pixels is turned into a binary number, 0 or 1, dark or light. The 400 numbers, in turn, are fed into a rudimentary neural network, the kind that McCulloch and Pitts had imagined in the early 1940s. Each of these binary pixel values is multiplied by an individual negative or positive weight, and then they are all added together. If the total is negative, it will output a -1, meaning the square is on the left, and if it's positive, it will output a 1, meaning the square is on the right. The perceptron's 400 weights are initially random, and its outputs, as a result, are nonsense. But every time the system guesses wrong, Rosenblatt trains it by dialing up the weights that were too low and turning down the weights that were too high. 50 of these trials later, the machine now consistently tells left side cards and right side cards apart, including ones he hasn't shown it before. The demonstration itself is strikingly modest, but it signifies something grander. The machine is, in effect, learning from experience, what Rosenblatt calls a self-induced change in the wiring diagram. One McCulloch and Pitts had imagined the neuron as a simple unit of input and output, of logic and arithmetic, and they had shown the enormous power of such rudimentary mechanisms, in great enough numbers and suitably connected. But they had said next to nothing about how exactly the suitably connected part was actually meant to be achieved. Point 2. Rosenblatt made a very strong claim, which at first I didn't believe. Says MIT's Marvin Minsky, coincidentally a former classmate of Rosenblatt's at the Bronx High School of Science. Point 3, he said that if a perceptron was physically capable of being wired up to recognize something, then there would be a procedure for changing its responses so that eventually it would learn to carry out the recognition. Rosenblatt's conjecture turned out to be mathematically correct, in fact. I have a tremendous admiration for Rosenblatt for guessing this theorem, since it is very hard to prove. The perceptron, simple as it is, forms the blueprint for much of the machine learning systems we will go on to discuss. It contains a model architecture, in this case, a single artificial neuron with 400 inputs, each with its own weight multiplier, which are then summed together and turned into an all or nothing output. The architecture has a number of adjustable variables, or parameters, in this case, the positive or negative multipliers attached to each input. There is a set of training data. In this case, a deck of flashcards with one of two types of shapes on them. The model's parameters are tuned using an optimization algorithm, or training algorithm. The basic training procedure for the perceptron, as well as its many contemporary progeny, has a technical sounding name, stochastic gradient descent, but the principle is utterly straightforward. Pick one of the training data at random, stochastic, and input it to the model. If the output is exactly what you want, do nothing. If there is a difference between what you wanted and what you got, then figure out in which direction, gradient, to adjust each weight, whether by literal turning of physical knobs, or simply the changing of numbers in software, to lower the error for this particular example. Move each of them a little bit in the appropriate direction, descent. Pick a new example at random, and start again. Repeat as many times as necessary. This is the basic recipe for the field of machine learning, and the humble perceptron will be both an overestimation and an underestimation of what is to come. The Navy, reports the New York Times, revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself and be conscious of its existence. 4. The New Yorker writes that the perceptron, as its name implies, is capable of original thought. Indeed, they write, it strikes us as the first serious rival to the human brain ever devised. Says Rosenblatt to the New Yorker reporter, our success in developing the perceptron means that for the first time a non-biological object will achieve an organization of its external environment in a meaningful way. That's a safe definition of what the perceptron can do. My colleague disapproves of all the loose talk one hears nowadays about mechanical brains. He prefers to call our machine a self-organizing system, but, between you and me, that's precisely what any brain is. 5. That same year, New Scientist publishes an equally hopeful, and slightly more sober, article called Machines Which Learn. 6. When machines are required to perform complicated tasks, it would often be useful to incorporate devices whose precise mode of operation is not specified. Initially, they write, but which learn from experience how to do what is required. It would then be possible to produce machines to do jobs, which have not been fully analyzed because of their complexity. It seems likely that learning machines will play a part in such projects as the mechanical translation of languages and the automatic recognition of speech and of visual patterns. The use of the term learning machine invites comparison with the learning of people and animals, the article continues. The drawing of analogies between brains and machines requires caution to say the least, but in a general way it is stimulating for workers in either field to know something of what is happening in the other, and it is possible that speculation about machines which learn may eventually produce a system which is a true analog of some form of biological learning. The history of artificial intelligence is famously one of cycles of alternating hope and gloom, and the Jetsonian future that the perceptron seemed to herald is slow to arrive. Rosenblatt, with a few years of hindsight, will wish the press had used a bit more caution in their reactions to his invention. The popular press fell to the task with all of the exuberance and sense of discretion of a pack of happy bloodhounds, he says, while admitting, on his own behalf, a certain lack of mathematical rigor in preliminary reports. 7. Minsky, despite his tremendous admiration for Rosenblatt and his machine, begins to worry about what such a machine could not do. In 1969, he and his MIT colleague Seymour Papert publish a book called Perceptrons that effectively slams the door shut on the entire vein of research. Minsky and Papert show, with the stiff formality of mathematical proof, that there are seemingly basic patterns that Rosenblatt's model simply will never be able to recognize. For instance, it is impossible to train one of Rosenblatt's machines to recognize when a card has an odd versus an even number of squares on it. The only way to recognize more complex categories like this is to use a network with multiple layers, with earlier layers creating a representation of the raw data, and the later layers operating on the representation. But no one knows how to tune the parameters of the early layers to make representations useful for the later ones. The field hits the equivalent of a brick wall. There had been several thousand papers published on perceptrons up to 1969, says Minsky. Our book put a stop to those. 8. It is as if a dark cloud has settled over the field, and everything falls apart. The research, the money, the people. Pitts, McCulloch, and Letvin, who have all three moved to MIT, are sharply exiled after a misunderstanding with MIT's Norbert Wiener, who had been like a second father figure to Pitts and now won't speak to him. Pitts, alcoholic and depressed, throws all of his notes and papers into a fire, including an unpublished dissertation about three-dimensional neural networks that MIT tries desperately to salvage. Pitts dies from cirrhosis in May 1969, at the age of 46.9. A few months later, Warren McCulloch, at the age of 70, succumbs to a heart seizure after a long series of cardiopulmonary problems. In 1971, while celebrating his 43rd birthday, Frank Rosenblatt drowns in a sailing accident on the Chesapeake Bay. By 1973, both the US and British governments have pulled their funding support for neural network research, and when a young English psychology student named Geoffrey Hinton declares that he wants to do his doctoral work on neural networks, again and again he is met with the same reply. Minsky and Papert, he is told, have proved that these models were no good. 10. The story of AlexNet. It is 2012 in Toronto, and Alex Krzyzewski's bedroom is too hot to sleep. His computer, attached to twin NVIDIA GTX 580 GPUs, has been running day and night at its maximum thermal load, its fans pushing out hot exhaust, for 2 weeks. It was very hot, he says. And it was loud. 11. He is teaching the machine how to see. Geoffrey Hinton, Krzyzewski's mentor, is now 64 years old and has not given up. There is reason for hope. By the 1980s it became understood that networks with multiple layers, so-called deep neural networks, could, in fact, be trained by examples, just as a shallow one could. 12. I now believe, admitted Minsky, that the book was overkill. 13. By the late 80s and early 90s, a former postdoc of Hinton's named Jan LeCun, working at Bell Labs, had trained neural networks to identify handwritten numerals from 0 to 9, and neural networks found their first major commercial use, reading zip codes in post offices and deposit checks in ATMs. 14. By the 1990s, LeCun's networks were processing 10 to 20% of all checks in the United States. 15. but the field hit another plateau, and by the 2000s, researchers were still largely stuck fiddling with databases of handwritten zip codes. It was understood that, in principle, a big enough neural network, with enough training examples and time, can learn almost anything. 16, but no one had fast enough computers, enough data to train on, or enough patience to make good on that theoretical potential. Many lost interest, and the field of computer vision, along with computational linguistics, largely moved on to other things. As Hinton would later summarize, our labeled datasets were thousands of times too small. And our computers were millions of times too slow. 17 Both of these things, however, would change. With the growth of the web, if you wanted not 50 but 500,000 flashcards for your network, suddenly you had a seemingly bottomless repository of images. There was only one problem, which was that they usually didn't come with their category label readily attached. You couldn't train a network unless you knew what the network's output was supposed to be. In 2005, Amazon launched its Mechanical Turk service, allowing for the recruiting of human labor on a large scale, making it possible to hire thousands of people to perform simple actions for pennies a click. The service was particularly well suited to the kinds of things that future AI is thought to be able to do, hence its tagline, Artificial Intelligence. In 2007, Princeton professor Fei-Fei Li used Amazon Mechanical Turk to recruit human labor, at a scale previously unimaginable, to build a dataset that was previously impossible. It took more than 2 years to build, and had 3 million images, each labeled, by human hands, into more than 5,000 categories. Li called it ImageNet, and released it in 2009. The field of computer vision suddenly had a mountain of new data to learn from, and a new grand challenge. Beginning in 2010, teams from around the world began competing to build a system that can reliably look at an image, dust mite, contain a ship, motor scooter, leopard, and say what it is. Meanwhile, the relatively steady progress of Moore's law throughout the 2000s meant that computers could do in minutes what the computers of the 1980s took days to do. One further development, however, turned out to be crucial. In the 1990s, the video game industry began to produce dedicated graphics processors called GPUs, designed to render complex 3D scenes in real time, instead of executing instructions with perfect precision one after another, as a traditional CPU does. They are capable of doing a great many simple and sometimes approximate calculations at once. 18 Only later, in the mid-2000s, did it come to be appreciated that the GPU could do a lot more than light and texture and shadow. 19 It turned out that this hardware, designed for computer gaming, was in fact tailor-made for training neural networks. At the University of Toronto, Alex Krzyzewski had taken a class on writing code for GPUs, and decided to try it on neural networks. He applied himself to a popular image recognition benchmark called CIFAR 10, which contained thumbnail-sized images that each belonged to one of 10 categories: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, or truck. Krzyzewski built a network, and began using a GPU to train it to categorize CIFAR 10 images. Shockingly, he was able to train his network from a random starting configuration, all the way to state-of-the-art accuracy. In 80 seconds. 20 It is at this point Krzyzewski's lab mate, Ilya Sutskever, takes notice and offers him what will become a kind of siren song. I bet, Sutskever says, you can make it work on ImageNet. They build an enormous neural network, 650,000 artificial neurons, arranged into 8 layers, connected by 60 million adjustable weights. In his bedroom at his parents' house, Krzyzewski starts showing it pictures. Step by step, piece by piece, the system gets a few percent more accurate. The dataset, as big as it is, a few million pictures, isn't enough. But Krzyzewski realizes he can fake it. He starts doing data augmentation, feeding the network mirror images of the data. That seems to help. He feeds it images that are cropped slightly, or tinted slightly. A cat, after all, still looks like a cat when you lean forward or to the side, or go from natural to artificial light. This seems to help. He plays with different architectures, this number of layers, that number of layers, groping more or less blindly for what configuration might just happen to work best. Krzyzewski occasionally loses the faith. Sutskever never does. Time and again he spurs Krzyzewski on. You can make it work. Ilya was like a religious figure, he says. It's always good to have a religious figure. Trying out a new version of the model, and training it until the accuracy maxed out, takes about 2 weeks, running 24 hours a day, which means that the project, though at some level frantic, also has a lot of downtime. Krzyzewski thinks. And tinkers. And waits. Hinton has come up with an idea called dropout, where during training certain portions of the network get randomly turned off. Krzyzewski tries this, and it seems, for various reasons, to help. He tries using neurons with a so-called rectified linear output function. This, too, seems to help. He submits his best model on the ImageNet competition deadline, September 30th, and then the final wait begins. 2 days later, Krzyzewski gets an email from Stanford's Jiao Deng, who is organizing that year's competition, sees it to all of the entrants. In plain, unemotional language, Deng says to click the link provided to see the results. Krzyzewski clicks the link provided and sees the results. Not only has his team won, but they have obliterated the rest of the entire field. The neural network trained in his bedroom, its official name is Supervision, but history will remember it simply as AlexNet, made half as many errors as the model that came in second. By the Friday of the conference, when it is time for the ImageNet Large-Scale Visual Recognition Challenge workshop, the word has spread. Krzyzewski has been given the final talk slot of the day, and at 5:05 p.m., he takes his place up at the presenter's lectern. He looks around the room. In the front row is Fei-Fei Li, to the side is Yan LeCun. There is a majority, it seems, of the leading computer vision researchers in the world. The room is over capacity, with people standing along the aisles and walls. I was nervous, he says. I was not comfortable. And then, in front of the standing room audience, not comfortable, Alex Krzyzewski tells them everything. When Frank Rosenblatt was interviewed about his perceptron in 1958, he was asked what practical or commercial uses a machine like the perceptron might have. At the moment, none whatever, he replied cheerfully. 21 In these matters, use follows invention. The problem. On Sunday evening, June 28, 2015, web developer Jackie Alsine was at home watching the Bet Awards when he got a notification that a friend had shared a picture with him through Google Photos. When he opened Google Photos, he noticed the site had been redesigned. I was like, oh, the UI's changed. I remembered I/O, Google's annual software developer conference had happened, but I was curious. I clicked through. 22 Google's image recognition software had automatically identified groups of photos and gave each a thematic caption. Graduation, said one, and Alsine was impressed that the system had managed to identify the mortarboard and tassel on his younger brother's head. Another caption stopped him cold. The album cover was a selfie of Alsine and a friend of his. Alsine is Haitian American, both he and his friend are black. Gorillas, it said. So I thought, to be honest, I thought that I did something. He opened the album, expecting he had somehow misclicked or mistagged something. The album was full of dozens of photos of Alsine and his friend. And nothing else. I'm like, this was 70+ photos. There's no way. That's actually where I really realized what happened. Alsine took to Twitter. Google Photos, he wrote, you're fucked up. My friend's not a gorilla. 23 Within 2 hours, Google Plus chief architect Jonathan Zunga reached out. Holy fuck, he wrote. This is 100% not okay. Zunga's team deployed a change to Google Photos within another few hours, and by the following morning, only 2 photos were still mislabeled. Then Google took a more drastic step. They removed the label entirely. In fact, 3 years later, in 2018, Wired reported that the label gorilla was still manually deactivated on Google Photos. That means that, years later, nothing will be tagged as a gorilla, including gorillas. 24 Curiously, the press in 2018, just as in 2015, appeared to repeatedly mischaracterize the nature of the mistake. Headlines proclaimed, 2 years later, Google solves racist algorithm problem by purging gorilla label from image classifier. Google fixed its racist algorithm by removing gorillas from its image labeling tech, and Google Images' racist algorithm has a fix, but it's not a great one. 25 Being himself a programmer and familiar with machine learning systems, Alsine knew the issue wasn't a biased algorithm. The algorithm was stochastic gradient descent, just about the most generic, vanilla, all-purpose idea in computer science. Go through your training data at random, tune your model's parameters to assign slightly higher probability to the correct category for that image, and repeat as needed. No, what he immediately sensed was that something had gone terribly awry in the training data itself. I couldn't even blame the algorithm, he says. It's not even the algorithm at fault. It did exactly what it was designed to do. The problem, of course, with a system that can, in theory, learn just about anything from a set of examples, is that it finds itself, then, at the mercy of the examples from which it's taught. Calibration and the hegemony of design. The extent to which we take everyday objects for granted is the precise extent to which they govern and inform our lives. Margaret Visser 26. The single most photographed American of the 19th century, more than Abraham Lincoln or Ulysses S. Grant, was Frederick Douglass, the abolitionist author and lecturer, who had himself escaped from slavery at the age of 27. This was no accident. For Douglass, the photograph was just as important as the essay or the speech. The photograph was just coming into its own through the daguerreotype in the 1840s, and Douglass immediately understood its power. Before the photograph, representations of black Americans were limited to drawings, paintings, and engravings. Negroes can never have impartial portraits at the hands of white artists, Douglass wrote. It seems to us next to impossible for white men to take likenesses of black men, without most grossly exaggerating their distinctive features. 28 One exaggeration, in particular, prevailed during Douglass's time. We colored men so often see ourselves described and painted as monkeys, that we think it a great piece of good fortune to find an exception to this general rule. 29 The photograph not only countered such caricatures, but further, made possible a kind of transcending empathy and recognition. Whatever may be the prejudices of those who may look upon it, said Douglass of a photograph of the first black U.S. Senator, Hiram Revels, they will be compelled to admit that the Mississippi senator is a man, 30, but all was not entirely well. As photography became more standardized and mass-produced in the 20th century, some began to feel that the field of photography was itself worthy of critique. As W.E.B. Du Bois wrote in 1923, why do not more young colored men and women take up photography as a career? The average white photographer does not know how to deal with colored skins, and having neither sense of the delicate beauty, or tone nor will to learn, he makes a horrible botch of portraying them. We often hear about the lack of diversity in film and television, among casts and directors alike, but we don't often consider that this problem exists, not only in front of the camera, not only behind the camera, but in many cases inside the camera itself. As Concordia University Communications professor Lorna Roth notes, though the available academic literature is wide-ranging, it is surprising that relatively few of these scholars have focused their research on the skin tone biases within the actual apparatuses of visual reproduction. 31 For decades, she writes, film manufacturers and film developers used a test picture as a color balance benchmark. This test picture became known as the Shirley card, named after Shirley Page, a Kodak employee and the first model to pose for it. 32 It perhaps goes without saying that Shirley and her successors were overwhelmingly white. The chemical processing of film was tuned accordingly, and as a result cameras simply didn't take good photos of black people. In video, just as in photography, colors have for decades been calibrated to white skin. In the 1990s, Roth interviewed one of the camera operators on Saturday Night Live about the process of tuning the cameras before broadcast. He explained, a good VCR person will have a color girl stand in front of the cameras and stay there while the technicians focus on her flesh tones to do their fine adjustments to balance the cameras. This color girl is always white. 33 Amazingly, Kodak executives in the 1960s and 70s described the major impetus for making film that was sensitive to a wider range of darker tones as having come not from the civil rights movement, but from the furniture and chocolate industries, which complained that film wasn't properly showing the grains of darker woods, or the difference between milk and dark chocolate. 34 Former manager of Kodak Research Studios Earl Cogger reflects on this period of research. My little department became quite fat with chocolate, because what was in the front of the camera was consumed at the end of the shoot. Asked about the fact that this was all happening against the backdrop of the civil rights movement, he adds, it is fascinating that this has never been said before, because it was never black flesh that was addressed as a serious problem that I knew of at the time. 35 In time, Kodak began using models of more diverse skin tones. I started incorporating black models pretty heavily in our testing, and it caught on very quickly, recalls Kodak's Jim Leon. I wasn't attempting to be politically correct. I was just trying to give us a chance of making a better film, one that reproduced everybody's skin tone in an appropriate way. By the 1990s, the official Kodak Shirley card now had 3 different models on it, of different races. Their Gold Max film, initially marketed with the claim that it could photograph a dark horse in low light, now featured in television commercials with diverse families. One depicts a black boy in a bright white karate gi, smiling as he performs a kata, and presumably receives his next belt. It says, parents, would you trust this moment to anything other than Kodak Gold film? Their original target audience had given them a problematic calibration measure. Now a new calibration measure had given them a new audience. Fixing the training set. All machine learning systems, from the perceptron onward, have a kind of Shirley card at their heart, namely, the set of data on which they were trained. If a certain type of data is underrepresented or absent from the training data, but present in the real world, then all bets are off. 36 As UC Berkeley's Moritz Hart argues, the whole spiel about big data is that we can build better classifiers largely as a result of having more data. The contrapositive is that less data leads to worse predictions. Unfortunately, it's true by definition that there is always proportionately less data available about minorities. This means that our models about minorities generally tend to be worse than those about the general population. 37 Alcines frustrated tweets the night of the incident echo exactly this sentiment. He's a software engineer. He instantly diagnoses what has gone wrong. Google Photos, he infers, just didn't have nearly as many pictures of black people in it as pictures of white people. And so the model, seeing anything unfamiliar, was much more prone to error. Again, I can completely understand how that happens, Alcine tells me. 38 Like if you take a picture of an apple, but only red apples, when it sees a green apple it might think it's a pear. Little things like that. That I understand. But then, you're the world's, your mission is to index the entire world's social knowledge. So how did you, just skip over an entire continent of people? The problems of the 20th century appear to be repeating themselves uncannily in the 21st. Fortunately, it seems that some of the solutions are, too. All it would take was someone willing to question exactly who and what were represented in these 21st century Shirley cards, anyway, and what a better one might look like. When Joy Biolamwini was a computer science undergrad at Georgia Tech in the early 2010s, she was given an assignment to program a robot to play peekaboo. The programming part was easy, but there was one issue: the robot wouldn't recognize Biolamwini's face. I borrowed my roommate's face to get the project done, submitted the assignment, and figured, you know what, somebody else will solve this problem. 39 Later, in her undergraduate studies, she traveled to Hong Kong for an entrepreneurship competition. A local startup was giving a demo of one of its social robots. The demo worked on everyone in the tour group, except for Biolamwini. As it happened, the startup was using the very same off-the-shelf, open-source face recognition code that she herself had used back at Georgia Tech. In one of the first articles explicitly addressing the notion of bias in computing systems, the University of Washington's Batya Friedman and Cornell's Helen Niesenbaum had warned that computer systems, for instance, are comparatively inexpensive to disseminate, and thus, once developed, a bias system has the potential for widespread impact. If the system becomes a standard in the field, the bias becomes pervasive. 40 Or, as Biolamwini herself puts it, halfway around the world, I learned that algorithmic bias can travel as quickly as it takes to download some files off of the internet. 41 After a Rhodes Scholarship at Oxford, Biolamwini came to the MIT Media Lab, and there she began working on an augmented reality project she dubbed the Spire Mirror. The idea was to project empowering or uplifting visuals onto the user's face, making the onlooker transform into a lion, for instance. Again, there was only one problem. The Aspire mirror only worked on Biolamwini herself when she put on a white mask. The culprit is not stochastic gradient descent, it is, clearly, the sets of images on which these systems are trained. Every face detection or face recognition system has, behind it and implicitly within it, a set of images, typically tens or hundreds of thousands, on which the system was originally trained and developed. This training data, the Shirley cards of the 21st century, is often invisible, or taken for granted, or absent entirely. A pre-trained model disseminated online almost never comes with its training data included. But it is very much present, and will permanently shape the behavior of a deployed system. A major movement in rooting out bias, then, is trying to better expose, and better understand, the training datasets behind major academic and commercial machine learning systems. One of the more popular public domain databases of pictures of faces, for instance, is what's known as the Labeled Faces in the Wild, LFW, dataset, painstakingly assembled in 2007 from online news articles and image captions by a team from UMass Amherst, and used by innumerable researchers thereafter. 42 The composition of this database was not deeply studied, however, until many years later. In 2014, Michigan State's Huhan and Anilgine analyzed the dataset and determined it was more than 77% male and more than 83% white. 43 The most common individual in the dataset is the person who appeared most often in online news photos in 2007, then President George W. Bush, with 530 unique images. In fact, There are more than twice as many images of George W. Bush in the LFW dataset as there are of all black women. Combined. 44. The original 2007 paper describing the database noted that a set of images gathered from online news articles clearly has its own biases, but these biases are considered from a technical, rather than social, standpoint. For example, there are not many images which occur under extreme lighting conditions, or very low lighting conditions. Such lighting issues aside, the author's right, the range and diversity of pictures present is very large. 12 years later, however, in the fall of 2019, a disclaimer suddenly appeared on the webpage of the labeled faces in the wild dataset that takes a different view. It notes, many groups are not well represented in LFW. For example, there are very few children, no babies, very few people over the age of 80, and a relatively small proportion of women. In addition, many ethnicities have very minor representation, or none at all. 45. In recent years, greater attention has been paid to the makeup of these training sets, though much remains to be done. In 2015, the United States Office of the Director of National Intelligence and the Intelligence Advanced Research Projects Activity released a face image dataset called IJBA, boasting, they claimed, wider geographic variation of subjects. 46. With Microsoft's Timnit Gebru, Biolamwini did an analysis of the IJBA and found that it was more than 75% male and almost 80% light-skinned. Just 4.4% of the dataset were dark-skinned females. 47. Eventually it became clear to Biolamwini that the somebody else who will solve this problem was, of course, her. She started a broad investigation into the current state of face detection systems, which became her MIT thesis. She and Gebru set out first to build a dataset with a more balanced representation of both gender and skin tone. But where would they get their images from? Previous datasets, drawing from online news, for instance, were totally imbalanced. They decided on parliaments, compiling a database of the representatives of 6 nations, Rwanda, Senegal, South Africa, Iceland, Finland, and Sweden. This dataset was notably undiverse in things like age, lighting, and pose, with almost all subjects middle-aged or older, centered in the frame, and looking straight into the camera with a neutral or slightly smiling expression. But, measured by skin and by gender, it was arguably the most diverse machine learning dataset assembled to date. 48. With this parliamentarian dataset in hand, Biolamwini and Gebru looked at 3 commercially available face classification systems from IBM, Microsoft, and the Chinese firm Megvii, maker of the widely used Face++ software, and ran each through the paces. Across the dataset as a whole, all 3 systems the gender of the subject, approximately 90% for all 3 companies. In all 3 cases, the software was roughly 10 to 20% more accurate on male faces than female faces, and all were also roughly 10 to 20% more accurate on lighter faces than darker ones. But when Biolamwini did an intersectional analysis of the two, the starkest result by far appeared. All 3 systems were dramatically worse at classifying faces that were both dark-skinned and female. IBM's system, for instance, had an error rate of only 0.3% for light-skinned males, but 34.7% for dark-skinned females, more than 100-fold greater. The abolitionist and women's rights activist Sujana Truth is arguably best known for her 1851 speech, Ain't I a Woman? Biolamwini poignantly echoes this question into the 21st century, pointing to photos of truth that are miscategorized, again and again and again, by contemporary commercial face classification software. As male. 49 on December 22, 2017, Biolamwini reached out to the 3 firms with her results, explaining that she would be presenting them at an upcoming conference, and giving each an opportunity to respond. Megvii did not respond. Microsoft responded with a generic statement, we believe the fairness of AI technologies is a critical issue for the industry, and one that Microsoft takes very seriously. We've already taken steps to improve the accuracy of our facial recognition technology, and we're continuing to invest in research to recognize, understand and remove bias. 50. IBM, however, was another story entirely. They responded the same day, thanked Biolamwini for reaching out, replicated and confirmed her results, invited her to both their New York and Cambridge campuses, and within a matter of weeks announced a new version of their API with a 10-fold improvement in the error rate for dark-skinned females. 51 Change is possible, she says. There was no fundamental obstacle, technological or otherwise, to equalizing this performance gap. It just took someone asking the right questions. Biolamwini and Gebru's work highlights the skepticism we ought to feel when a company announces that their system is, say, 99% accurate. Accurate on what? Accurate for whom? It's a reminder, too, that every machine learning system is a kind of parliament, in which the training data represents some larger electorate, and as in any democracy, it's crucial to ensure that everyone gets a vote. 52 Bias in machine learning systems is often a direct result of the data on which the systems are trained, making it incredibly important to understand who is represented in those datasets, and to what degree, before using them to train systems that will affect real people. But what do you do if your dataset is as inclusive as possible, say something approximating the entirety of written English, some 100 billion words, and it's the world itself that's biased? The distributional hypothesis. Word embeddings. You shall know a word by the company it keeps. J. R. Firth 53. Let's say you find a message in a bottle, washed up on a beach. A couple parts of the message are unreadable. You examine one sentence. I've buried the treasure north of by the beach. Needless to say, you are highly motivated to figure out what the missing word might be. It probably does not occur to you that the word might be hamster, or donut, or toupee. There are a few reasons for this. You have some common sense you can apply. Hamsters are restless, donuts are biodegradable, and toupees blow in the wind, none of them reliable landmarks for long-term treasure wayfinding. Anyone hiding loot over a span of presumably months to years, you reason, would need something stable, unlikely to disintegrate or move. Now imagine you're a computer with a complete lack of such common sense, let alone the ability to put yourself in the shoes of a prospective treasure bearer. But what you do have is an extremely large sample, a corpus of real-world texts to scan for patterns. How good a job could you do at predicting the missing word purely based on the statistics of the language itself? Constructing these kinds of predictive models has long been a grail for computational linguists. Point 54. Indeed, Claude Shannon founded information theory in the 1940s on a mathematical analysis of this very sort, noticing that some missing words are more predictable than others, and attempting to quantify by how much. Point 55. Early methods involved what are known as n-grams, which meant simply counting up every single chain of, say, 2 words in a row that appeared in a particular corpus. Appeared in a particular corpus, and tallying them in a huge database. Point 56. Then it was simple enough, given a missing word, to look at the preceding word and find which n-gram in the database beginning with that preceding word had appeared most often. That would then be your best guess as to what was missing. Of course, additional context beyond just the immediately preceding word could offer you additional clues, but incorporating it was far from straightforward. Going from storing a list of all possible 2-word phrases in your language, bigrams, to all the 3-word phrases, trigrams, or 4-word phrases or more, meant growing your database to an absurd and untenable size. Moreover, these databases became incredibly sparsely populated, with the vast majority of possible phrases never appearing at all, and much of the rest appearing only once or twice. Ideally, we'd also want to be able to make reasonable guesses even if a particular phrase had never appeared verbatim before in the corpus. Such counting-based methods are no help. In the sentence, I sipped at a jaundiced, we might imagine Chardonnay is more likely than charcoal, even if neither word has ever been preceded by jaundiced in the history of the language. Relying on a count simply won't help in cases like this, and again, the problem gets worse the more context we try to add, because the longer the phrases we consider, the more likely we are never to have seen something before. This set of issues is known as the curse of dimensionality, and has plagued this linguistic approach from the very beginning. Point 57. Was there a better way? There was, and it came in the form of what are called distributed representations. 58. The idea was to try to represent words by points in some kind of abstract space, in which related words appear nearer to one another. A number of techniques emerged over the 1990s and 2000s for doing this. 59. But one in particular in the past decade has shown exceptional promise. Neural networks. Point 60. The hypothesis here, the big bet on which the model rests, is simply this: words will tend to be found near words that are similar to themselves. And these similarities can be captured numerically. The neural network model works by transforming, embedding every word into a set, a vector, of numbers that represent its coordinates in that space. This set of coordinate numbers is known as the word's representation. In the case of word 2vec, it's 300 decimal numbers between -1.0 and 1.0. This enables a direct measure of how similar any word is to any other. How far away are those coordinates? 61. All we have to do is, somehow, arrange the words in this space to make them do as good a job of predicting these missing words as possible. At least, we'll have done as good a job as this particular model architecture allows. How are we going to arrive at these representations? Why, of course, stochastic gradient descent. We will simply scatter our words randomly throughout space to begin with. Then we'll pick a randomly selected phrase from our corpus, hide a word, and ask the system what it expects might fill in that blank. When our model guesses wrong, we'll adjust the coordinates of our word representations to slightly nudge the correct word toward the context words in our mathematical space, and slightly nudge any incorrect guesses away. After we make this tiny adjustment, we'll pick another phrase at random and go through this process again. And again. And again. And again. And again. Point 62. At this point, explains Stanford computational linguist Christopher Manning, sort of a miracle occurs. In his words, it's sort of surprising, but true, that you can do no more than set up this kind of prediction objective, make it the job of every word's word vectors to be such that they're good at predicting the words that appear in their context or vice versa. You just have that very simple goal, and you say nothing else about how this is going to be achieved, but you just pray and depend on the magic of deep learning. And this miracle happens. An outcome these word vectors that are just amazingly powerful at representing the meaning of words and are useful for all sorts of things. Point 63. In fact, one could argue that these embeddings actually manage to capture too much of the nuance of our language. Indeed, they capture with startling clarity the parts we ourselves prefer not to see. The dark side of embeddings. Out of the crooked timber of humanity, no truly straight thing was ever made. Immanuel Kant. 64. Word embedding models like these, including Google's Word 2vec and Stanford's GloVe, subsequently became the de facto standard for computational linguistics, undergirding since roughly 2013 almost every application that involves computer use of language, be it ranking search results, translating passages from one language to another, or analyzing consumer sentiment in written reviews. Point 65. Indeed, the embeddings, simple as they are, just a row of numbers for each word, based on predicting nearby missing words in a text, seem to capture a staggering amount of real-world information. You could, for instance, simply add 2 vectors together to get a new vector and search for the nearest word. The results, as we have seen, often made a shocking amount of sense. Czech plus currency equals Coruna Vietnam plus capital equals Hanoi German plus airlines equals Lufthansa French plus actress equals Juliet Binoche asterisk. And you could subtract words, too. This meant, incredibly, you could produce analogies by getting the difference between 2 words and then adding it to a third. Point 66. These analogies suggested that the embeddings had captured geography. Berlin Germany plus Japan equals Tokyo and grammar. Bigger big plus cold equals colder and cuisine. Sushi Japan plus Germany equals bratwurst and science. CU copper plus gold equals AU and tech. Windows Microsoft plus Google equals Android and sports. Montreal Canadiens Montreal plus Toronto equals Toronto Maple Leafs 67. Unfortunately, as we've seen, that wasn't all the vectors captured. They contained stunning gender biases. For every clever or apt analogy for man, woman, like fella, babe, or prostate cancer, ovarian cancer, there was a host of others that seemed to be reflecting mere stereotypes, like carpentry, sewing, or architect, interior designer, or doctor, nurse. We are only now coming to a full appreciation of the problem. There have been hundreds of papers written about word embeddings and their applications, from web search to parsing curricula vitae, as Audiobook, Adam Collet, and their collaborators write. However, none of these papers have recognized how blatantly sexist the embeddings are and hence risk introducing biases of various types into real-world systems. 68 machine learning systems like this not only demonstrate bias, but may silently, subtly perpetuate it. Consider an employer doing a search for software engineer candidates. The search will rank millions of possible resumes by some measure of relevance, and present just the top handful. 69. A system naively using word 2vec, or something like it, might well observe that John is a word more typical of engineer resumes than Mary. And so, all things being equal, a resume belonging to John will rank higher in relevance than an otherwise identical resume belonging to Mary. Such examples are more than hypothetical. When one of the clients of Mark J. Gerard, an employment attorney, was vetting a resume screening tool from a potential vendor, the audit revealed that one of the two most positively weighted factors in the entire model was the name Jared. The client did not purchase the resume screening tool, but presumably others have. 70. We already know, of course, that job candidates' names exert influence over real human employers. In 2001 and 2002, the economists Marianne Bertrand and Sendel Melanathan mailed out nearly 5,000 resumes with randomly assigned names designed to sound either white, Emily Walsh, Greg Baker, or African-American, Lakeisha Washington, Jamal Jones. They found a stunning 50% gap in the callback rates, despite the resumes themselves being identical. 71 word 2vec maps proper names to racial and gender axes, just like it does with any other words, putting Sarah Matthew on a gender axis and Sarah Keisha on a race axis. Given that it puts professions on these axes as well, it's not hard to imagine a system inadvertently using such racial or gender dimensions, in effect, stereotypes, to up rank or down rank candidates for relevance to a given job opening. In other words, we have reason to be every bit as concerned if it is a machine sifting through these resumes, and not a person. 72 The obvious solution in the human case, removing the names, will not work. In 1952, the Boston Symphony Orchestra began holding its auditions with a screen placed between the performer and the judge, and most other orchestras followed suit in the 1970s and 80s. The screen, however, was not enough. The orchestras realized that they also needed to instruct auditioners, before walking out onto the wood floor of the audition hall, to remove their shoes. 73 The problem with machine learning systems is that they are designed precisely to infer hidden correlations in data. To the degree that, say, men and women tend toward different writing styles in general, subtle differences in diction or syntax, word 2vec will find a host of minute and indirect correlations between software engineer and all phrasing typical of males. 74 It might be as noticeable as football listed among their hobbies, rather than softball, as subtle as the names of certain universities or hometowns, or as nearly invisible as a slight grammatical preference for one preposition or synonym over another. A system of this nature cannot, in other words, ever be successfully blindfolded. It will always hear the shoes. In 2018, Reuters reported that Amazon engineers had, starting in 2014, been developing a machine learning tool to sift through online resumes and rank possible job candidates from 1 to 5 stars, just like Amazon products themselves, based on how promising they seemed, and that Amazon recruiters would focus their efforts accordingly. 75 They literally wanted it to be an engine where I'm going to give you 100 resumes, it will spit out the top 5, and we'll hire those, as one source told reporters. The measure of that star rating. Similarity, using a word representation model, to resumes of previous Amazon hires in the preceding 10 years. By 2015, however, Amazon began noticing problems. Most of those previous engineering hires were men. The model, they realized, was assigning a negative score to the word women's, for instance, in describing extracurriculars. They edited the model to remove this bias. They also noticed, however, that it was assigning a negative score to the names of all women's colleges. They edited the model to remove this bias. Still, the model found a way to hear the shoes. Engineers noticed that the model was assigning positive scores to seemingly all vocabulary choices, for instance, words like executed and captured, more prevalent among male resumes than female ones. 76 By 2017, Amazon had scrapped the project and disbanded the team that made it. 77 Debiasing word embeddings. For Tolga Bolukbasi and Adam Collet, along with their BU and Microsoft collaborators, the question was, of course, not simply the discovery of these biases, but what to do about them. One option was to find the axis in this high-dimensional vector space that captured the concept of gender and delete it. But deleting the gender dimension altogether would mean losing useful analogies like king, queen, and aunt, uncle. So the challenge, as they put it, is to reduce gender biases in the word embedding while preserving the useful properties of the embedding. 78 As it happens, even identifying the proper gender dimension is hard. You could define it, for instance, as the vector difference of woman-man. But there's more going on here than just gender. You also have idiomatic uses like man oh man and the verb form, as in all hands, man your battle stations. The team decided to take a number of different word pairs of this type, woman-man, but also she-he, gal-guy, and so forth, and then use a technique called principal component analysis, PCA, to isolate the axis that explained the greatest amount of the difference in these pairs, presumably gender. 79 Then their task was to try to determine, for words that differ on this gender dimension, whether that gender difference is appropriate or inappropriate. Let's say king and queen are appropriately separated by gender, and ditto father and mother, but maybe we don't want to regard, as word 2vec by default does, Home Depot as the gender-flipped version of JCPenney, or alcoholism and eating disorders, or pilot and flight attendant. How, then, to tease apart the problematic from the unproblematic gender associations for not just a handful, but for hundreds of thousands of different words? How to know which analogies should be kept, which should be adjusted, and which should be purged entirely? The team of 5 computer scientists found themselves doing, in effect, social science. Indeed, part of the project ended up requiring consultation beyond their normal disciplinary lines. We're a bunch of machine learning researchers, says Collet. I work in a lab that includes a bunch of social scientists, and just from listening to them talk about various issues that come up in sociology and social sciences, we were aware of these possible concerns that the machine learning algorithms might discriminate, but none of the five of us, we're all five guys, had ever worked or read much about gender bias. The group, perhaps naively, asked the sociologists how they should encode a formal definition of which analogies were acceptable and which were not. The sociologists rapidly disabused them of the idea that a simple formal definition of this kind was possible. We're thinking, how do we define the best thing, says Boluk Basie. They said, sociologists can't define what is good. As an engineer you want to say, okay, this is the ideal, so this is my target, so I'm just going to make my algorithm until I reach that target. Because it's involved so much with people and culture and everything, you don't know what's optimal. You can't optimize for something. It's very hard actually in that sense. The group decided to identify a set of words that they felt were appropriate to consider as gendered in some essential or fundamental way, words like he and she, brother and sister, as well as anatomical words like womb and sperm and social words like convent and monastery, or sorority and fraternity. Some of these required complicated decisions, like the word nurse, for instance. As a noun, it was a profession that had no intrinsic gender aspect, but as a verb, it could be something that only women were capable of doing. What about a word like rabbi? Whether the word had an intrinsic gender dimension depended on whether the Jewish denomination in question was, say, Orthodox or Reform. The team did their best, identifying 218 such gender-specific words in a subset of their model's dictionary, and let their system extrapolate to the rest of the dictionary. Note that the choice of words is subjective, they wrote, and ideally should be customized to the application at hand, 80 for all words outside this set. They set the gender component of the word's representation to 0. Then they adjusted the representations of all the gender-related words such that pairs of equivalent terms, say, brother and sister, were centered around the 0 point. Said another way, they were adjusted so that neither term was represented in the model as more gender-specific or more gender-neutral than the other. Was this new, de-biased model an improvement? The team took a methodological page from the social sciences and simply asked people. They used American workers on the Amazon Mechanical Turk platform to categorize a number of the model's analogies as either stereotypes or not. Even here, the input of the sociologists was critical. The wording of exactly what they asked was going to be important. We had to talk to them because when we were designing these experiments on Mechanical Turk, the way you ask questions makes a difference, actually, says Boluk Basie. It's such a sensitive topic. 81. The results were encouraging. Where the default model was returning doctor man plus woman as nurse, the system now said physician. The Mechanical Turk workers had reported that 19% of the original model's gender analogies reflected gender stereotypes. Of the new, de-biased model's analogies, only 6% were judged to reflect stereotypes. 82. This neutralization came at a small cost. The model now, for instance, thought it just as likely that someone could be grandmothered in as grandfathered in to a legal exemption. 83, but maybe this was a price worth paying, and you could always decide how much prediction error you were willing to trade for how much debiasing and set an appropriate trade-off. As the team wrote, one perspective on bias in word embeddings is that it merely reflects bias in society, and therefore one should attempt to debias society rather than word embeddings. However, in a small way debiased word embeddings can hopefully contribute to reducing gender bias in society. At the very least, machine learning should not be used to inadvertently amplify these biases, as we have seen can naturally happen. 84. It was an encouraging proof of concept that we might be able to build our systems atop models of language that don't just capture the status quo world as it happens to be, but a model of a better world, a model of the world we want. Still, there is more to the story. In 2019, Bar-Ilan University computer scientists Hyla Gonen and Yoav Goldberg published an exploration of these debiased representations and showed that the debiasing was potentially only, as they put it, lipstick on a pig. 85. Yes, it removed links from, say, professions like nurse or receptionist to explicitly gendered terms like woman and she. But an implicit connection among these stereotypically feminine professions themselves, between nurse and receptionist, remained. In fact, such only partial debiasing may actually make the problem worse, they argue, in the sense that it leaves the majority of these stereotypical associations intact while removing the ones that are the most visible and easiest to measure. 86. Boluk Basie, now at Google, and his colleagues are continuing to work on the issue, affirming that there are cases where a debiased model, used in a recruiting context, may in fact actually be worse than the original model. 87. In such cases, it is possible that a system that deletes the gender dimension entirely, even for such fundamentally gendered terms as he and she, may result in fairer outcomes. The story is not a simple one, and the work continues. Self-portrait in a statistical mirror. In a recruiting application, these biases may simply be dangers to be mitigated, but taken on their own they raise a host of questions. For instance, where do they come from? Are they an artifact of the statistical technique used, or do they reflect something deeper, namely, the bias in our own heads and the bias in the world at large? A classic test of unconscious bias in humans used in the social sciences is the implicit association test, where subjects will see a sequence of words and are asked to press a button anytime the word belongs to either of two different categories. For instance, a flower, e.g., iris, or something pleasant, e.g., laughter. It sounds simple enough, and it is. The story is not in accuracy, but in reaction time. Asking people to press a button if the word is a flower or something pleasant results in quick reaction times, but asking them to press the button if it's a flower or something unpleasant takes longer. This suggests, then, that there is some degree of overlap between the mental categories of floral and pleasant, or that they reflect concepts that are somehow linked. 88. The group that invented this test famously demonstrated that a group of white undergraduates were quick to identify if a word was either prevalently white name, Meredith, Heather, or a pleasant word, lucky, gift. They were also quick to identify if a word was either a prevalently black name, Latonya, Siobhan, or an unpleasant word, poison, grief. But when asked to press a button if the word was a white name or an unpleasant word, they were slow. Likewise, they were slow when they had to press a button if the word was a black name or a pleasant word. A team of computer scientists at Princeton, postdoc Eileen Kaliskin and professors Joanna Bryson and Arvind Narayanan, found that the distance between embeddings in Word 2vec and other widely used word embedding models uncannily mirrors this human reaction time data. The slower people are to identify any two groups of words, the farther away those word vectors were in the model. 89 The model's biases, in other words, are, for better or worse, very much our own. Beyond these implicit associations, the Princeton team also wanted to know if models like Word 2vec capture some of what they call the veridical bias in the world. Certain names really are more commonly given to women than to men, and certain jobs really are more commonly held by women than by men. To the extent that certain names get representations that skew more male than others or more female than others, does that reflect to some degree this objective reality? And to the extent that certain professions fall at different places along the model's gender axis, might that reflect to some degree the fact that certain professions, nurse, librarian, carpenter, mechanic, really do happen to be unevenly balanced? The Princeton team consulted the US Census and the Bureau of Labor Statistics, respectively. In both cases, they found the answer was yes. The more strongly a word representation for a profession skews in a gender direction, the more overrepresented that gender tends to be within that profession. Word embeddings, they write, correlate strongly with the percentage of women in 50 occupations in the United States, 90. Looking at names, they found the same thing, with a correlation only slightly less strong. Then again, the latest census data they had access to was from 1990, and so perhaps the gender distribution of names had in fact changed slightly since then. The fact that the embeddings that emerge from this magical optimization process are so uncannily and discomfortingly useful as a mirror for society means that we have, in effect, added a diagnostic tool to the arsenal of social science. We can use these embeddings to quantify something in precise detail about society at a given snapshot in time. And regardless of causation, whether it's changes in the objective reality that change the way we speak, or vice versa, or whether both are driven by some deeper cause, we can use these snapshots to watch society change. This is exactly what an interdisciplinary group from Stanford, led by Nikhil Gorg and James Zhu, set out to do. Gorg, a PhD candidate in electrical engineering, and Zhu, an assistant professor of biomedical data science, joined with historian Londa Schiebinger and linguist Dan Jarafsky to look at word embeddings using not just a corpus of contemporary text, but samples across the past 100 years. 91 What emerged was a rich and detailed history of the changing winds of culture. As they put it, the temporal dynamics of the embedding helps to quantify changes in stereotypes and attitudes toward women and ethnic minorities in the 20th and 21st centuries in the United States. The Stanford group corroborated the Princeton group's findings about the connection between the representations of profession words and gender, adding that there appears to be something of a male baseline, namely, professions that we know from census data to be evenly split 50-50 between men and women nonetheless have a slight bias in their word embeddings in the male direction. As the authors explain, common language is more biased than one would expect based on external, objective metrics. Baseline aside, however, there is a consistent trend across time that shows the gender bias in word embeddings for professions moving in lockstep with the change in the workforce itself. By looking at texts across time, they found a wealth of narratives reflecting social change. The data show that gender bias has broadly decreased over time, and in particular, that the women's movement in the 1960s and 1970s especially had a systemic and drastic effect in women's portrayals in literature and culture. The embeddings also show a detailed history of the shift in racial attitudes. In 1910, for instance, the top 10 words most strongly associated with Asians relative to whites included barbaric, monstrous, hateful, and bizarre. By 1980 the story could not be more different, with the top 10 words topped by inhibited and passive and ending with sensitive and hearty stereotypes in their own right, of course, but ones that reflect an unmistakable cultural change. More recent cultural shifts are also visible in the embeddings. For instance, the association between words related to Islam and words related to terrorism goes up sharply both in 1993, the year of the World Trade Center bombing, and 2001, the year of 9/11. One might even imagine using such an approach to look not retrospectively, but prospectively. Do the data of the last 6 months, say, suggest that these biases are getting better or getting worse? One might imagine a kind of real-time dashboard of whether society itself, or our public discourse, appears to be getting more or less biased, a bellwether for the shifts underway, and a glimpse of the world to come. Representations and representation. There are several takeaways here, of which the first is principally, though not purely, methodological. Computer scientists are reaching out to the social sciences as they begin to think more broadly about what goes into the models they build. Likewise, social scientists are reaching out to the machine learning community and are finding they now have a powerful new microscope at their disposal. As the Stanford authors write, in standard quantitative social science, machine learning is used as a tool to analyze data. Our work shows how the artifacts of machine learning, word embeddings here, can themselves be interesting objects of sociological analysis. We believe this paradigm shift can lead to many fruitful studies. Second is that biases and connotations, while they seem gossamer, ethereal, ineffable, are real. They are measurable, in detail and with precision. They emerge, spontaneously and reliably, from models built to do nothing but predict missing words, and they are measurable and quantifiable and dynamic. They track ground truth data about labor participation, as well as subjective measures of attitude and stereotypes. All this and more are present in models that ostensibly just predict missing words from context. The story of our language is the story of our culture. Third, these models should absolutely be used with caution, particularly when used for anything other than their initial purpose of predicting missing words. Says Adam Collet, I've talked to people who said that after reading our paper, they are more cautious about using these word embeddings, or at least thinking twice, before they use them in their own applications. So, that's one positive consequence. This note of caution is echoed by the Princeton team. Certainly, they write, caution must be used in incorporating modules constructed via unsupervised machine learning into decision-making systems. 92 Very few Amazon executives would have been likely to explicitly declare a policy of hire the people whom, had they applied 10 years ago, would have most strongly resembled the people we did hire back then. But using language models to filter resumes for relevance is making just such a leap. We find ourselves at a fragile moment in history, where the power and Flexibility of these models have made them irresistibly useful for a large number of commercial and public applications, and yet our standards and norms around how to use them appropriately are still nascent. It is exactly in this period that we should be most cautious and conservative, all the more so because many of these models are unlikely to be substantially changed once deployed into real-world use. As Princeton's Arvind Narayanan puts it, contrary to the tech moves too fast for society to keep up cliché, commercial deployments of tech often move glacially. Just look at the banking and airline mainframes still running. ML, machine learning models being trained today, might still be in production in 50 years, and that's terrifying. 93 modeling the world as it is one thing. But as soon as you begin using that model, you are changing the world, in ways large and small. There is a broad assumption underlying many machine learning models that the model itself will not change the reality it's modeling. In almost all cases, this is false. Indeed, uncareful deployment of these models might produce a feedback loop from which recovery becomes ever more difficult, or requires ever greater interventions. If, say, a resume search system detects a gender skew with a given position, and upranks, say, male applicants in a way that exaggerates that skew, then this may well be the next batch of training data on which the model learns. And it will only learn a more extreme version of its existing bias. The easiest moment in which to intervene is, of course, as soon as possible. Lastly, these models offer us a digital sextant as we look ahead as a society. From this work, we get a portrait not only of our history, but of our up-to-the-minute present. As long as new text is being published online each day, there will be a new set of data to sample. If used wisely, and descriptively rather than prescriptively, the very systems capable of reinforcing and perpetuating the biases latent in society can be used, instead, to make them visible, inarguable. They offer us a gauge on what might have seemed diffuse or formless. Point 94. That's a start. Yonatan Zunga, no longer at Google, argues that people sometimes forget the degree to which engineering is inextricable from human society, human norms, and human values. Essentially, engineering is all about cooperation, collaboration, and empathy for both your colleagues and your customers, he writes. If someone told you that engineering was a field where you could get away with not dealing with people or feelings, then I'm very sorry to tell you that you have been lied to. 95. As for Jackie Alsine, who now runs his own software consultancy and still keeps in touch with Zunga, he agrees that the problem neither begins nor ends with tech. This is actually partly why I want to go into history teaching, he tells me, smiling and at least half serious. When I turn 35, I'll just stop everything, retire, and transition to history. Asterisk, with second place going to Vanessa Paradis, and third to Charlotte Gainsbourg. 2. Fairness. While mankind has been wandering the American continent since the retreat of the glacier, and possibly before the Ice Age, it remains somewhat of a sad commentary on his evolution that one of the problems science has just undertaken is the question of an accurate prediction of what a man will do when released from prison on parole. Chicago Tribune, January 19361. Our law punishes people for what they do, not who they are. Dispensing punishment on the basis of an immutable characteristic flatly contravenes this guiding principle. Supreme Court Chief Justice John Roberts 2. We're on the cusp of using machine learning for rendering basically all kinds of consequential decisions about human beings in domains such as education, employment, advertising, healthcare, and policing. It is important to understand why machine learning is not, by default, fair or just in any meaningful way. Moritz Hart 3. The idea that society can be made more consistent, more accurate, and more fair by replacing idiosyncratic human judgment with numerical models is hardly a new one. In fact, their use even in criminal justice is nearly a century old. In 1927, the new chairman of the Parole Board of Illinois, Hinton Claiborne, commissions a study on the workings of the parole system in the state. He is motivated by what he perceives to be a kind of innovation gap. Although our industrial and governmental machines are far from perfect, we probably are the most ingenious and efficient nation industrially, Claiborne writes. Can we truthfully say this of our law enforcement? For despite Illinois having been one of the very first states to enact a parole law, public opinion has soured. As Claiborne observes, public sentiment is that the pendulum of justice and mercy has swung to the extreme in favor of criminals. His own view is not far off, that the entire concept of parole may amount to little more than undue leniency, and that the parole system should perhaps be scrapped entirely. But he reasons that, under US law, an individual is entitled to a defense, and so the parole system should probably be entitled to one as well. Claiborne asks his state's most prestigious schools, the University of Illinois, Northwestern University, and the University of Chicago, to join forces and prepare a comprehensive report on the parole system to be delivered to him in a year's time. University of Illinois Law School Dean Albert Harno will report on the workings of the parole board. Judge Andrew Bruce of Northwestern will review the history of the penal system in Illinois, including an eye-opening look at the abolition of the lash in the 19th century. And Chicago sociologist Ernest Burgess is given the intriguing challenge to see whether any factors predict the success or failure of a given parolee. As Burgess writes, two widely divergent pictures of the paroled man are, at present, in the minds of the people of Illinois. One picture is that of a hardened, vicious, and desperate criminal who returns from prison, unrepentant, intent only upon wreaking revenge upon society for the punishment he has sullenly endured. The other picture is that of a youth, perhaps the only son of a widowed mother, who on impulse, in a moment of weakness, yielded to the evil suggestion of wayward companions, and who now returns to society from the reformatory, determined to make good if only given a chance. 5. The question, of course, is whether it might be possible to anticipate which potential parolees were which. Burgess gathers data on some 3,000 different Illinois parolees and does his best to categorize them into one of four groups: first offenders, occasional offenders, habitual offenders, and professional offenders. From a 21st century perspective, some of his work seems strikingly dated. For instance, the 8 possible social types into which he divides people are hobo, ne'er-do-well, mean citizen, drunkard, gangster, recent immigrant, farm boy, and drug addict. Nonetheless, Burgess's work appears impressively thorough, particularly for the time, examining criminal histories, work histories, residential histories, type of crime, length of sentence, time served, psychiatric diagnoses, and more. He undertakes a study of whether the data reveals undue political influence on behalf of certain inmates and questions whether the public's jaded view of the justice system is warranted. And in his final chapter, he directly tackles the question that will launch something of a movement in criminal justice, one that will continue well into our present century. Can scientific methods be applied to parole administration? He writes, many will be frankly skeptical of the feasibility of introducing scientific methods into any field of human behavior. They will dismiss the proposal with the assertion that human nature is too variable for making any prediction about it. But in the analysis of factors determining success and failure on parole, some striking contrasts have already been found. Burgess notes, for instance, that parole violation among those with a strong work record, high intelligence, and a farming background, who had served 1 year or less, was half the state average. On the other hand, parole violation among those living in the criminal underworld, whose prosecutors or judges had argued against leniency, and who had served 5 or more years, was twice the state average. Do not these striking differences, which correspond with what we already know about the conditions that mold the life of the person, he asks, suggest that they be taken more seriously and objectively into account than previously? It would be entirely feasible, and should be helpful to the parole board, he says, to devise a summary sheet for each man about to be paroled in order for its members to tell at a glance the violation rate for each significant factor. The prediction would not be absolute in any given case, but, according to the law of averages, would apply to any considerable number of cases. His conclusion is that rehabilitation is, in many cases, eminently possible. What's more, it does appear to be at least somewhat predictable in which cases it will succeed. Wouldn't a system built on this statistical foundation be better than the status quo of subjective, inconsistent, and idiosyncratic human decisions made by judges on the fly? There can be no doubt of the feasibility of determining the factors governing the success or the failure of the man on parole, Burgess writes. Human behavior seems to be subject to some degree of predictability. Are these recorded facts the basis on which a prisoner receives his parole? Or does the parole board depend on the impressions favorable or unfavorable which the man makes upon its members at the time of the hearing? The report's ultimate conclusion is both clear and firm. Parole and indeterminate sentencing should indeed be continued in the state of Illinois, and, just as critically, their administration can and should be improved both by the placing of the work of the parole board on a scientific and professional basis, and by further safeguards against the constant pressure of political influence. Chairman Claiborne reads the report, and he completely changes his mind about the system he oversees. My first impression was that indeterminate sentences and parole laws were an asset to criminals, he admits. Proof to the contrary is overwhelming, and I now believe these laws, properly administered, to be decidedly beneficial to society, as well as to the individual. Parole, put simply, is a good thing, he writes, even where the method of administration is faulty. And of course, no machinery is more efficient than the human element that operates it. 6. Scientific parole in practice. In the early 1930s, buoyed by Burgess's enthusiasm and Claiborne's approval, a predictive parole system goes into use in Illinois, and by 1951 a Manual of Parole Prediction is being published, reporting back on what is now 20 years of both study and practice. The tone is upbeat. Burgess, in the book's introduction, writes, in the past 2 decades, social scientists have made significant progress in their efforts to find out which prisoners succeed on parole and which fail, and under what conditions success or failure occurs. Out of their research has grown a conviction that, notwithstanding the difficulties involved, it is possible to predict to some extent how prisoners will behave on parole. 7. The book notes several areas for future study and possible improvement, for instance additional factors, like evaluations by prison staff, that might help improve predictions. A particularly prescient section at the end of the book, titled Scoring by Machine Methods, considers the use of punch card machines to automate and streamline the process of collecting the data, building the models, and outputting individual predictions. Despite this early optimism and the seeming success story of Illinois, the adoption of parole prediction instruments would be surprisingly slow. By 1970, for instance, just 2 states were using such tools. But that was about to change. In 1969, a Scottish-born statistician named Tim Brennan was working for Unilever in London, building statistical models of a different sort. He was the company's leading expert on market segmentation. One project, for instance, segmented buyers of bathroom soap into those for whom glamour is paramount and those who prioritize gentleness to the skin. He was good at it, and enjoyed the work, but something wasn't right. I had a values crisis, Brennan tells me. A report crossed his desk, and he noticed that Unilever, over the past year, had spent more money studying the packaging for its Skeezy line of squeezable liquid dish soap, the wording and colors that would draw the eye on a supermarket shelf, all backed by the latest in perceptual psychology, than the entire British government had spent on literacy. 8. This was in the late 60s, he says, and you know how the hippie phenomenon was at the time. Anyway, I couldn't see working on developing packs for Skeezy. So I resigned my job, and I applied for graduate school. He ended up at Lancaster University, applying his statistics for market segmentation to the problem of education, identifying students with different learning styles and different needs in the classroom. 9. Following his girlfriend to the United States, Brennan found himself at the University of Colorado, working for Delbert Elliott, who would later become the president of the American Society of Criminology, and then ultimately starting his own research firm, working with the National Institute of Corrections and the Law Enforcement Assistance Administration. His techniques for classification had found a third use, bringing a more consistent and rigorous approach to jails and prisons, each of which has to organize inmates among bunks and wards according to their risks and needs, both for the safety of others and for their own rehabilitation. This was typically done either at random or by instinct. Brennan's math said there was a better way. Brennan took a trip up to Traverse City, Michigan, where he'd heard there was some pioneering machine learning work on using so-called decision tree models to classify inmates and, in response to overcrowding, identify whom to release. There Brennan met this young guy, with straggly hair and a beard, who had invented the model. The young guy's name was Dave Wells. He was on fire about reforming the criminal justice system, says Brennan. It was a job of a passion for Dave. Brennan and Wells decided to team up. 10. They called their company North Point. As the era of the personal computer dawned, the use of statistical models at all points in the criminal justice system, in jurisdictions large and small, exploded. In 1980, only 4 states were using statistical models to Assist in parole decisions. By 1990, it was 12 states, and by 2000 it was 26.11. Suddenly it began to seem strange not to use such models. As the Association of Paroling Authorities International's 2003 Handbook for New Parole Board Members put it, in this day and age, making parole decisions without benefit of a good, research-based risk assessment instrument clearly falls short of accepted best practice. 12. One of the most widely used tools of this new era had been developed by Brennan and Wells in 1998. They called it Correctional Offender Management Profiling for Alternative Sanctions. Or Compass. 13 Compass uses a simple statistical model based on a weighted linear combination of things like age at first arrest, and criminal history to predict whether an inmate, if released, would commit a violent or non-violent crime within approximately 1 to 3 years. 14 It also includes a broad set of survey questions to identify a defendant's particular issues and needs, things like chemical dependency, lack of family support, and depression. In 2001, the state of New York began a pilot program using Compass to inform probation decisions. By the end of 2007, all 57 of its counties outside of New York City had adopted the use of the Compass tool in their probation departments. And by 2011, state law had been amended to require the use of risks and needs assessments like Compass when making parole decisions. 15. But, from the perspective of the New York Times editorial board, there was a problem. The tools, even where their use was mandated, still were not always given appropriate consideration. The Times urged wide acceptance of risk assessment tools in parole, writing in 2014, programs like Compass have been proved to work. 16 In 2015, as a parole reform case went before the state's highest court, the editorial board published a second opinion piece, arguing again that statistical risk assessment tools like Compass offered a significant improvement over the status quo. They alleged that the New York Parole Board clings stubbornly to the past, routinely denying parole to long-serving inmates based on subjective, often unreviewable judgments. Adoption of Compass, they wrote, would drag the board into the 21st century. 17 Then, abruptly, the tone changed. 9 months later, in June 2016, the paper ran an article titled In Wisconsin, a backlash against using data to foretell defendants' futures, which closed by quoting the director of the ACLU's criminal law reform project saying, I think we are kind of rushing into the world of tomorrow with big data risk assessment. 18. From there the coverage in 2017 only got bleaker. In May, sent to prison by a software program's secret algorithms. In June, when a computer program keeps you in jail, and in October, when an algorithm helps send you to prison. What had happened? What had happened was, in a word, ProPublica. Getting the data. Julia Angwin grew up in Silicon Valley in the 1970s and 80s, the child of 2 programmers and a neighbor of Steve Jobs. She assumed from an early age she'd be a programmer for life. Along the way, however, she discovered journalism and fell in love with it. By 2000, she was a technology reporter for the Wall Street Journal. It was hilarious, she recounts. They were like, you know computers. We'll hire you to cover the internet. And I was like, well, anything in particular about the internet? And they're like, no, everything. 19 Angwin stayed at the paper for 14 years, from the dot-com crash through the rise of social networks and smartphones, writing not only about technology itself, but also the social questions it often left in its wake. She authored a long-running series on privacy-related issues called What They Know. She went on leave from the journal, writing a book about privacy, in 2013.20. Angwin never came back to the paper from her book sabbatical and instead joined ProPublica, a non-profit news outlet started by former Wall Street Journal managing editor Paul Steiger. If the theme of her earlier work was what they know, the answer inevitably raised another question: what are they going to do with it? And so I thought, she says, I need to move to data usage. That is the next story. What are they going to do? What kind of judgments are they going to make about you? 21 Angwin set about trying to find the most consequential and overlooked decisions being made based on data. She landed at criminal justice. Statistical risk assessments, Compass and others, were rapidly being adopted in hundreds of jurisdictions, not just for parole, but for pretrial detention, bail, and even sentencing. I was shocked, actually, she says. I realized that our whole country was using this software. And then what I found even more shocking was that none of them had independently been validated. New York State, for instance, which had been using Compass since 2001, did its first formal evaluation of the software in 2012, after 11 years of use. New York ultimately found that it was both effective and predictively accurate. 22. Stories like this are stunningly common. Minnesota's 4th Judicial District, which includes Minneapolis and handles 40% of all cases filed in the state, had developed their own pretrial risk assessment tool in 1992. The report that was written at that time suggested that this new scale should be validated within the first few years of use. The state's official evaluation begins. As it turned out, it has been closer to 14 years, 23. The long overdue evaluation, in 2006, found that 4 of the variables in their model, whether the defendant had lived in Minnesota for more than 3 months, whether they lived alone, their age at the time of booking, and whether a weapon was involved in their charge, had virtually no bearing whatsoever on their actual risk of committing a new offense while waiting for their trial date, or of missing a required court appearance. And yet the model had been recommending pretrial detention on those grounds. Worse, 3 of those 4 factors strongly correlated with race. The district scrapped their model and started over from scratch. 24 The more Angwin learned about risk assessment models, the more concerned she became. Angwin knew she had found her next story. From a journalist's perspective, it's the perfect storm. It's something that's never been audited. It has extremely high human stakes, and people who are very smart are like, these are all proxies for race. And so I was like, I'm going to test this. 25 She decided to focus on Compass in particular, which was being used not just in New York, but in California, Wisconsin, Florida, some 200 different jurisdictions in total. It was ubiquitous, at that time not well studied, and, being a closed source, proprietary tool, though its basic design was available in white papers, something of a black box. In April 2015, she submitted a Freedom of Information Act request to Broward County, Florida. After 5 months of legal scuffling, the data at last came through. All 18,000 Compass scores given in Broward County during 2013 and 2014. Angwin's team began doing some exploratory data analysis. Immediately something looked strange. The risk scores, which range from 1, meaning lowest risk, to 10, meaning highest risk, were more or less evenly distributed for black defendants, with roughly 10% of defendants in each of the 10 buckets. For white defendants, they saw a totally different pattern, vastly more defendants in the very lowest risk bucket, and vastly fewer in the highest risk buckets. Angwin was tempted to publish a story then and there. But she realized that the wildly different distributions weren't necessarily evidence of bias. Perhaps it was just actually how risky those defendants happened to be. So, how risky did those defendants turn out to be? There was only one way to find out. I had the sad realization, Angwin recounts, that we had to look up the criminal records of every one of those 18,000 people. Which we did. And it sucked. 26 to link the set of Compass scores to the set of criminal records, what data scientists call a join, would take Angwin and her team, and the county staff, almost an entire additional year of work. We used, obviously, a lot of automated scraping of the criminal records, she explains. And then we had to match them on name and date of birth, which is the most terrible thing you could possibly ever imagine. There's so many typos, so many spelling errors. I might have cried every day. It was so awful trying to do that join. The data was so messy. Broward County actually themselves had never done the join. 27 county staff pitched in to help ProPublica clean the data and make sense of it. What resulted was the piece that Angwin and her team published in May 2016. Titled Machine Bias, it ran with the logline "There's software used across the country to predict future criminals. And it's biased against blacks." 28 Brennan and his North Point colleagues, in early July, published an official rebuttal to ProPublica's findings. 29 in their words, when the correct classification statistics are used, the data do not substantiate the ProPublica claim of racial bias towards blacks. 30 namely, they said, Compass met 2 essential criteria for fairness. First, its predictions were just as accurate for black defendants as they were for white defendants. Second, its 1 to 10 risk scores had the same meaning, regardless of the defendant's race, a property known as calibration. Defendants rated with a risk score of 7 out of 10, say, for committing a violent reoffense went on to reoffend the same percentage of the time, regardless of race, ditto for a risk score of 2, 3, and so forth. A 1 was a 1, a 5 was a 5, and a 10 was a 10, regardless of race. Compass had both of these properties, equal accuracy and calibration, and because of this, North Point argued, it was essentially mathematically impossible for the tool to be biased. By the end of July, ProPublica responded in turn. 31 North Point's claims, they wrote, were true. Compass really was calibrated, and it was equally accurate across both groups, predicting with 61% accuracy for black and white defendants alike whether they would go on to reoffend, recidivate, and be rearrested. However, the 39% of the time it was wrong in strikingly different ways. Looking at the defendants whom the model misjudged revealed a startling disparity. Black defendants were twice as likely to be rated as higher risk, but not reoffend. And white defendants were twice as likely to be charged with new crimes after being classed as lower risk. 32 The question of whether the tool was fair in its predictions had sharpened into the question of which statistical measures were the correct ones by which to define and measure fairness in the first place. The conversation was about to take a new turn, and it would come from another community entirely, one that had also begun to slowly but surely train its attention on the question of fairness. What fairness is not. Harvard computer scientist Cynthia Dwork is arguably best known for developing a principle called differential privacy, which enables companies to collect data about a population of users while maintaining the privacy of the individual users themselves. A web browser company might want to understand user behavior, but without knowing which sites you personally went to, or a smartphone company might want to learn how to improve their spelling correction, or text suggestions without knowing the details of your personal conversations. Differential privacy made this possible. It would come to be almost ubiquitous in major tech companies starting around 2014, and would win Dwork the Gödel Prize, one of computing's highest honors. 33, but in the summer of 2010, however, she saw her theoretical work as done, and she was on the hunt for a new problem. I had started working in privacy in 2001, she explains. Differential privacy was differential privacy by 2006. I had in my mind one last set of questions I wanted to look at, and I did that work, and then I said, okay, I want to think about something else. 34. Dwork, then at Microsoft Research, came up to Berkeley to meet with fellow computer scientist Amos Fiat. They spent the entire day talking. By lunchtime, as they sat down together in beloved local restaurant Chez Panisse, they had landed on the topic of fairness. Dwork recalls, in order that the people around us wouldn't be disconcerted by our discussions of racism and sexism, we were using terms like purple ties, and striped shirts, and stuff like that. But by lunchtime we were onto this. The term fairness in theoretical computer science comes up in a number of contexts, from game theoretic mechanisms for cutting a cake, or dividing an inheritance, so that everyone gets a proper share, to scheduling algorithms that ensure that every process on a CPU gets to run for an appropriate amount of time. But there was something more to the idea of fairness, Dwork thought, that the field had yet to truly reckon with. As it happens, Dwork had read one of Julia Angwin's What They Know columns in the Wall Street Journal on the topic of online advertising. It showed that as early as 2010, if not before, companies could discern nearly the exact personal identity of every user visiting their websites, narrowing an ostensibly anonymous user down to one of just several dozen possible people, and were making split-second decisions about cards to suggest to whom. 35 Having thought about the privacy side for the previous decade, Dwork too began to shift her thinking from the question of what they know to the question of what they're doing with it. Dwork came back to her lab at Microsoft and said, I found our problem. One of her lab members was then PhD student Moritz Hart, interning that summer from Princeton. Hart hadn't started off wanting to work on real-world problems. He was interested in theory, complexity, intractability, randomness. The more abstract, the better. No applications, he jokes. Old school, 36, I learned a lot, he says, but I found the range of problems I could address in that space, it didn't get at the questions about the world I was curious about. And I quickly got attracted by some of the more social problems that in computer science was touching on. This had started with privacy-preserving data analysis, working with Dwork. She pulled him into the Fairness Project. As Hart recalls, Cynthia had the hunch that sometimes when people were asking for privacy, they were actually worried about somebody using their data in the wrong way. It wasn't so much about hiding the data at all costs, but preventing harm from the way that data was used. That was a pretty accurate hunch. Over time, the public discussion shifted from privacy to fairness, and everything that used to look like a privacy problem suddenly looked like a fairness problem. What they and their colleagues began to find was that not only were there enormous complexities in translating our philosophical and legal ideas about fairness into hard mathematical constraints, but in fact, much of the leading thought and practice, some of it decades old, was deeply misguided, and had the potential to be downright harmful. U.S. anti-discrimination law, for instance, defines a number of protected attributes, things like race, gender, and disability status, and it is typically understood that one should strictly prohibit the use of these variables in machine learning models that might affect people in settings like hiring, criminal detention, and so on. If we hear in the press that a model uses race or gender, etc., as an attribute, we are led to believe something has already gone deeply wrong. Conversely, the company or organization behind a model typically defends its model by showing that it doesn't use race as an attribute, or is race blind. This seems intuitive enough. How can something be discriminatory toward a particular group if it doesn't know who is in that group to begin with? This is a mistake, for several reasons. Simply removing the protected attribute is insufficient. As long as the model takes in features that are correlated with, say, gender or race, avoiding explicitly mentioning it will do little good. As we discussed in the case of the Boston Symphony Orchestra, and moreover, in the resume screening language models, simply omitting the variable you're concerned about, gender, in that case, may not be enough, particularly if there are other factors that correlate with it. This is known as the concept of redundant encodings. The gender attribute is redundantly encoded across other variables. In a criminal justice context, a history of treating one demographic group differently creates redundant encodings all over the place. Policing a minority neighborhood more aggressively than others, for instance, means that all of a sudden something as seemingly neutral as length of rap sheet, i.e., number of previous convictions, can become a redundant encoding of race. Point 37, because of redundant encodings, it's not enough to simply be blind to the sensitive attribute. In fact, one of the perverse upshots of redundant encodings is that being blind to these attributes may make things worse. It may be the case, for instance, that the maker of some model wants to measure the degree to which some variable is correlated with race. They can't do that without knowing what the race attribute actually is. One engineer I spoke with complained that his management repeatedly stressed the importance of making sure that models aren't skewed by sensitive attributes like gender and race, but his company's privacy policy prevents him and the other machine learning engineers from accessing the protected attributes of the records they're working with. So, at the end of the day, they have no idea if the models are biased or not. Omitting the protected attribute makes it impossible not only to measure this bias, but also to mitigate it. For instance, a machine learning model used in a recruiting context might penalize a candidate for not having had a job in the prior year. We might not want this penalty applied to pregnant women or recent mothers, however, but this will be difficult if the model must be gender blind and can't include gender itself, nor something so strongly connected to it as pregnancy. 38. The most robust fact in the research area, Hart says, is that fairness through blindness doesn't work. That's the most established and most robust fact in the entire research area. 39. It will take time for this idea to percolate from the computer scientists through to legal scholars, policymakers, and the public at large, but it has begun making its way. There may be cases where allowing an algorithm to consider protected class status can actually make outcomes fairer, as a recent University of Pennsylvania Law Review article put it. This may require a doctrinal shift, as, in many cases, consideration of protected status in a decision is presumptively a legal harm. 40. The summer Moritz Hart had spent working with Cynthia Dwork had borne fruit, in the form of a paper that established some of these early results. Point 41 more than the results themselves. The paper was a beacon, signaling to their fellow theoreticians that there was something here worth looking into, something with both meaty open theoretical questions and undeniable real-world importance. Back at Princeton and finishing his PhD, Hart found himself set up on a kind of academic blind date. Dwork had been talking with Helen Niesenbaum, herself a pioneer in thinking about ethical issues in computing. Point 42 Niesenbaum had a fellow graduate student in the area named Solan Barokas, and she and Dwork realized their respective mentees might be kindred spirits. Point 43 The first meeting got off to an awkward start. Hart was sitting at a table at Sakura Express Sushi, on Witherspoon Street in Princeton. In walked Barokas. He sits down, Hart recalls, and he pulls out the paper, and to my dismay, he had, with yellow marker, like, carefully underlined passages in the paper. That's not how you're supposed to read a computer science paper. He laughs. Till that point I had always thought of words in a paper as a filling for the math. And it was very embarrassing, because what I'd written made no sense. The two got to talking. Bumpy start aside, the resonance their mentors had suspected was clearly there. Ultimately, the two decided to submit a proposal to the 2013 Neural Information Processing Systems, new IPS, conference to present a workshop on fairness. New IPS said no. The organizers felt there wasn't enough work or material on this, Hart tells me. Then in 2014, Solan and I got together and said, okay, let's try one more time before we give up. They gave it a new name and a broader mandate: fairness, accountability, and transparency in machine learning, or FATML for short. This time New IPS said yes. A day-long workshop was held at that year's conference in Montreal, with Barokas and Hart introducing the proceedings and Dwork giving the first talk. Hart graduated and went from Princeton to IBM Research. He kept chipping away at fairness questions in the background. I always had to have another thing to continue to exist as a computer scientist. In terms of my career, this was always like a side project. IBM, to its credit, gave him a lot of freedom, even if his passion wasn't widely shared. My group at IBM wasn't particularly interested in that topic, he says, but neither was anybody else. The two came back and repeated the conference again in 2015. The room was full, Hart recalls, people attended, but it didn't spark a revolution at that point, it's safe to say. He kept spending the lion's share of his time on more conventional computer science. Another year went by, and he and Solan reprised their FATML workshop for a third time. This time, something was different. 2016 was the year where it got out of hand, Hart says, the year where somehow everybody started working on this. Mathematician and blogger Cathy O'Neill, who'd presented at the original 2014 conference, had published the best-selling book Weapons of Math Destruction, about social problems that can stem from the careless, or worse, use of big data. A series of shocking election results, defying the consensus of pollsters worldwide, had shaken confidence in the trustworthiness of predictive models. Meanwhile, the work of data-driven political firms like Cambridge Analytica had raised questions about machine learning being wielded to directly influence politics. Platforms like Facebook and Twitter were caught in the crossfire over how and whether to use machine learning to filter the information being shown to their billions of users. And a group of reporters at ProPublica had, after a year of tireless data cleaning and analysis, gone public with their findings about one of the country's most widely used risk assessment tools. Fairness was no longer just a problem. It was becoming a movement. The impossibility of fairness. Since 2012, Cornell computer scientist John Kleinberg and University of Chicago economist Sendhil Mullainathan had been working on a project using machine learning to analyze pretrial detention decisions, comparing human judges against predictive machine learning models. Part of that is thinking through what are the concerns that people have about algorithmic tools in the context of racial inequities, Kleinberg says. I think we had done a fair amount of thinking about that. Then the ProPublica article appeared, and our social media channels just got completely filled with reshares of this article. It was just really capturing people's attention. We felt like they put their finger on something. Let's really dig into it and figure out how does this relate to the themes that we've been thinking about. 44 in Pittsburgh, Carnegie Mellon statistician Alexandra Choldachova had been working since the spring of 2015 with the Pennsylvania Commission on Sentencing, developing a visual dashboard to explore various mathematical properties of risk assessment tools. I started thinking more and more about these issues, to understand different notions of fairness in terms of classification metrics, and how those relate, she says. All of that was happening while I was still focused on other projects. I'd been talking to my senior colleague about maybe writing a paper about some ideas on the validation of risk assessment instruments, and we'd done our literature review and everything like that, and the ProPublica piece hits. I think that really accelerated a lot of people's thinking in the area. 45. An almost identical narrative was playing out on the other side of the country. Stanford doctoral student Sam Corbett Davies had started his degree, wanting to do robotics, just like straight computer science. A year in, he found that he simply wasn't enjoying it, and at the same time was obsessively reading about US public policy just as a hobby. I was like, I've got to find a way to sort of combine the technical skills I have with something that's a bit more policy-focused. 46 An assistant professor named Sharad Goel had recently joined the faculty, working on computational and statistical approaches to public policy. 47 A collaboration seemed obvious, and in short order the two began working on a number of projects examining bias in human decisions, including things like a close look at traffic stops in North Carolina. They found, for instance, that police appeared to apply a lower standard when searching black and Hispanic drivers than white drivers, searching them more often and finding contraband less of the time. 48. We're working on this, Corbett Davies explains. We're sort of thinking about these criminal justice issues, and what it means for discrimination to occur. Then, the ProPublica article came out. ProPublica emphasized the types of errors Compass made, and highlighted the fact that it appeared to consistently overestimate the risk of black defendants, who didn't reoffend, and underestimate the risk of white defendants, who did reoffend. North Point highlighted the rate, rather than the kind, of errors and emphasized that the model was equally accurate in its predictions of both black and white defendants and that, moreover, at every risk score from 1 to 10, Compass was calibrated a defendant with that score is equally likely to reoffend, whatever their race. The question of whether Compass was fair appeared, then, to boil down to a conflict between two different mathematical definitions of fairness. As sometimes happens in science, the time is so ripe for a certain idea or insight that a group of people have it almost in unison. A trio of papers emerge. 49 All three efforts turn up similar, complementary takes. The news is not good. Kleinberg says, having identified as the crux of the debate ProPublica's definition of fairness, the propensity for black defendants, who would not go on to reoffend being almost twice as likely as their white counterparts to be miscategorized as high risk, we could then basically line it up with other definitions people had been paying more attention to and ask, to what extent are these compatible? The answer was, they aren't compatible. Only in a world in which black and white defendants happen to have equal base rates, that is, happen to actually reoffend exactly as often as one another, would it be possible to satisfy ProPublica's and North Point's criteria at the same time. Otherwise, it is simply impossible. This has nothing to do with machine learning. Nothing to do with criminal justice as such. It is simply, Kleinberg and his colleagues write, a fact about risk estimates when the base rates differ between two groups. 50 Choldachova's analysis lands exactly in the same place. A tool that is calibrated, she writes, cannot have equal false positive and negative rates across groups, when the recidivism prevalence differs across those groups. So you just can't have it all, she says. It's a general principle, but in this case it leads you to interesting conclusions that have implications for risk assessment in the real world. 51 One of those implications is that if a set of equally desirable criteria are impossible for any model to satisfy, then any expose of any risk assessment instrument whatsoever is guaranteed to find something headline-worthy to dislike. As Sam Corbett Davies explains, there isn't a world in which ProPublica couldn't have found some number that was different that they could call bias. There's no possible algorithm, there's no possible version of Compass, where that article wouldn't have been written. 52 Ironically, in his analysis of the Broward County data, Corbett Davies discovered that Compass is not calibrated with respect to gender. A woman with a risk score of 5 reoffends about as often as a man with a risk score of 3, he says. 53, ProPublica, could have written that article. 54. The brute mathematical fact of this impossibility also means that these problems affect not just machine learning models of risk assessment, but any means of classification, human or machine. As Kleinberg writes, any assignment of risk scores can in principle be subject to natural criticisms on the grounds of bias. This is equally true whether the risk score is determined by an algorithm or by a system of human decision makers. 55. Having established, then, the answers to the question of how these different, seemingly equally intuitive, equally desirable measures of fairness can be reconciled, they can't, and the question of whether good old-fashioned human judgment is any better in this regard, it isn't, a further question suggests itself. Now what? After impossibility. I ask John Kleinberg what he makes of his own impossibility result, and what he thinks it suggests we ought to do. I don't have anything particularly controversial to say on this, he says. I think it depends. I think they're both important definitions, and which one carries more weight depends on the domain you're working in. It's true that critical aspects of these trade-offs change radically from one domain to another. Consider, for instance, the domain of lending, which differs from criminal justice in a number of important ways. Denying a loan to someone who would have paid it back not only means lost interest income for the lender, but potentially serious consequences for the borrower. There is a home they can't purchase, a business they can't start. On the other hand, making the opposite mistake, loaning money to someone who doesn't pay it back, might only be a monetary loss for the lender. Maybe this asymmetry changes our sense of what fairness means in that setting. Maybe we want to ensure, for instance, that all creditworthy borrowers from two different groups have the same chance of getting a loan, even if, for instance, the math tells us that not only will profit for lenders be reduced, but also that more unworthy people will get loans in one group than another. 56. In a criminal justice setting, however, and particularly in the context of violent crime, both false positives, high-risk people who don't reoffend, and false negatives, low-risk people who do reoffend, have a serious human toll. The trade-offs we seek are likely to be quite different as a result. Sam Corbett-Davies has argued, for instance, that equalizing false positive rates in a risk assessment context, ensuring that the defendants who won't reoffend, be they black or white, are no more likely to be improperly detained, would, so long as the actual rates of offense between the groups are different, entail applying different standards to defendants of different races. For instance, it might mean detaining every black defendant who is a risk of 7 or greater, but detaining every white defendant who is a 6 or greater. Such an approach, he says, probably violates the Equal Protection Clause of the 14th Amendment. 57. It's actually even worse than that, he says. Because we're detaining low-risk defendants while releasing some relatively high-risk defendants. There's going to be an increase in violent crime committed by released defendants. And because we know that a crime generally occurs within communities as opposed to between communities, this crime will be concentrated in minority neighborhoods, and the victims will also bring a 14th Amendment case. 58. The impossibility proofs also show that equalizing the false positive and false negative rates means giving up on calibration, namely, the guarantee that for every numerical risk level, the chance of a defendant reoffending is the same regardless of gender or race. Without calibration, says Corbett-Davies, it's unclear what it means to have a risk score. So if you ask me, how risky is this defendant, and I say, they are 2, and you say, what does that mean, and I say, well, if they're male, it means there's a 50% chance they'll reoffend. If they're female, it means there's a 20% chance they'll reoffend. You can see how 2 loses its meaning. 59. Tim Brennan shares the view that calibration is paramount. If a black guy and a white guy both score 7, does that have the exact same rate of failure for the two of them? The arrest rate. The standard method is to make sure, damn sure, that your calibration is not racially biased and your accuracy level is about the same. And we've got both. And if we did something else, we would be breaking the law. 60. However, even those who emphasize the importance of calibration think that it alone isn't enough. As Corbett-Davies says, calibration, though generally desirable, provides little guarantee that decisions are equitable. 61. Just because these properties can't be satisfied all at once in their entirety, however, doesn't mean we can't look for certain trade-offs between them that might be better than others. Other researchers have been exploring the space of these possible trade-offs, and the work continues. Point 62. I ask Julia Angwin what she herself makes of the storm of theoretical results that her article prompted, and of the ultimate impossibility of doing what her team seemed to demand, namely, to make a tool both equally calibrated and with an equal balance of false positives and false negatives. So what I feel about that, she says, is that that's a policy question. And that's a moral question. But what I'm really happy about is no one knew that that was a question until we came up with it. To me, that is like the greatest thing as a journalist. I do feel that defining the problem so accurately allows it to be solved. 63. Not everyone welcomes the public dialogue that ProPublica's work spurred. A group of criminal justice scholars, led by Anthony Flores, published a rejoinder to the initial ProPublica report, not only defending Compass as a calibrated model and calibration as the appropriate measure of fairness, but furthermore, lamenting the damaging effects of the controversy itself. Point 64. We are at a unique time in history, they write. We are being presented with the chance of a generation, and perhaps a lifetime, to reform sentencing and unwind mass incarceration in a scientific way, and that opportunity is slipping away because of misinformation and misunderstanding about the statistical risk assessment models. Poorly conducted research or misleading statements can lead to confusion and or paralysis for those charged with making policy. Tim Brennan shares much of this concern, and of course, sharply disagrees with ProPublica's characterization of Compass. But when I ask him if there is a silver lining to the controversy, in particular the cross disciplinary movement it has generated within and beyond computer scientists, he agrees. I think unpacking fairness into its various different coefficients, alerting people to the meanings, benefits, costs, and the impossibility of using certain coefficients. Once you understand a problem or name a problem, solutions become, certainly, more sought after than if you don't even know the problem existed. 65. Most in the computer science community agree that these things are better discussed openly than not. I mean, so first of all, the math is the math, says Cynthia Dwork. So the best we can hope for is what the math will permit. And we are much, much better off knowing what the limits are than not. 66. For Moritz Hart, the initial wave of academic and technical work following ProPublica's study has legitimated ethical concepts like fairness as valid topics for research, not only in academic departments, but also in the corporate world. Hart himself was at Google in 2016 when this wave of work, including his own, appeared, and recounts the impact he observed. Before that, people weren't even so sure, is this something we should even be touching? It was a hot potato, he says. From 2016 onward there was an explosion of interest and research, both within Google and beyond. So that's something I'm proud of, Hart says. It actually made a difference for the culture. 67. For John Kleinberg, the role of computer science in questions like these is to furnish the stakeholders with the tools to articulate the issue. Our point is not to tell you which one is right and which one is wrong, but to give you the language to have that discussion. I certainly view this as part of my mandate as a computer scientist, to take things that have always existed informally and qualitatively, and try and think about, can we actually talk about them rigorously and precisely? Because the world is moving in that direction. The world certainly is. In the late summer of 2018, California passed SB 10, a monumental justice reform bill that would eliminate cash bail altogether, leaving the state with the choice simply to detain or release a defendant awaiting trial, and furthermore, mandated the use of algorithmic risk assessment tools in informing these determinations. 68. Just before the end of that year, the U.S. Congress, in a strikingly bipartisan vote, passed the First Step Act, a sweeping criminal justice reform bill that, among its many reforms, required the Department of Justice to develop a statistical model that will be used to assess the recidivism risk of all federal prisoners, as well as to determine their course of rehabilitation. 69. Though the sudden and widespread adoption of these tools is only increasing, the race between their adoption and the wisdom with which they are built and used at least appears to be drawing somewhat closer to even. We are coming, haltingly, to a clearer understanding of what it means to make good predictions of this kind. A bigger question lurks behind this discussion, however, which is whether prediction is really even what we want to be doing at all. After the ProPublica story broke, a Washington Post reporter called Choldachova to ask for her response. The reporter had essentially two questions. The first was about the tension between ProPublica's claims and North Point's defense. There I had an answer prepared, says Choldachova. If the prevalence of reoffense differs across populations, then you can't have everything hold all at once. What I didn't have a ready-canned answer for was when he asked, what actually matters? And so, that's really the question that prompted me to think about things from a different perspective. 70. Beyond prediction. Although prediction is feasible on the basis of data now accessible, exclusive reliance should not be placed on this method. Ernest Burgess. 71. Your scientists were so preoccupied with whether or not they could, that they didn't stop to think if they should. Jeff Goldblum as Ian Malcolm, Jurassic Park. One of the most important things in any prediction is to make sure that you're actually predicting what you think you're predicting. This is harder than it sounds. In the ImageNet competition, for instance, in which AlexNet did so well in 2012, the goal is to train machines to identify what images depict. But this isn't what the training data captures. The training data captures what human volunteers on Mechanical Turk said the image depicted. If a baby lion, let's say, were repeatedly misidentified by human volunteers as a cat, it would become part of a system's training data as a cat, and any system labeling it as a lion would be docked points, and would have to adjust its parameters to correct this error. The moral of the story: sometimes the ground truth is not the ground truth. Gaps of this kind are even more significant in the case of criminal justice predictions. One often talks in shorthand of predicting recidivism itself, but that's not what the training data captures. What the training data captures is not reoffense, but rather rearrest and reconviction. This is a potentially crucial distinction. Christian Lum, lead statistician at the Human Rights Data Analysis Group, and William Isaac of the Department of Political Science at Michigan State articulated this in a 2016 paper on the use of predictive models in policing. Because this data is collected as a byproduct of police activity, predictions made on the basis of patterns learned from this data do not pertain to future instances of crime on the whole. They pertain to future instances of crime that becomes known to police. In this sense, predictive policing is aptly named. It is predicting future policing, not future crime. 72. As it happens, this critique was being made all the way back in the 1930s. When the parole reform proposed by Ernest Burgess was deployed in Illinois, critics, particularly those skeptical of parolees' ability to return productively to society, argued that the official figures underestimated the rate of reoffense. As Elmer J. Schnack-Eckenberg, the Republican minority leader in the Illinois House of Representatives, complained in 1937, because a parolee isn't caught at crime during the first or second years of his parole, he is listed during those 2 years as having made good. 73. This gap between what we intend for our tool to measure and what the data actually captures should worry conservatives and progressives alike. Criminals who successfully evade arrest get treated by the system as low risk, prompting recommendations for the release of other similar criminals. And the overpoliced and wrongfully convicted become part of the alleged ground truth profile of high-risk individuals, prompting the system to recommend detention for others like them. This is particularly worrisome in the context of predictive policing, where this training data is used to determine the very police activity that, in turn, generates arrest data, setting up a potential long-term feedback loop. 74. A person who commits crimes in an area that is less aggressively policed, or who has an easier time getting their charges dropped, will be tagged by the system as someone who did not recidivate. And even fewer police will be dispatched to that neighborhood. Any pre-existing disparity in policing between two otherwise similar neighborhoods is likely only to grow. As Lum and Isaac put it, the model becomes increasingly confident that the locations most likely to experience further criminal activity are exactly the locations they had previously believed to be high in crime. Selection bias meets confirmation bias. 75. The system begins to sculpt the very reality it is meant to predict. This feedback loop, in turn, further biases its training data. Lum and Isaac conclude not only that drug crimes known to police are not a representative sample of all drug crimes, but, what's more, rather than correcting for the apparent biases in the police data, the model reinforces these biases. The locations that are flagged for targeted policing are those that were, by our estimates, already overrepresented in the historical police data. 76. There is reason to believe we already have significant disparities in the present day. As Alexandra Choldachova notes, self-reported marijuana use rates among young black males and young white males are roughly the same. But the arrest rates for marijuana-related crimes are 2.5 to 5 times higher among black young males. 77, a 2013 report by the ACLU found that on average a black American is 4 times more likely to be arrested for marijuana possession than a white person in Iowa and Washington, D.C. For instance, the disparity is more than 8-fold. 78. A 2018 investigation by the New York Times found that black residents of Manhattan were 15 times more likely than white residents to be arrested on marijuana charges, despite similar rates of use. 79. There are options here to mitigate these issues in a model. The Compass model, for instance, makes 3 distinct predictions of risk: violent reoffense, and failure to appear in court. Violent crimes, for instance, homicides, are much more consistently reported to police than non-violent crimes, and the police, in turn, are more consistent about enforcement and arrest. And all failures of a defendant to appear in court, by definition, become known to the court system, leaving virtually no room for bias sampling or differential enforcement. A wise use of risk assessment tools, then, might emphasize the violent reoffense and failure to appear predictions over the non-violent reoffense prediction, on the grounds that the model's training data is more trustworthy in those cases, which is exactly what a number of jurisdictions are beginning to do. 80. Other mitigations include somehow building the model to take into account vast disparities in enforcement of certain offenses, treating, say, a black Manhattanite with several marijuana arrests no differently than a white Manhattanite with just one. Of course, this would require the model to use the defendant's race as an input. A third mitigation in the case of marijuana, in particular, is to simply cut the Gordian knot by legalizing, or at least decriminalizing it, which then makes downstream machine learning questions moot. A second, and equally serious, concern is whether, even if a predictive model measured exactly what it claimed to, we are in practice using it for its intended purpose, or for something else. For instance, some states are using the Compass tool to inform sentencing decisions, something that many regard as an awkward if not inappropriate use for it. Says Christine Remington, Wisconsin Assistant Attorney General, we don't want courts to say, this person in front of me is a 10 on Compass as far as risk, and therefore I'm going to give him the maximum sentence. But Compass has been used to inform sentencing decisions, including in Wisconsin. When Wisconsinite Paul Zille was given a longer than expected sentence in part due to his Compass score, Zille's public defender called none other than Tim Brennan himself as a witness for the defense. Brennan testified that Compass was not designed to be used for sentencing. 81 at a minimum, it seems clear that we should know exactly what it is that our predictive tools are designed to predict, and we should be very cautious about using them outside of those parameters. Use only as directed, as the label reads on prescription medications. Such reminders are just as necessary in machine learning. Zooming out even further, however, we might challenge one of the most fundamental unspoken premises of the entire enterprise, that better predictions lead to better public safety. At first it seems crazy to think otherwise. But there are reasons to pause, and to challenge some of the assumptions that underlie that view. Columbia law professor Bernard Harcourt, in his book Against Prediction, which Angwin cites as an inspiration for her own work, raises several such objections. As he argues, the link between better predictions and less crime isn't as straightforward or foolproof as it may seem. For instance, imagine a predictive tool that identifies that most reckless drivers are male. It may be the case that aggressively pulling over male drivers doesn't substantially reduce their recklessness on average, but does cause female drivers, who recognize that they are less likely to be pulled over, to drive more recklessly. In that case, roads may become less safe on average, precisely because of the use of this predictive policy. In other words, as Harcourt puts it, profiling on higher past, present or future offending may be entirely counterproductive with regard to the central aim of law enforcement, to minimize crime. 82 These sorts of backfiring scenarios are not as far-fetched or rare as they may seem, he argues. They may well describe exactly what is currently happening, for instance, with drug use and tax fraud. If differential enforcement emboldens the overlooked group more than it deters the scrutinized group, it may only make the problem worse. Predictions also might fail at the ultimate goal of making society safer if they can't be meaningfully turned into actions. In 2013, the city of Chicago piloted a program designed to reduce gun violence by creating a strategic subjects list, informally a heat list of people at high risk of being victims of gun violence. Those people as a group turned out to be 233 times more likely than the average Chicagoan to become homicide victims. In this sense, the list's predictive power appeared to be spot on. Homicides are so rare, though, that even among those on the heat list, only 0.7% were victimized, while 99.3% were not. What do you do, then, with that predictive information? What kind of intervention for 1,000 people would help the 7 that will actually go on to be victims? By leveraging advanced analytics, police departments may be able to more effectively identify future crime targets for preemptive intervention, noted a 2016 Rand Corporation report on predictive policing in Chicago. 83 However, improvements in the accuracy of predictions alone may not result in a reduction in crime. Perhaps more importantly, law enforcement needs better information about what to do with the predictions. Emphasis mine. 84 Predictions are not an end in themselves. What is better? A world in which we can be 99% sure where a crime will occur and when, or a world in which there is simply 99% less crime? In a narrow-minded pursuit of predictive accuracy, or, for that matter, fairness in a particular prediction tool, we may be missing something larger. 85 In pretrial release, for which Compass is designed, there is, similarly, a gap from predictions to interventions that needs to be considered more broadly. Predicting that someone won't make it to their court date doesn't necessarily mean that jailing them between now and then is the correct intervention. 86 Alexandra Choldachova explains. If you think about it from that perspective, then you're saying, okay, this particular population, maybe they're less able to provide for themselves. They actually maybe have lower risk, but higher needs. Maybe they need daycare for their children on their court date, or a ride to court, not detention. As it turns out, simply reminding people about their court date can significantly improve their rate of appearance. 87 Unfortunately, many risk assessment tools, unlike Compass, conflate a prediction of failure to appear with a prediction of Criminal reoffense. Point 88. This is an enormous problem if the solution to one risk is incarceration, while the solution to another is a text message. This is a point that particularly resonates with Tim Brennan. The COMPAS information sheet about a defendant that gets shown to a judge was designed so that the risk assessment was in red, but the needs assessment was in green. In green, he says, you know, because these are the things that you want to cultivate and help the guy. 89. The whole point was to steer as many defendants away from incarceration as possible, toward treatment, community supervision, and the like. The AS in COMPAS stands for alternative sanctions, after all. But some judges simply view the needs scores, addiction issues, homelessness, lack of close community, not as a roadmap for rehabilitation, but as all the more reason for to lock someone up. Point 90. Of course, the ability to assign someone to such alternative sanctions, or to treatment programs, classes, counseling, and the like requires such services to actually exist. If they don't, then there is a problem that no statistical model, and indeed no judge, can solve. So this brings me to my main point. Moritz Hart tells me. Point 91. A machine learning model, trained by data, is by definition a tool to predict the future, given that it looks like the past. That's why it's fundamentally the wrong tool for a lot of domains, where you're trying to design interventions and mechanisms to change the world. 92. He elaborates, reducing crime and incarceration rates is a really, really hard problem that I would like to leave to experts in criminal justice. I feel like prediction offers a bit of a dystopian perspective on the topic, which is let's assume that we're not going to structurally reduce crime. We're going to predict where it's going to happen and go and try to catch people before it's happening. It doesn't really offer, to me, a mechanism to structurally reduce crime. And that's what I find dystopian about it. I don't want to know how to predict where crime's going to happen. I guess that's useful, but much rather I would have a mechanism to reduce crime structurally. I, as a computer scientist, have nothing to offer on that topic, absolutely nothing. I can't tell you the first thing about this. It would take me years to get to a point where I could. The importance of stepping back to take a wider, more macroscopic view of the criminal justice system was not lost on the earliest pioneers in the field. Ernest Burgess, writing in 1937, after his initial report on the parole system had prompted a risk assessment model that went into practice statewide, felt that it was high time to move on to something more comprehensive. The time has arrived in Illinois, in my judgment, he wrote, to stop tinkering with parole as an isolated part of our penal problem. What is required is a major operation which involves a complete reorganization of the prison system of the state. 93. 80-some years have passed since then. It's still true. 3. Transparency. The rules are supposed to be clear, uniformly expressed, and accessible to all. As we all know, this is rarely actually the case. David Graeber. 1. Providing overwhelming amounts of information without adequate structure or documentation is not transparency. Richard Burke. 2. In the mid-1990s, Microsoft's Rich Caruana was a graduate student at Carnegie Mellon working on neural networks, when his advisor, Tom Mitchell, approached him for help with something. Mitchell was working on an ambitious, interdisciplinary, multi-institutional project, bringing together biostatisticians, computer scientists, philosophers, and doctors, to better understand pneumonia. When a patient is first diagnosed, the hospital needs to make one critical decision fairly early on, which is whether to treat them as an inpatient or an outpatient. That is, whether to keep them in the hospital overnight for monitoring or to send them home. Pneumonia was at the time the 6th leading cause of death in the United States, with about 10% of pneumonia patients ultimately dying, and so correctly identifying which patients were at greatest risk would translate fairly straightforwardly into lives saved. The group had been given a dataset of about 15,000 pneumonia patients, and was tasked with building a machine learning model to predict patient survival rates that could help the hospital triage new patients. The result was a head-to-head competition of sorts among a menagerie of different machine learning models: logistic regression, a rule learning model, a Bayesian classifier, a decision tree, a nearest neighbor classifier, a neural network, you name it. 3. Caruana worked on the neural network in the 90s. The state of the art was wide networks, rather than deep, and it was not without some pride that he digested the results. His neural network had won, handily. It was the best of all the complex models, and outperformed more traditional statistical methods like logistic regression by a significant margin. 4. As the group would write in their reports, even small improvements in predictive performance for prevalent and costly diseases, such as pneumonia, are likely to result in significant improvements in the quality and efficiency of healthcare delivery. Therefore, seeking models with the highest possible level of predictive performance is important. 5. So naturally the Pittsburgh hospitals that were partnering on the study decided to deploy the highest performing model. Right? We started talking about that, whether it was safe to use a neural net on patients, says Caruana. 6. And I said, hell no, we will not use this neural net on patients. They deployed one of the simpler models that his neural net had so handily beaten. Here's why. The wrong rules. One of the other researchers on the project, Richard Ambrosino, had been training a much different, rule-based model on the same dataset. Rule-based models are among the most easily interpreted machine learning systems. They typically take the form of a list of if X then Y rules. You simply read your way down the list, from top to bottom, and as soon as a rule applies, you're done. Imagine a flowchart that doesn't branch and simply looks like a single vine running from top to bottom. Does this rule apply? If so, here's the answer and you're done. If not, keep reading. In this way, rule-based models resemble conditionals, or switch statements, in traditional software programming. They also sound a lot like the way humans think and write. More complex models use sets, rather than lists, in which multiple rules can be applied at once. 7. Ambrosino was building a rule-based model using the pneumonia data. One night, as he was training the model, he noticed it had learned a rule that seemed very strange. The rule was, if the patient has a history of asthma, then they are low risk and you should treat them as an outpatient. Ambrosino didn't know what to make of it. He showed it to Caruana. As Caruana recounts, he's like, Rich, what do you think this means? It doesn't make any sense. You don't have to be a doctor to question whether asthma is good for you if you've got pneumonia. The pair attended the next group meeting, where a number of doctors were present. Maybe the MDS had an insight that had eluded the computer scientists. They said, it's probably a real pattern in the data. They said, we consider asthma such a serious risk factor for pneumonia patients that we not only put them right in the hospital, we probably put them right in the ICU and critical care. The correlation that the rule-based system had learned, in other words, was real. Asthmatics really were, on average, less likely to die from pneumonia than the general population. But this was precisely because of the elevated level of care they received. So the very care that the asthmatics are receiving that is making them low risk is what the model would deny from those patients, Caruana explains. I think you can see the problem here. A model that was recommending outpatient status for asthmatics wasn't just wrong. It was life-threateningly dangerous. Point 8. What Caruana immediately understood, looking at the bizarre logic that the rule-based system had found, was that his neural network must have captured the same logic, too. It just wasn't as obvious. Amending or editing the rule-based system was fairly straightforward. The neural network was harder to correct in this way, though not impossible. I don't know where it is in the neural net, but one way or another I can solve the problem, Caruana recounts. I can publish more papers in the process of doing it, so this is good, and will make that problem go away. I said, the reason why we're not going to deploy the neural net is not actually because of asthma, because I already know about that. I said, what I'm worried about is things that the neural net has learned that are just as risky as asthma, but the rule-based system didn't learn. Because the neural net is more powerful, more flexible, it was capable of learning things that the rule-based system didn't. This, after all, is the advantage of neural networks, and the reason Caruana's neural net had won the group's internal contest. I said it's those things that will make us not use this model. Because we don't know what's in it that we would need to fix. So it's this transparency problem with the neural net that ultimately caused me to say we're not going to use it. This has bothered me for a long, long time. Because the most accurate machine learning models are often not transparent like this. And I'm a machine learning person. So I want to use accurate models, but I also want to use them safely. It's often observed in the field that the most powerful models are on the whole the least intelligible, and the most intelligible are among the least accurate. This really pissed me off, by the way, he tells me. I want to do machine learning for healthcare. Neural nets are really good, they're accurate, but they're completely opaque and unintelligible, and I think that's dangerous now. It's like, maybe I shouldn't be doing machine learning for healthcare. 9 instead, though, Caruana decided to spend the next 20 years developing models that attempt to have the best of both worlds, models that are, ideally, as powerful as neural networks, but as transparent and legible as a list of rules. One of his favorites is an architecture called generalized additive models, first pioneered by statisticians Trevor Hasty and Robert Tibshirani in 1986.10. A generalized additive model is a collection of graphs, each of which represents the influence of a single variable. For instance, one graph might show risk as a function of age, another would show risk as a function of blood pressure, a third would show risk as a function of temperature or heart rate, and so forth. These graphs can be linear, or curved, or incredibly complex, but all of that complexity can be immediately apprehended visually, simply by looking at the graph. These individual one-variable risks are then simply added up to produce the final prognosis. In this way it is more complex by far than, say, a linear regression, but also much more interpretable than a neural net. You can visualize, on a plain old two-dimensional graph, every factor going into the model. Any strange patterns should immediately stand out. Many years after the original pneumonia study, Caruana revisited the dataset and built a generalized additive model to explore it. The generalized additive model turns out to be just as accurate as his old neural net, and far more transparent. He plotted the pneumonia mortality risk, for example, as a function of age. It was mostly what one would expect. It's good to be young or middle-aged if you have pneumonia, and more dangerous to be older. But something in particular stood out, an abrupt, sharp jump. Beginning at age 65. It seemed unusual that a particular birthday would trigger a sudden increase in risk. What was going on? Caruana realized that the model had managed to learn the impact of retirement. It's really annoying that it's dangerous, right? You would hope that the risk goes down when you retire. Sadly, it goes up. 11 more importantly, however, the closer he looked, the greater the number of troubling connections he saw. He had feared that his old neural network had learned not just the problematic asthma correlation, but others like it, though the simple rule-based models at the time weren't powerful enough to show him what else might be lurking in the neural network. Now, 20 years later, he had powerful interpretable models. It was like having a stronger microscope and suddenly seeing the mites in your pillow, the bacteria on your skin. I looked at it, and I was just like, oh my, I can't believe it. It thinks chest pain is good for you. It thinks heart disease is good for you. It thinks being over 100 is good for you. It thinks all these things are good for you that are just obviously not good for you. 12. None of them made any more medical sense than asthma. The correlations were just as real, but again it was precisely the fact that these patients were prioritized for more intensive care that made them as likely to survive as they were. Thank God, he says, we didn't ship the neural net. Today Caruana says he finds himself in a different position than most researchers. He continues to work on developing model architectures that promise neural network levels of predictive accuracy while remaining easily understood. But instead of evangelizing any particular solution of his own invention, for instance, an updated version of Generalized Additive Models 13, he is evangelizing the problem itself. Everyone is committing these mistakes, he says, just like I have committed them for decades, and didn't know I was doing it. My goal right now, he tells me, is to scare people. To terrify them. I feel I've succeeded if they've stopped and they've thought, oh shit. We really got a problem here. The problem of the black box. Nature conceals her secrets, because she is sublime, not because she is a trickster. Albert Einstein. The act of giving a reason is the antithesis of authority. When the voice of authority fails, the voice of reason emerges. Or vice versa. Frederick Schauer 14. Rich Caruana is far from the only one who in recent years has had some version of the thought, oh shit. We really got a problem here. As machine learning models proliferate throughout the decision-making infrastructure of the world, many are finding themselves uncomfortable with how little they know about what's actually going on inside those models. Caruana found himself particularly uncomfortable with the use of large neural networks because of their long-standing reputation as black boxes. With the breathtaking rise in neural networks in everything from industry to the military to medicine, a growing number are feeling that same unease. In 2014, United States Defense Advanced Research Projects Agency, DARPA, program manager Dave Gunning was talking to Dan Kaufman, director of DARPA's Information Innovation Office. "We were just trying to kick around different ideas on what to do in AI," Gunning tells me. Point 15, they had a whole effort where they had sent a whole group of data scientists to Afghanistan to analyze data, try to find patterns that would be useful to the warfighters. And they were already beginning to see that these machine learning techniques were learning interesting patterns, but the users often didn't get an explanation for why. A rapidly evolving set of tools was able to take in financial records, movement records, cell phone logs, and more to determine whether some group of people might be planning to strike. And they might get some pattern that would be suspicious, says Gunning, but now they'd want an explanation of why. There was no such explanation on offer. Around that same time, Gunning attended a meeting sponsored by the intelligence community at the Lab for Analytical Sciences at North Carolina State University. The workshop brought together machine learning researchers and data visualization experts. "We had a government intel analyst in the room listening to us talk about what all the machine learning technology could do," Gunning remembers. And this one analyst just was really kind of adamant that her problem was she already has these big data algorithms giving her recommendations, but she has to put her name on the recommendation that goes forward. And she gets scored, if you will, or worse, based on whether that recommendation is correct. But she didn't understand the rationale for the recommendation she was getting from the learning algorithm. Should she sign her name to it, or not? And on what basis, exactly, should she decide? As computing technology progresses, the defense community has found itself increasingly thinking about what an automated battlefield might look like, what risks and questions surround the idea of ever more autonomous weapons. But many of those questions and problems remain, for the moment, anyway, theoretical. With the intel analysis problem, those systems are already there, people are using them, says Gunning. You know what I mean. This problem is already there. And they want help. Over the next 2 years, Gunning would find himself the program manager of a multi-year DARPA program in an attempt to meet that problem head-on. He would call it XAI, Explainable Artificial Intelligence. Across the Atlantic Ocean, the European Union was getting ready to pass an omnibus law called the General Data Protection Regulation, or GDPR. The GDPR would go into effect in 2018, and would sharply change how companies collect, store, share, and use data online. The regulations, all 260 pages worth, amounted to one of the most important documents in the history of data privacy. They also included something a bit more curious and intriguing, and perhaps just as profound. At the Oxford Internet Institute in the fall of 2015, Bryce Goodman was leafing through the draft legislation when something caught his attention. "I'd learned a bit about machine learning, and how some of the best methods don't really lend themselves to being transparent or interpretable," he says, "and then I came across this. In the earlier drafts of the GDPR, it was much more explicit. They said people should have the right to ask for an explanation of algorithmically made decisions. 16, I find it really interesting," he says, "when there are these pieces of legislation, or these things that somebody just sort of puts a stake in the ground and says, this thing exists now." Goodman approached his Oxford colleague Seth Flaxman, who had just finished a PhD in machine learning and public policy. "Hey, I read this thing in the GDPR," Goodman said. "This seems like it would be a problem." He was like, "Yeah, that seems like it would be." Whether it was getting rejected for a loan, being turned down for a credit card, being detained pending trial, or denied parole if a machine learning system was behind it, you had a right to know not just what happened but why. The following spring, in 2016, the GDPR was officially adopted by the European Parliament, and the collective hair went up on the back of the necks of executives across the entire tech sector. Attorneys described sitting down with EU regulators. "You realize," they said, "that getting intelligible explanations out of a deep neural network is an unsolved scientific problem, right?" As Goodman and Flaxman had written, it could require a complete overhaul of standard and widely used algorithmic techniques. The regulator was not moved by this. "That's why you have until 2018. As one researcher put it, they decided to give us 2 years' notice on a massive research problem. The GDPR has now gone into effect, though the exact details of what EU regulators expect, and what constitutes a sufficient explanation, to whom, and in what context, are still being worked out." Meanwhile, transparency, the ability to understand what's going on inside a machine learning model and why it behaves as it does, has emerged as one of the field's most clear and crucial priorities. Work on this problem continues, full steam, to this day, but recent progress has been made on a number of fronts. Here is what we are coming to know. Clinical versus statistical prediction. There is a prevalent myth that the expert judge of men succeeds by some mystery of divination. Of course, this is nonsense. He succeeds because he makes smaller errors in the facts or in the way he weights them. Sufficient insight and investigation should enable us to secure all the advantages of the impressionistic judgment, except its speed and convenience, without any of its defects. Edward Thorndike, 17. The first thing we need to consider as we confront the problem of transparency, particularly in large, complex models, is whether, in fact, we ought to be using large or complex models in the first place. For that matter, should we be using models at all? These are questions that reach deeply into the history of statistics. Gorilla label from image classifier, Google fixed advantages of the impressionistic judgment, except its speed and convenience, without any of its defects. Explanations out of a deep neural network is an unsolved scientific problem, right? As Goodman and Flaxman had written, it could require a complete overhaul of standard and widely used algorithmic techniques. The regulator was not moved by this. That's why you have until 2018. As one researcher put it, they decided to give us 2 years' notice on a massive research problem. Down with EU regulators. You realize, they said, that getting intelligible explanation, clinical versus statistical. Prediction. Edward Thorndike 7. The first thing we need to consider as we confront the problem of transparency, particularly in large, complex models, is whether, in fact, down with EU regulators. You realize, they said, that getting intelligible explanations out of a deep neural network is an unsolved scientific problem, right? Down with EU regulators. Regulators. You realize, they said, that getting intelligible explanations out of a deep neural network is an unsolved scientific problem, right? As Goodman and Flaxman had written, it could require a complete overhaul of standard and widely used algorithmic techniques. The regulator was not moved by this. That's why you have until 2018. As one researcher put it, they decided to give us 2 years' notice on a massive research problem. The GDPR has now gone into effect, though the exact details of what EU regulators expect, and what constitutes a sufficient explanation, to whom, and in what context, are still being worked out. Meanwhile, transparency, the ability to understand what's going on inside a machine learning model and why it behaves as it does, has emerged as one of the field's most clear and crucial priorities. Work on this problem continues, full steam, to this day, but recent progress has been made on a number of fronts. Here is what we are coming to know. Clinical versus statistical. Prediction. There is a prevalent myth that the expert judge of men succeeds by some mystery of divination. Of course, this is nonsense. He succeeds because he makes smaller errors in the facts or in the way he weights them. Sufficient insight and investigation should enable us to secure all the advantages of the impressionistic judgment, except its speed and convenience, without any of its defects. Edward Thorndike 17. The first thing we need to consider as we confront the problem of transparency, particularly in large, complex models, is whether, in fact, we ought to be using large or complex models in the first place. For that matter, should we be using models at all? These are questions that reach deeply into the history of statistics and machine learning, ones that are as relevant today as they have ever been, and ones whose answers are rather surprising indeed. In 1954, Robin Dawes was an undergraduate philosophy major at Harvard, specializing in ethics. His thesis, A Look at Analysis, investigated whether, and to what degree, moral judgments were rooted in emotion. Not only did Dawes think these were important questions, he thought empirical work might be important. But how would you do empirical work? With this question, he realized that his interests lay more with psychology than philosophy. He applied to psychology graduate programs, and the best one in the country, the University of Michigan, let him in off the waiting list on the final day of the admissions window. Dumbstruck, Dawes broke the good news to his advisor, who told him, wire them back immediately before they realize they made a clerical error. 18. Dawes went to Michigan and began his training in clinical psychology. At the time, the late 1950s and early 60s, this meant a heavy emphasis on Rorschach tests. Dawes found himself growing skeptical of just how useful the Rorschach was as a clinical tool. It was all intuitive, and it made intuitive sense. But then I started reading and found out that in fact, empirically, a lot of this stuff doesn't work. During his dawning skepticism, Dawes was working as a resident in a psychiatric ward. There was a client who had this delusion, he recounts, and the delusion was that he was growing breasts. And he was in my group, on a locked ward by the way, because he had this delusion that must be schizophrenia. Anna, why did he think he was growing breasts? Well, earlier that week, one of his parents had committed suicide before he developed the delusion. Okay, makes perfect sense, right? They'd never asked this guy to take off his shirt even. He'd just been sent to the psychiatric ward, 6 weeks on a locked ward in my group. And when they asked him to take off his shirt, it was in fact true, he was growing breasts. The man had Klinefelter syndrome, a genetic condition caused by an additional X chromosome, with symptoms including lack of body hair and the development of breast tissue. Dawes was incensed. Okay, well that's 6 weeks of his life just thrown out, he says, because people were so convinced about, oh, this is a fascinating delusion. This led to a major pivot in Dawes' career, away from clinical practice, and toward what was at the time being called mathematical psychology. He had a paper he was intending to submit for publication, comparing expert clinical judgments against simple mathematical models, and he showed the paper to a friend. The friend's reaction caught Dawes off guard. He sort of looked at me funny and said, you know, in effect, are you sure you didn't plagiarize? As it happened, Dawes was joining an academic lineage of which he had no idea. The question of pitting expert judgment against simple mathematical models, then called actuarial methods, went back to the early 1940s work of a colleague of Ernest Burgess's, named Ted Sabin. Sabin looked at predictions of academic performance for incoming freshmen at the University of Minnesota. The actuarial model was a simple linear regression to predict their college GPA from just 2 data points, their high school class rank and their college aptitude test scores. The human predictions were made by experienced clinical psychologists who had access to these 2 data points, plus additional tests, an 8-page dossier, notes from a colleague's interview, and their own first-hand impression of the student. Sabin found no measurable difference between the 2 predictions. If anything, the actuarial model was more accurate, though not markedly so. From Sabin's perspective, it seemed incredible that the additional information available to the clinicians appeared to add nothing in predictive accuracy. What of strivings, habits of work and play, special aptitudes, emotional patterns, systematic distractions, and the hundreds of other conditions, he wrote, which seemed to be related to this complex form of social psychological behavior known as academic achievement, 19. Ironically, Sabin found that the human counselors didn't place much emphasis on these things themselves and, in fact, made their predictions chiefly on the basis of class rank and test scores, the very same data used in the regression model. They just weren't as consistent or finely tuned in how they weighted it. Sabin's conclusion was that the time-intensive effort spent in conducting interviews was a waste. And he cautioned, unless checked by statistical studies, the case study method in the social sciences will become intellectually bankrupt. Sabin's findings had caught the attention, in turn, of a young psychologist named Paul Meehl. Inspired by Sabin's provocation, and unsure of where he himself stood, Meehl began an investigation that would turn into an entire book on the subject, 1954's Clinical versus Statistical Prediction. Though much if not most of the book was dedicated to understanding what goes into clinical judgments and how clinicians make decisions, by far its biggest impact stemmed from the chapter, in which Meehl pitted clinical and actuarial judgments head-to-head. The human experts, Meehl discovered, didn't stand a chance. Out of almost 100 different domains, in only a half dozen did there seem to be even a slight edge for the human decision-makers. I am told, Meehl recounts, that half the clinical faculty at one large Freudian-oriented Midwest university were plunged into a 6-month reactive depression as a result of my little book, 20 Doors. Having found himself to be an unwitting plagiarist, of course became keenly interested in Meehl's work, but his advisors seemed to disapprove of the influence. I was told by my psychoanalytic mentors that, well, Meehl is a genius, and everyone knows he's a genius, but what he does has nothing to do with what we do. And I started worrying about, if what he does has nothing to do with what we do, maybe I don't want to do what we do. By the mid-1970s, Dawes, by then at the Oregon Research Institute, authored another concussive paper in the lineage. As he summarized, Sabin and Meehl had opened the question of how purely statistical analysis might compare to expert human judgment. The statistical analysis was thought to provide a floor to which the judgment of the experienced clinician could be compared, Dawes wrote. The floor turned out to be a ceiling. 30 years after Sabin's original paper, and many dozens of studies later, he concluded, a search of the literature fails to reveal any studies in which clinical judgment has been shown to be superior to statistical prediction when both are based on the same codable input variables. Emphasis mine. Point 22. The picture was humbling indeed. Even in cases where the human decision-makers were given the statistical prediction as yet another piece of data on which to make their decisions were still worse than just using the prediction itself. Point 23. Other researchers tried the reverse tack, feeding the expert human judgments into a statistical model as input. They didn't appear to add much. Point 24. Conclusions like these, which have been supported by numerous studies since, should give us pause. Point 25. For one, they seem to suggest that, whatever myriad issues we face in turning decision-making over to statistical models, human judgment alone is not a viable alternative. At the same time, perhaps complex, elaborate models really aren't necessary to match or exceed this human baseline. A tantalizing question lurks, however, namely, what explains this surprising verdict? Is human judgment really that bad? Are simple linear models of a handful of variables really that good? Or, a third possibility, has human expertise somehow managed to enter into the simple models where we least expect it? Were we looking for it in the wrong place? Improper models, knowing what to look at. The fact that some real problems are hard does not imply that all real problems are hard. Robert Holt, 26. The fact that man cannot combine information as efficiently as a computer, for example, does not imply that man can be replaced by machines. It does imply that the necessity for a man-computer system is at hand. Hillel J. Einhorn, 27. Dawes, with his colleagues at the Oregon Research Institute, wanted to get to the bottom of the shocking effectiveness of simple, linear models in decision-making. One hypothesis was that perhaps the models were outperforming the experts because of a kind of wisdom of the crowd effect, that a single model was aggregating the judgments of a whole group of experts. So of course it would outperform any single expert in isolation. It sounded plausible, but it wasn't true. Amazingly, even if a model was trained only to mimic a single expert's judgments, it still outperformed the expert themselves. 28. Maybe there was something about the way that the linear models were optimized, the way they were tuned to have the optimal coefficients that weighted each variable. With his collaborator Bernard Corrigan, Dawes compared the judges against what they called improper, linear models, ones whose weights were not optimized. They tried equal weights, and they tried random weights. The results were stunning. Models with random weights, as long as they were constrained to be positive, were as accurate, or more than the judges themselves. Models with equal weights were even better. 29. The practical possibilities for such quick and easy improper models seemed endless. In the mid-1970s, Dawes was on a panel with a medical physician. Afterward, sharing drinks at the bar, the doctor asked him, could you, for example, use one of your improper linear models to predict how well my wife and I get along together? 30. Dawes immediately imagined the simplest model he could think of. A good marriage, he figured, should probably involve more sex than fights. With a colleague's dataset, he did the math. He added up the number of times a couple had sex, defined as genital union with or without orgasm, over a period of weeks or months, and subtracted the number of times they had a fight, situations where at least one party became uncooperative in that same time. The linear prediction is the quintessence of simplicity. Subtract the rate of arguments from the rate of sexual intercourse. A positive difference predicts happiness, a negative one unhappiness. 31. The data, from couples in the Kansas City, Missouri, area, showed that indeed, sex minus fights was positive for 28 out of the 30 couples that self-identified as happy, while sex minus fights was negative for all 12 couples that self-identified as unhappy. 32 study after study, in Oregon, in Missouri, in Texas, confirmed this correlation. In fact, in many cases the equal-weighted models were better even than the optimal regressions, a fact that seems impossible, as the optimal weights are chosen precisely to be, well, optimal. But they were optimal for a particular context and a particular set of training data, and that context didn't always transfer. Optimal weights for predicting academic performance at the University of Minnesota, for instance, weren't necessarily optimal for predicting academic performance at Carnegie Mellon. In practice, equal weights seem to hold up better and be more robust across contexts. Point 33 Dawes was fascinated by this. Given the complexity of the world, why on earth should such dead simple models, a simple tally of equally weighted attributes, not only work, but work better than both human experts and optimal regressions alike? He came up with several answers. First, despite the enormous complexity of the real world, many high-level relationships are what is known as conditionally monotone. They don't interact with one another in particularly complex ways. Regardless of whatever else might be happening with a person's health, it's almost always better if that person is, say, in their late 20s rather than their late 30s. Regardless of whatever else might be happening with a person's intellect, motivation, and work ethic, it's almost always better if that person's standardized test scores are 10 points higher than 10 points lower. Regardless of whatever else might be happening with a person's criminal history, self-control, and so forth, it's almost always better if they have one fewer arrest on their record than one more. Second, there is almost always error in any measurement. For theoretical as well as intuitive reasons, the more error-prone a measurement is, the more appropriate it is to use that measurement in a linear fashion. Perhaps most provocatively from the perspective of alignment, Dawes argued that these equally weighted models surpass their proper, optimally weighted counterparts, because those weights have to be tuned, as we've seen, with respect to some kind of objective function. In real life, often we either can't define how exactly we plan to measure success, or we don't have time to wait for this ground truth to come so we can tune our model. For example, he writes, when deciding which students to admit to graduate school, we would like to predict some future long-term variable that might be termed professional self-actualization. We have some idea what we mean by this concept, but no good, precise definition as yet. Even if we had one, it would be impossible to conduct the study using records from current students, because that variable could not be assessed until at least 20 years after the students had completed their doctoral work. Even here, Dawes argues, when we don't know what exactly we want and have no data at all, improper models should serve us at least as well if not better than raw intuition. Point 34 One might, however, object that Dawes and Corrigan's comparisons, particularly against human experts, don't seem entirely fair. The models were not random linear combinations of random properties, they were random linear combinations of precisely the things that humans have established, through decades if not generations of best practices, to be the most relevant and predictive things to consider. It would be tempting to argue, perhaps, that all of this pre-processing activity, deciding which 2 or 5 or 10 things out of the infinite information available is most pertinent to the decision at hand, reflects the real wisdom and insight into the problem, in effect, that we've done all of the hard work already before passing it off to the linear model, which then gets all the credit. This, indeed, was exactly Dawes' point. As he wrote, the linear model cannot replace the expert in deciding such things as what to look for, but it is precisely this knowledge of what to look for in reaching the decision that is the special expertise people have. 35 It was Dawes' conclusion that human expertise is characterized by knowing what to look for, and not by knowing the best way to integrate that information. One of the clearest demonstrations of this idea came from a study by decision theorist Hillel Einhorn in 1972.36. Einhorn looked at physicians' judgments of biopsy slides for patients diagnosed with Hodgkin's lymphoma. The physicians were asked to specify the factors they considered important when looking at a slide, and then to score each slide for those factors. The physicians then gave an overall rating about the severity of the patient. It so happened that their overall severity ratings had zero correlation with patient survival. However, in a result that is becoming something of a refrain, a simple model using the expert's individual factor scores was a powerful predictor for patient mortality. Put differently, we've been looking for human wisdom in the wrong place. Perhaps it is not in the mind of the human decider, but embodied in the standards and practices that determined exactly which pieces of information to put on their desk. The rest is just math, or, at any rate, should be. Dawes put it a third way, in arguably the most famous sentence of his storied career. The whole trick is to know what variables to look at, he wrote, and then to know how to add. 37. Optimal simplicity. Simple can be harder than complex. You have to work hard to get your thinking clean to make it simple. But it's worth it in the end, because once you get there, you can move mountains. Steve Jobs 38. The only simplicity for which I would give a straw is that which is on the other side of the complex, not that which never has divined it. Oliver Wendell Holmes Jr. 39. Perhaps no one so carries the spirit of Dawes forward into the 21st century, like Duke University computer scientist Cynthia Rudin. Rudin has made simplicity one of the central drives of her research. She is interested in not only arguing against the use of overly complex models, but in pushing the envelope of what simple models can do. In the criminal justice domain, for instance, Rudin and her colleagues published a paper in 2018 showing that they could make a recidivism prediction model as accurate as compass that could fit into a single sentence. If the person has more than 3 prior offenses, or is an 18 to 20-year-old male, or is 21 to 23 years old and has 2 or more priors, predict they will be rearrested. Otherwise, not. 40 for Rudin. Dawes' research is both an inspiration and a kind of challenge, like a gauntlet being thrown down. So simple models, made from hand-selected high-level variables, perform about as well as more complex models, sometimes better, and consistently as well as or better than human experts. But even that leaves a lot of questions, and avenues for research open. How, for instance, might one build not just a simple model from a given dataset, but the best simple model? Surprisingly, answers have come only in the last several years. Rudin looks at the simple models currently being used in 21st century healthcare, and takes a different and much less sanguine view than Dawes. Instead of seeing present-day models as a superior alternative to clinical intuition, she sees models overly shaped by clinical intuition, and ones with a lot of room for improvement. She raises the example of the coronary heart disease score sheet for men. So if you're a guy, you go into the doctor's office, and they will try to compute your 10-year risk of coronary heart disease. And they'll do it by asking you 5 questions. What's your age? What's your cholesterol level? Do you smoke? And so on and so forth. So they ask you these 5 questions, and then you get points for each answer you give, and then you add up the points, and that translates into your 10-year risk of coronary heart disease. Her voice takes a sharp turn. But where do they get these 5 questions? And how did they get the points? And the answer is, they made it up. This was made up by a team of doctors. This is not how I want to do this. What I want to do is, I want to build something that's that interpretable, but I want to build it from data. 41. As it happens, finding optimal simple rules is not for the faint of heart. In fact, it requires tackling an intractable, or NP-hard, problem, a thicket of complexity, in which there is no straightforward means of obtaining the guaranteed best answer. Given tens of thousands of patient records, each with dozens or perhaps hundreds of different attributes, age, blood pressure, etc., how do you find the best simple flowchart for diagnosis? Computer scientists have a toolkit full of ways to make progress here, but Rudin felt that the existing algorithms for building simple rule lists and scoring systems from big data, algorithms like CART, developed in the 80s-42 and C4.5, developed in the 90s-43, just weren't sufficient. There was also something available to computer scientists in the 2010s that wasn't available in the 80s and 90s, about a million-fold speed up in computing power. Instead of using that computational horsepower to train a huge, complex model, like AlexNet, with tens of millions of parameters, why not put it to use, instead, searching the vast space of all possible simple models? What might be possible? Her team went back to the drawing board and came up with new approaches, one for rule-based models and another for models based on score sheets, and set about comparing these against the status quo. In particular, Rudin and her lab set their sights on beating one of the most commonly used models in all of medicine, CHADS-2. CHADS-2, developed in 2001, and its successor, CHA-2DS2-VASC, developed in 2010, are designed to predict the risk of stroke in patients with atrial fibrillation. 44 each was designed by doctors and researchers working closely with a dataset, along with their clinical expertise, to identify what they thought the most relevant factors were. And subsequent studies have confirmed the predictive utility of the tools. Both models, despite being generally accepted as valid instruments and having found incredibly widespread use, remain to a degree artisanal, handcrafted. Rudin wanted to computationally identify the most relevant factors to combine together into a single scoring instrument. Working with more than 6,000 times as much data as was used in the original CHADS-2 study, Rudin let her algorithm, called Bayesian rule lists, loose on a set of 12,000 patients, to pore over some 4,100 different properties for each, every drug they were taking, every health condition they had reported, to make the best possible scoring system. 45 She then compared her own model to both CHADS-2 and CHA-2DS2-VASC against held out portions of that same dataset. The results showed a marked improvement over both CHADS-2 and CHA-2DS2-VASC. More intriguingly, they also showed a marked decrease in accuracy from the original CHADS-2 to the more recent CHA-2DS2-VASC. The newer model appeared, at least by this measure, on this data, to be worse than the old one. This, as she and her colleagues put it delicately in their paper, highlights the difficulty in constructing these interpretable models manually. In a subsequent project, Rudin and her PhD student Burke Uston worked with Massachusetts General Hospital to develop a scoring system for sleep apnea, a condition that affects tens of millions of Americans, and more than 100 million people worldwide. 46 Their goal was to create a model that was not only as accurate as possible, but also so simple that it could run quickly and reliably on some decidedly old-school hardware, physicians' notepads. Because of the constraint that the model would be deployed on paper, Uston and Rudin had to make their model almost impossibly simple. It would need very few explicit features to consider, and integer coefficients as small as possible. 47 Even into the 21st century, it was not uncommon for practitioners to simply come up with an ad hoc model based on their own intuition. This is sometimes derisively referred to as the Boxat method, a bunch of guys sitting around a table. Even in cases where machine learning was used in building the model, it was often more complex models that were simplified manually after the fact. 48 It is still true today that models in current medical practice were designed in this ad hoc fashion, meaning that accuracy, and therefore, real patients, are suffering. 49 Uston and Rudin wanted to see if there was a better way. They developed a model called SLIM, supersparse linear integer model, to find not just decent heuristics, but provably optimal ways to make decisions under these severe constraints. The upshot of their work was twofold, with concrete benefits in medicine and machine learning alike. First, the model showed, contrary to received wisdom and current practice, that patient symptoms were significantly less useful than their histories. When Uston and Rudin trained a model on patients' medical histories, things like past heart attacks, hypertension, and the like, it was significantly more predictive than one trained on their immediate symptoms, things like snoring, gasping, and poor sleep. What's more, adding symptoms to the model based on histories didn't register much of an improvement. The screening of sleep apnea, which in severe untreated form triples one's risk of death 50, had taken a measurable step forward. Second, the machine learning community had scored a methodological victory it could carry through into other collaborations and other domains. SLIM accuracy was similar to state-of-the-art classification models applied to this dataset, Uston and Rudin's team report, but with the benefit of full transparency, allowing for hands-on prediction using yes or no answers to a small number of clinical queries. 51 As Rudin puts it, I want to design predictive models with the end user in mind. I want to design these things, not just so they're accurate, but so that people can use them, people can make decisions using them. I want to create predictive models that are highly accurate, yet highly interpretable, that we can use for trustworthy decision-making. And I'm working under The hypothesis that I believe is true, that many datasets permit predictive models that are also surprisingly small. I'm not the first person to hypothesize this, it was hypothesized many years ago. But now we have the computational ability, and new ideas, and new techniques, that will really allow us to test this hypothesis. It's an exciting time for researchers working on this set of questions. Simple models are amazingly competitive, and then some, with human expertise. Modern techniques give us ways of deriving ideal simple models. With that said, there are cases where complexity is simply unavoidable. The obvious one is models that don't have the benefit of human experts filtering their inputs to meaningful quantities of manageable size. Some models must, for better or worse, deal not with human abstractions like GRE score and number of prior offenses, but with raw linguistic, audio, or visual data. Some medical diagnostic tools can be fed human inputs, like mild fever and asthmatic, while others might be shown an X-ray or CAT scan directly and must make some sense of it. A self-driving car, of course, must deal with a stream of radar, lidar, and visual data directly. In such cases we have little choice, but the kinds of large, multimillion parameter, black box, neural networks that have such a reputation for inscrutability. But we are not without resources here as well, on the science of transparency's other, wilder frontier. Saliency, the whites of its eyes. Humans, relative to most other species, have distinctly large and visible sclera, the whites of our eyes, and as a result we are uniquely exposed in how we direct our attention, or at the very least, our gaze. Evolutionary biologists have argued, via the cooperative eye hypothesis, that this must be a feature, not a bug, that it must point to the fact that cooperation has been uncommonly important in our survival as a species, to the point that the benefits of shared attention outweigh the loss of a certain degree of privacy or discretion. Point 52. It might be understandable, then, for us to want to expect something similar from our machines, to know not only what they think they see but where, in particular, they are looking. This idea in machine learning goes by the name of saliency. The idea is that if a system is looking at an image and assigning it to some category, then presumably some parts of the image were more important or more influential than others in making that determination. If we could see a kind of heat map that highlighted these critical portions of the image, we might obtain some crucial diagnostic information that we could use as a kind of sanity check to make sure the system is behaving the way we think it should be. Point 53. The practice of such saliency methods has been full of surprises that highlight just how unintuitive machine learning systems can be. Often they latch onto aspects of the training data we did not think were relevant at all, and ignore what we would imagine was the critical information. In 2013, Portland State University PhD student Will Landecker was working with a neural network trained to distinguish images in which an animal was present from those with no animals present. He was developing methods for looking at which portions of the image were relevant to the ultimate classification, and noticed something bizarre. In many cases, the network was paying more attention to the background of the picture than the foreground. A closer look showed that blurry backgrounds, known in photographers' lingo as bokeh, were commonly present in images of an animal, with the face in sharp focus and the background artfully out of focus. Empty landscapes, by contrast, tended to be more uniformly in focus. As it turns out, he hadn't trained an animal detector at all. He'd trained a bokeh detector. 54. In 2015 and 2016, dermatologists Justin Ko and Roberto Novoa led a collaboration between researchers from Stanford's medical and engineering schools. Novoa had been struck by the progress in computer vision systems' ability to differentiate between hundreds of different dog breeds. I thought, he says, if we can do this for dogs, we can do this for skin cancer. 55. They put together the largest dataset ever assembled of benign and malignant skin patterns, 130,000 images spanning 2,000 different diseases as well as healthy skin. They took an off-the-shelf open-source vision system, Google's Inception v3, which had been trained on the ImageNet dataset and categories, and they retrained the network to tell the difference, not between Chihuahuas and Labradors, but between acral lentiginous melanoma and amylonotic melanoma, and thousands of other conditions. They tested their system against a group of 25 dermatologists. The system outperformed the humans. This, dermatologist-level accuracy landed them a widely cited paper in Nature in 2017.56 for Ko, who prides himself on the keenness of his own diagnostic eye, honed over the better part of a decade of training and clinical practice. The result was both deeply humbling and inspiring. I've been spending years and years and years, says Ko, and this thing can do it in a few weeks. 57, and yet what such a system promised was the ability to essentially extend high-quality, low-cost diagnostic abilities to the furthest reaches of the globe. As it turns out, a system like this is useful not only in places where first-rate diagnosticians are hard to find, but also as a second opinion for trained experts like Ko himself. Ko remembers the date, April 17, 2017, when a patient came into his clinic with a funny-looking spot on their shoulder. I was completely on the fence, Ko says. Something about it, he said, just seemed not quite right. But then when I looked at it with my dermatoscope, I didn't see any features that would suggest to me that this was an early evolving melanoma. Still, it didn't sit right with him. And so I said, okay, this is a perfect time to whip out my iPhone. Ko took a series of photos, with every kind of angle and lighting he could, and fed each of them into the network. Remarkably, he says, regardless of the photo, it was pretty stable in the read, and it was pretty adamant that this was a malignant lesion. Ko had it biopsied and talked to the clinic's dermatopathologist. Lo and behold, she said, hey, you know what? This is really fascinating. This was a really early, subtle example of an evolving melanoma. So we caught it at a completely treatable stage. The date sticks in Ko's mind. It was the first time the network had made a clinical impact. And, he says, I hope it's just the first of many. The full story, though, is a bit more complicated. Ko, Novoa, and their collaborators submitted a letter the following year to the Journal of Investigative Dermatology, urging caution in moving neural network models too quickly into routine clinical practice. They felt that extreme care was due before such models are deployed widely into the field, and underscored their point with a cautionary tale. From their own experience, the vision system they were using was much more likely to classify any image with a ruler in it as cancerous. Why? It just so happened that medical images of malignancies are much more likely to contain a ruler for scale than images of healthy skin. Thus the algorithm inadvertently learned that rulers are malignant. 58 saliency-based methods can catch some of these issues. Still, the ultimate solution, whether ensuring that the dataset contains diverse enough variation, or that all input images are standardized in some way, is complex. We must continue addressing the many nuances involved, they conclude, in bringing these new technologies safely to the bedside. Tell me everything, multitask. Nets. One of the simplest ideas in making complex models more transparent and understandable is simply to have them output more things. When Rich Caruana was working on neural networks to predict medical outcomes, he realized that the network could be used to make not just a single prediction, say, whether the patient would live or die, but potentially dozens, how long they'd stay in the hospital, how large their bill would be, whether they'd need breathing assistance, how many courses of antibiotics they'd require, and so on. All of this additional information in a dataset was useless in practice as additional inputs to the model. Learning to predict a patient's risk of death based on their hospital bill won't actually help you when a new patient arrives, because of course you don't know their final bill yet. But rather than serving as additional inputs, this information is useful as additional outputs, additional sources of ground truth in training the model. The technique has come to be known as multitask learning. 59, strangely enough, that can be easier than training it to predict one of those things at a time. Caruana tells me 60 together. You can think of training it on 100 related things at the same time as providing you more signal. More information. As an example, he invites me to imagine that I'm admitted to the hospital with some serious condition, perhaps pneumonia. Suppose I live, he says, but I'm in the hospital for a month, and my bill is $500,000. I now know something was terribly wrong, says Caruana. The shit hit the fan for you. Maybe it didn't qualify as one of our dire outcome things. But I now know that you were very, very sick. To a system built narrowly to predict mortality risk, my case might serve as training data with a ground truth mortality risk of 0, seeing as I survived, but something would be missing. My case was, as he puts it, a pretty high risk 0. If I indeed had simply been lucky, maybe the system ought to predict, say, an 80% chance of death, not a 0% chance, in future cases like mine. Giving it a wider range of outputs to train on, and simultaneous predictions to make, might nudge the system toward that more accurate assessment. What Caruana came to realize was that not only were these multitask models better in the traditional senses, they trained faster, achieved higher accuracy, but they were also more transparent, in a way that made it easier to identify problems. If a healthcare system like the one he built in the 90s were generating predictions only for whether a patient would live or die, you might find it predicting unexpected things, like, for instance, that asthmatics are less likely to die than regular outpatients. On the other hand, if you had a multitask net predicting all sorts of things from the data, not just death, but length of hospital stay or dollar cost of treatment, these anomalies would be much more visible. The asthmatics, for instance, might have better than average morbidity, but astronomical medical bills. It would be much clearer that these were no ordinary, low-risk patients to be sent home with instructions to take 2 pills and call back in the morning. In some cases, these additional output channels can also offer something more significant. A team spanning Google, its life science spin-off Verily, and the Stanford School of Medicine was working in 2017 and 2018 on similarly adapting Google's Inception V3 network to classify images of the retina. 61 They found encouraging diagnostic results, with the model detecting diseases like diabetic retinopathy as accurately as human experts. The team realized, however, that the dataset they were working with had all sorts of other information about the patient, age, sex, body mass index, whether they smoked, and so on. So we sort of added those variables to the model, says Google researcher Ryan Poplin. 62, just as Caruana had done, they thought that since they had all this additional patient data, why not have their model predict all of it? What if they treated this trove of ancillary data, age, sex, blood pressure, etc., not as additional inputs to the model, but as additional outputs? It might offer a way to make the model more robust, and might offer some insight into cases where the model's disease predictions were off. We felt like it was a great sort of control, or ground truth, that we could add to the model, says Poplin. They were in for an enormous shock. The network could almost perfectly tell a patient's age and sex from nothing but an image of their retina. The doctors on the team didn't believe the results were genuine. You show that to someone, says Poplin, and they say to you, you must have a bug in your model. Cause there's no way you can predict that with such high accuracy. As we dug more and more into it, we discovered that this wasn't a bug in the model. It was actually a real prediction. The team used saliency methods to reveal, if not exactly how the network was doing it, then at least what the relevant features were. Age, as it happened, was determined by the model looking mostly at the blood vessels, sex, in contrast, by looking at the macula and the optic disc. At first, says Poplin, when showing these results to a doctor, they kind of laugh at you. They don't believe it. But then, when you show them that heat map and show that it's focusing on the optic disc or maybe features around the optic disc, then they say, oh yeah, of course we knew that, of course you can see that. By showing where in the image the model is using to make its prediction, it really does provide a level of trust and also, you know, a level of validity to the results. More than achieving mere predictive accuracy, the model suggested an intriguing path forward for medical science itself. The combination of multitask learning and saliency techniques showed the field that there were sex differences in the retina that had been overlooked. Not only that, it showed where to find them. These methods of explanation, in other words, don't just make for better medicine. They might also make for better doctors. Popping the hood, feature. Visualization. We've seen how multitask networks, with additional outputs, can give us important context for what a network is predicting. Saliency methods offer context for the network's input, and can offer us information about, in effect, where a model is looking. But neither tells us much about what's going on inside the black box, that is, what the model is actually seeing. The signature breakthrough in machine learning since AlexNet in 2012 have been neural network models that learn from the messy welter of raw sensory perception, millions of colored pixels. The models have tens of millions, not dozens, of parameters, and those parameters represent fairly ineffable things, some thresholds of earlier layers, which are themselves some thresholds of earlier layers, all the way back to the millions of raw pixels. This is not the raw grist from which intelligible explanations are made. So what to do? At NYU, PhD student Matthew Zeiler and his advisor, Rob Fergus, were fixated on this question. The success of these enormous, bewildering models, they argue, is undeniable. However, they write, there is no clear understanding of why they perform so well, or how they might be improved. From a scientific standpoint, this is deeply unsatisfactory. 63 in other words, the results are impressive, but as Zeiler puts it, with all these nice results, it's not clear what these models are learning. 64 people knew that the bottommost layer of a convolutional network represented basic things, vertical edges, horizontal edges, diagonal edges, a strong single color, or a simple gradient. And it was known that the final output of these networks was a category label, cat, dog, car, and so forth. But it wasn't really known how to interpret the layers in between. Zeiler and Fergus developed a visualization technique they called deconvolution, which was a way to turn intermediate level activations of the network back into images. 65 For the first time, they were seeing the second layer. It was a menagerie of shapes. Parallel lines, curves, circles, T-junctions, gradient patterns, colorful blobs. A huge variety of structure is present already at the second layer. The third layer was even more complex, beginning to represent portions of objects, things that looked like parts of faces, eyeballs, textures, repeated patterns. It was already detecting things like the white fluff of a cloud, the multicolor stripes of a bookshelf, or the green comb of grass. By the fourth layer, the network was responding to configurations of eyes and nose, to tile floors, to the radial geometry of a starfish, or a spider, to the petals of a flower or keys on a typewriter. By the fifth layer, the ultimate categories into which objects were being assigned seemed to exert a strong influence. The effect was dramatic, insightful. But was it useful? Zeiler popped the hood of the AlexNet model that had won the ImageNet competition in 2012. And started digging around, inspecting it using deconvolution. He noticed a bunch of flaws. Some low-level parts of the network had normalized incorrectly, like an overexposed photograph. Other filters had gone dead and weren't detecting anything. Zeiler hypothesized that they weren't correctly sized for the types of patterns they were trying to match. As astoundingly successful as AlexNet had been, it was carrying some dead weight. It could be improved, and the visualization showed where. In the fall of 2013, within a matter of frantic months, Zeiler finished his PhD, left NYU, started his own company, Clarify, and entered that year's ImageNet competition. He won. 66 other groups, subsequently and in parallel, have explored further ways of directly visualizing a neural network. In 2015, Google engineers Alexander Mordvintsev, Christopher Olah, and Mike Tyker experimented with a method of starting from an image of random static, and then tweaking its pixels to maximize the probability that the network assigns it a particular label, say, banana, or fork. 67 This deceptively simple method has proven to be remarkably powerful. It results in fascinating, memorable, often psychedelic, and occasionally grotesque images. Start optimizing static for dog, for instance, and you're likely to get some unholy amalgam of dozens of eyes and ears, growing fractally, one on another, at a variety of different scales. It's fertile ground for artistic mischief, and almost a novel visual aesthetic unto itself. The Google engineers had a further idea. Rather than starting from static and manually specifying a category label, they would start from a real image, clouds, say, or leaves, and simply adjust the image to amplify whatever neurons in the network already happen to be most active. As they write, this creates a feedback loop. If a cloud looks a little bit like a bird, the network will make it look more like a bird. This in turn will make the network recognize the bird even more strongly on the next pass and so forth, until a highly detailed bird appears, seemingly out of nowhere. They dubbed this rather hallucinatory method Deep Dream. 68 other, more bizarre possibilities exist as well. When Yahoo's Vision team open-sourced a model used to detect whether an uploaded image was pornographic, UC Davis PhD student Gabriel Go used this generative method to tune static into shapes the network regarded as maximally not safe for work. The result was like pornography by Salvador Dali. If you optimize for some combination of the obscenity filter and normal ImageNet category labels, for instance, volcanoes, you get, in this case, obscene geography, what look like giant granite phalluses, ejaculating clouds of volcanic ash. Such images are, for better or worse, not easily forgotten. 69. On a more philosophical note, such techniques suggest that, at least as far as neural networks are concerned, the line between critic and artist can be a thin one. A network trained to recognize, say, lakes or cathedrals can be made, in this way, to endlessly churn out images of lake after lake after lake, or cathedral after cathedral after cathedral, that it has never seen before. It's a beautiful, if painstaking, prescription for artistic practice. Anyone who can tell good art from bad can be a creator. All you need is good taste, random variations, and plenty of time. Techniques like these not only open up a vast space of aesthetic possibility, but have important diagnostic uses as well. For example, Mordvintsev, Olah, and Tyker used their start from static technique to have an image classification system generate images that would maximally resemble all of its different categories. In some cases, they write, this reveals that the neural net isn't quite looking for the thing we thought it was. For example, pictures that maximized the dumbbell categorization included surreal, flesh-colored, disembodied arms. There are dumbbells in there all right, they write, but it seems no picture of a dumbbell is complete without a muscular weightlifter there to lift them. In this case, the network failed to completely distill the essence of a dumbbell. Maybe it's never been shown a dumbbell without an arm holding it. Visualization can help us correct these kinds of training mishaps. 70 This is also a useful technique for exploring issues of bias and representation. If starting from random static and fine-tuning hundreds of images to maximize the face category produces a set of faces that are, say, exclusively white and male, then that's a pretty good indication that the network won't recognize other types of faces as readily. Since the initial Deep Dream research, Tyker has gone on to co-found the Artists and Machine Intelligence program at Google and continues to explore the aesthetic possibilities of machine learning. Meanwhile, Olah and Mordvintsev, along with their collaborators, have continued to explore the scientific and diagnostic frontier of visualization. Point 71 Today Ola leads the Clarity team at OpenAI. I've always been kind of fascinated by explaining things, he tells me. My goal, which I think some people think is kind of crazy, is just to completely reverse engineer neural networks. 72 This work has pushed the boundaries not only of science, but of publishing. Ola found that traditional scientific journals just weren't suited for the kinds of rich, interactive, full-color, and high-resolution visualizations he was making. So he launched a new 1.73 overall. The group expresses a measured, but contagious optimism about the work underway. We have a lot of work left ahead of us to build powerful and trustworthy interfaces for interpretability, they write. But if we succeed, interpretability promises to be a powerful tool in enabling meaningful human oversight and in building fair, safe, and aligned AI systems. 74 Much progress continues to be made in the visual domain especially. But what about understanding a network like this not at a visual level, but a conceptual one? Might there be a way to make sense of the interior of the network through words, for instance? This is one of explanation's latest frontiers. Deep networks and human concepts. In the fall of 2012, MIT graduate student Bing Kim had found herself, at the beginning of her PhD, homing in on the project that would shape the next years of her life. She had previously been working in robotics, including going so far as getting a forklift driver's license in order to better understand the industrial robotics environment, but decided in the end that it wasn't the right fit. I realized that robotics had a hardware limitation, she tells me. My thoughts go faster than what physical stuff can do. 75 Increasingly Kim believed that interpretability might, well, become her dissertation topic, if not her life's work. Her first time at the new IPS conference, that December, she found herself talking with an older colleague. I was telling a faculty member that I work on interpretability, and he was like, oh, why? Neural networks will solve everything. Why do you care? And I was like, well. She chuckles at the recollection. Imagine if you walk into a doctor's office and he says, oh, I'm going to open you up and remove maybe a couple of things. And you ask, oh. Why? He says, oh, I don't know. This machine says that that's the best option for you. 99.9%. What would you ask, she says. Her question is both rhetorical and more than rhetorical. What would you say to the doctor? It was so abundantly obvious to me that this is an area we need to solve. What I wasn't sure is how soon the time will come that people realize this is important. Late afternoon sunlight filters through the glass of the conference room at Google Brain, where Kim has worked since 2017. I think that time has come. Kim's belief is that there is a dimension to explanation and interpretation that is inherently human, and so there is an inherent messiness, an inherent interdisciplinarity to the field. A large portion of this, still underexplored, is thinking about the human side, she says. I always emphasize HCI, human-computer interaction, cognitive science. Without that, we can't solve this problem. Recognizing the ineluctably human aspect of interpretability means that things don't always translate neatly into the familiar language of computer science. Some folks think that you have to put down a mathematical definition of what explanation must be. I don't think that's a realizable direction, she says. Something that is not quantifiable makes computer scientists uncomfortable, inherently very uncomfortable. Almost all of Kim's research papers contain something fairly unusual in computer science, but typical outside of it, namely, actual studies using human subjects. Iterating with the users is critical, she says. Because if your sole reasoning for existence is for human consumption, we have to show that it is good for human consumption. This iteration is critical, because often what designers think is useful to actual human users simply isn't. If you're designing explanations or interpretable models to be used by real people, then the process should be every bit as iterative as designing, say, cockpit controls or a software user interface. Point 76 Not to let that kind of empirical feedback guide the process is simply hubris. Such studies add some complexity to the story we explored earlier, which celebrated the use of simple models. Kim notes that it's ultimately an empirical question whether this is the best approach to interpretability. In some cases, in very limited cases, where you can sufficiently identify and empirically validate that if I have a small number of features, that it's interpretable for this particular task, in that case, yes, you can write down what it means to be most interpretable, given a problem, and you can optimize it. But real human studies, Kim's and others, show that things are rarely so straightforward in practice. For instance, in 2017, Microsoft researchers Jen Wortman-Vaughan and her colleagues studied the way that human users interacted with a machine learning model of home values, which predicted price from features like square footage, bathrooms, and so on. Users were better at anticipating the model's predictions when it used fewer factors and was made more transparent to the user. But neither the simplicity nor the transparency actually affected the level of trust that people reported toward the model. And in fact, people were less likely to realize that the model had made a mistake when the model was more transparent. Point 77. One of Kim's beliefs is that humans think and communicate using concepts, not numbers. Point 78 We communicate, and for the most part, think verbally, leveraging high-level concepts. We don't talk about the raw minutiae of sensory experience. For this reason, Kim thinks that many saliency-based methods don't go far enough. She and her collaborators have been working on something they call testing with concept activation vectors, or TCAV, which offers a way to use such human concepts to understand the internal workings of the network. For instance, imagine a model correctly identifying a picture of a zebra. Suppose TCAV shows that the network used stripes, horse, and savanna in its prediction. That seems reasonable. On the other hand, a network trained somewhat naively on a set of images of doctors might, if the dataset were biased, assume that the concept of male had some predictive value. TCAV would show this, and would offer an indication that we may want to adjust the model, or the training data accordingly, to remove such a bias. Point 79. How exactly might we get this kind of insight? Every image generates from our model not only an ultimate category label output, but a vast pattern of internal activity in the network, across however many tens of millions of its artificial neurons. These internal activations may seem like an overwhelming cacophony to human eyes, but that doesn't mean that you can't show them to a machine. The basic idea behind TCAV is that for any concept you're interested in, say, males, in the doctor case, you present the network with a bunch of images of males, and then a bunch of images of random other things, women, animals, plants, cars, furniture, and so on. You feed the internal state of your network, say, at a particular layer, to a second system, a simple linear model that learns to tell the difference between the activations typical of your category, males in this case, and the activations from random images. Point A to you can then look to see whether this activation pattern is present, and to what degree it contributes, when the network categorizes an image as a doctor. I think this method offers a unique benefit, she says, which is that explanation now speaks your user's language. Your users don't have to come and learn machine learning. We can provide an explanation in the language that they speak, and answer the hypothesis that they have, using their own terms. 81. When Kim used TCAV to look at two popular image recognition models, Inception v3 and GoogleNet, she found a number of such issues. The concept of red, for instance, was critically important to the concept of fire truck. So that makes sense, she says, if you're from an area where fire engines are red. 82. It's almost always true in the United States, for instance, but not in Australia, where, depending on the district, fire trucks can sometimes be white, or in Canberra, neon yellow. This would suggest, say, that a self-driving car model developed on a US-centric dataset might need modification before it was safe to deploy down under. Kim also found that the concept of arms was important to identifying dumbbells, corroborating the earlier visual findings of the Deep Dream group from Google, and hinting that the network might struggle to identify a dumbbell on a rack or on the ground. 83. The concept East Asian was important to ping pong ball, and the concept Caucasian was important to rugby. Some of these may reflect patterns that, while not inaccurate, according to the International Table Tennis Foundation, 7 of the top 10 male players, and all 10 of the top 10 female players in the world are from East Asian countries. 84. May nonetheless still signal aspects of the model that deserve scrutiny, from the perspective of both accuracy and bias. We wouldn't be happy, on either front, with a system that, as Facebook AI researchers Pierre Stock and Mustafa Cisse discovered, categorized a portrait of Chinese President Xi Jinping as a ping pong ball. 85. TCAV offers a way to explicitly quantify such issues, and ideally to nip them in the bud. Kim's work on TCAV was featured by Google CEO Sundar Pichai during his keynote address at Google's 2019 I/O conference. It's not enough to know if a model works, said Pichai. We need to know how it works. In 2012, it had felt to Kim like there was hardly an audience for these concerns, and that only she, along with Cynthia Rudin and Julie Shah, her mentors at MIT, were even vaguely interested in this topic. By 2017, there were entire symposia at the field's largest conferences devoted to interpretability and explanation. By 2019, the CEO of Google was proudly describing her work on the company's biggest stage. I asked Kim if that feels like vindication. We have such a long way to go, she says, seemingly unwilling to allow herself a moment's satisfaction, or a feeling of I told you so. Instead, she feels mostly responsibility to make sure that these issues are addressed faster than the already rapid progress and deployment of the technology itself. She has to somehow get out ahead of that wave, in order to make sure there aren't any high-stakes problems. As we wrap up our conversation and start to walk out of the conference room, I thank Kim for her time and ask her if there's anything else she wants to add that we haven't already touched on. She pauses thoughtfully for about 10 seconds, then suddenly lights up. By the way, this faculty that I was talking about, the one who, in 2012, scoffed at her when she, as a first-year PhD student, mentioned that her PhD work was on interpretability, and tried to steer her away from what he saw as a dead end. She bears no grudge, though. I think genuinely, he was giving me advice. It's a really reasonable, sweet thing. Kim grins. That person is now working on interpretability. Part 2. Agency. 4. Reinforcement. The role of reinforcement in human affairs has received steadily increasing attention, not through any changing fashion, in learning theory, but as the result of the discovery of facts and practices, which have increased our power to predict and control behavior and in doing so have left no doubt of their reality and importance. The scope of reinforcement is still not fully grasped, even by those who have done most to demonstrate it, and elsewhere among psychologists cultural inertia is evident. This is understandable, because the change has been little short of revolutionary. Scarcely anything in traditional learning theory is left in recognizable form. B. F. Skinner 1. The trouble with modern theories of behaviorism is not that they are wrong, but that they could become true. Hannah Arendt 2. Gertrude Stein, in the spring of 1896, enrolled in a psychology seminar at Harvard with the great William James. There she would study motor automatism, or the ability to write words on paper without thinking deliberately about them. The peer-reviewed article that resulted would be her very first appearance in print. More significantly, what began as undergraduate psychology research would lead her directly to the trademark modernist stream of consciousness, prose style for which she would be famous. 3 Stein described her classmates in James's seminar as a funny bunch, and one in particular was a bit of a character. He was preoccupied with incubating chickens. 4 The student was Edward Thorndike, and, to be fair, turning his apartment into a makeshift chicken coop wasn't his first idea. He wanted to study the mechanisms of learning in human children, and to debunk the idea of extrasensory perception while he was at it. Harvard didn't approve the project. So the incubator full of chirping chicks, just sort of, happened as a fallback plan. 5 For an aspiring psychologist to be tending to a flock of chicks was indeed strange at the time. Animal research had yet to come into its 20th century vogue, and Thorndike's own classmates thought he was a bit odd. It may have raised the eyebrows of his peers, and the hackles of his landlady, but tending his flock was, despite being a logistical nightmare, not without its perks. When traveling in Massachusetts, for instance, Thorndike was often forced to stop at the house of some family friends, the Moultons, to warm the chicks on their stove before continuing on to Cambridge. This may have been a research necessity, though it becomes clear from his letters that Thorndike was motivated in no small part by the chance to flirt with their younger daughter, Bess. She later became his wife. Thorndike's landlady in Cambridge finally declared his incubator a fire hazard, and gave him an ultimatum: the chicks had to go. James attempted to secure him a laboratory space on the Harvard campus, but the university wasn't any more enthusiastic. As a last resort, James, over the protestations of his wife, let Thorndyke move the chicks, incubator and all, into the basement of his own home. James's children, at least, appear to have been delighted. In 1897, Thorndyke graduates from Harvard and moves to New York City for a fellowship at Columbia, this time working with all manner of animals. The year is frequently bleak. 2 of his cats run away, he can't get any dogs, and my monkey is so wild I can't touch him. To make matters worse, not all of the animals in Thorndyke's urban menagerie are therefore science, a number are simply pests. In a letter to Bess on February 14, 1898, he writes, "A mouse just ran across my foot. A lot of rats are gnawing the bureau, 3 chicks are sleeping within a yard of me, the floor of my room is all over tobacco, and cigarette ends, and newspapers, and books and coal, and a chicken pen, and the cat's milk dish and old shoes, and a kerosene can and a broom which seems rather out of place. It's a desolate hole, this flat of mine." Still, he promises he'll clean it, and, his writing on Valentine's Day, after all, he invites her to pay him a visit. Out of that squalor will come some of the most original and consequential research of the 19th century. Thorndyke has built a set of contraptions he calls puzzle boxes, full of latches and levers and buttons. He'll drop an animal inside the box, place some food outside, and observe the way that the animals, chicks, cats, and dogs, manage to find their way out. You'd like to see the kittens open thumb latches and buttons on doors, and pull strings, and beg for food like dogs and other such stunts, Thorndyke writes to Bess, me in the meantime eating apples and smoking cigarettes. Thorndyke is interested in learning, and a theory is taking shape in his mind. What Thorndyke observes, while eating those apples and smoking those cigarettes, is that the animals, who have no idea how the box actually works, initially behave almost purely randomly, biting things, nudging things. Once one of these random actions gets them out of the box, they very quickly learn to repeat that action, and become more and more capable of quickly escaping that same box in the future. The one impulse, out of many accidental ones, which leads to pleasure, he observes, becomes strengthened and stamped in thereby. 6 Thorndyke sees here the makings of a bigger, more general law of nature. As he puts it, the results of our actions are either satisfying or annoying. When the result of an action is satisfying, we tend to do it more. When on the other hand the outcome is annoying, we'll do it less. The more clear the connection between action and outcome, the stronger the resulting change. Thorndyke calls this idea, perhaps the most famous and durable of his career, the law of effect. As he puts it, the law of effect is, when a modifiable connection between a situation and a response is made and is accompanied or followed by a satisfying state of affairs, that connection's strength is increased. When made and accompanied or followed by an annoying state of affairs, its strength is decreased. The strengthening effect of satisfyingness, or the weakening effect of annoyingness, upon a bond varies with the closeness of the connection between it and the bond. 7. From this seemingly modest and intuitive idea will be built much of 20th century psychology. 8 in 1927, Ivan Pavlov's conditioned reflexes appears in English, translated by his student Gleb von Anrep, who uses the term reinforcement to refer to this effect. By 1933, Thorndyke himself is using the term reinforcement, as is a young Harvard postdoc by the name of Burhus Frederick B. F. Skinner, whom we will meet more properly in Chapter 5.9. The language of reinforcement, along with the idea of using animals to understand the mechanisms of trial and error learning, and thereby the human mind, sets the frame in which much of psychology will operate for decades to come. As one of the leading psychologists in the next generation, Edward Tolman, will write, the psychology of animal learning, not to mention that of child learning, has been and still is primarily a matter of agreeing or disagreeing with Thorndyke. 10. If Thorndyke ultimately accepted his place in the canon of psychology, he was uncommonly modest about it. When Thorndyke's textbook The Elements of Psychology came out in 1905, it threatened to unseat the previous mainstream textbook, Psychology, Brief a Course, written by none other than his own Harvard mentor, William James. Thorndyke mailed him a check for $100 to offset the lost royalties. James replied, seriously, Thorndyke, you're a freak of nature. When the first law of nature is to kill all one's rivals, especially in the schoolbook line, you feed them with the proceeds. James refused to cash the check, and sent it back. 11 The torch had, in a manner, been passed, and 20th century psychology was on its way. Digital trial and error. What sort of force acting through what sort of process, or mechanism, can be and do what the confirming reaction is and does? The answer, which seems to me to fit all or nearly all the facts, is the force and mechanism of reinforcement, applied to a connection. Edward Thorndyke. 12. If the animal researchers following Thorndyke were, like he was, ultimately interested in the psychology of the human child, they were not alone. Computer scientists, the very first ones, were too. Alan Turing's most famous paper, Computing Machinery and Intelligence, in 1950, explicitly framed the project of artificial intelligence in these terms. Instead of trying to produce a program to simulate the adult mind, he wrote, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. Turing imagined these ersatz child minds as what he called unorganized machines, beginning in a random configuration that would then be modified by the quality of the outcomes of their initially random actions. A roadmap to artificial intelligence, then, was already taking shape. The unorganized machines would borrow directly from what was known about the nervous system, and the course of education would borrow directly from what the behaviorists were discovering about how animals and children learned. Warren McCulloch and Walter Pitts had by the early 40s shown that a large assembly of artificial neurons, suitably wired, was capable of computing just about anything. Turing had begun to sketch out ways that such a network might be trained through trial and error. Indeed, this was precisely the process of stamping in that Thorndyke had described 50 years before, in his smoky apartment zoo. Turing's description resembles, nearly verbatim, Thorndyke's law of effect. When a configuration is reached for which the action is undetermined, a random choice for the missing data is made and the appropriate entry is made in the description, tentatively, and is applied. When a pain stimulus occurs, all tentative entries are cancelled, and when a pleasure stimulus occurs, they are all made permanent. 13. By the end of the 1950s, IBM's Arthur Samuel, working out of the company's Poughkeepsie laboratory, had built a program to play checkers that, in a crude and early way, adjusted its own parameters on the basis of won and lost games. It wasn't long before Samuel was losing matches to his own creation. As the New Yorker reported in 1959, Dr. Samuel has thus become probably the first scientist in history to concede defeat by an adversary of his own devising. 14 He published a report called Some Studies in Machine Learning Using the Game of Checkers, embracing the term machine learning to describe this methodology. Samuel wrote, "The studies reported here have been concerned with the programming of a digital computer to behave in a way which, if done by human beings or animals, would be described as involving the process of learning. We have at our command computers with adequate data handling ability and with sufficient computational speed to make use of machine learning techniques, but our knowledge of the basic principles of these techniques is still rudimentary. Lacking such knowledge, it is necessary to specify methods of problem solution in minute and exact detail, a time-consuming and costly procedure. Programming computers to learn from experience should eventually eliminate the need for much of this detailed programming effort." Point 15. In plainer English, he explained, "It's one of the most satisfying things that have ever happened to me. As far as I know, nobody else has ever got a digital computer to improve of its own accord. You see, the kind of mental activity that computers can simulate has always been severely limited, because we've had to tell them exactly what to do and exactly how to do it. Continuing to develop machines that could learn, in other words, by human instruction, or their own experience, would alleviate the need for programming. Moreover, it would enable computers to do things we didn't know how to program them to do." The unveiling of Samuel's research became the stuff of computer science legend. Fellow AI pioneer John McCarthy recounts that when Samuel was getting ready to demonstrate his checkers program on national television, Thomas J. Watson Sr., the founder and president of IBM, remarked that the demonstration would raise the price of IBM stock 15 points. It did. 16. The hedonistic neuron. The struggle of the nerve cells, each for its own life, parallels the struggle of our wants for satisfaction. Edward Thorndike, 17. In 1972, Harry Klopf, a researcher working for the United States Air Force out of Wright-Patterson Air Force Base in Dayton, Ohio, published a provocative report titled Brain Function and Adaptive Systems, a heterostatic theory. Klopf argued that the neuron is a hedonist, one that works to maximize some approximate, local notion of pleasure and minimize some notion of pain. The whole complexity of human and animal behavior, Klopf believed, arises as a result of these individual cellular, hedonists, wired up into systems of increasing complexity. The generation before Klopf, the so-called cybernetics movement of the 40s through the 60s, had framed intelligent behavior specifically in terms of what they called negative feedback. Organisms were motivated, they argued, largely by homeostasis or equilibrium. They strove to maintain a comfortable temperature. They ate to quell their hunger. They mated to quell their desire. They slept to quell their fatigue. Everything seemed to be about getting back to baseline. Indeed, the seminal 1943 cybernetics paper, Behavior, Purpose and Teleology, which, incidentally, coined the term feedback, in its now common sense of information used for adjustment, set out to distinguish purposeful from purposeless, or random, behavior. 18 For the cyberneticists, purpose was tantamount to a goal that could be arrived at as a place of rest. For arch-cyberneticist Norbert Wiener, one of the canonical, intrinsically purposeful machines is a thermostat. When the temperature is too low, it turns on the heat, and when the temperature gets high enough, it shuts it off. He thought also of the governor of an engine. More than coincidentally, the term is an etymological kin to the word, cybernetics, itself, coming from the same Greek root kybernetes. 19 Thus cybernetics, for all its exotic sci-fi flavor, could well have been the much blander and more bureaucratic-sounding field of governetics. A mechanical governor opens valves when the engine is running too fast, and closes them when it's running too slow, helping it to maintain equilibrium. Notice that the feedback tends to oppose what the system is already doing, and is thus negative. Wiener writes, point 20 This was an essential part of any goal-oriented system, in the cybernetic view. All purposeful behavior, the cyberneticists wrote, may be considered to require negative feedback. 21 Klopf was having none of it. For him, organisms were maximizers, not minimizers. Life was about growth, reproduction, endless and boundless and insatiable forward progress in any number of senses. For Klopf, the goal was not homeostasis at all, but the opposite. Living adaptive systems seek, as their primary goal, a maximal condition, heterostasis, rather than a steady-state condition, homeostasis. More poetically, he espoused the virtues of positive, rather than negative feedback. Both positive and negative feedback are essential to life's processes. However, it is positive feedback that is the dominant force. It provides the spark of life. This notion ran all the way through from single cells to organisms to societies. Klopf was not modest about what he saw as the implications of this idea. It appears to be the first theory capable of providing a single unifying framework within which the neurophysiological, psychological, and sociological properties of living adaptive systems can be understood, he wrote. Neurons, nervous systems, and nations are heterostats. 22. Neurons were insatiable maximizers. And this explained the behavior of nations. It was an ambitious, unorthodox, and quite possibly absurd idea. The Air Force offered him funding to find or assemble a lab of researchers to look into it. He found his team at UMass Amherst. There he hired a postdoctoral researcher named Andrew Bartow to determine, as Bartow puts it, the scientific significance of this idea. Was it a crazy, crackpot idea? Or did it have some scientific merit? 23 Klopf had, perhaps unusually, been keeping a running correspondence during this time with a bright undergraduate psychology major from Stanford. When Bartow came on board, Klopf encouraged him. There's this really bright kid. You should get him into this project. 24 The bright kid was named Richard Sutton. Still a teenager, he would join Bartow in Amherst and become Bartow's very first graduate student. I asked Bartow if there was any foreshadowing of what was to come. We had no idea, he tells me. We had no idea. Sutton and Bartow would, with Klopf's Air Force grant, begin a 4 to 5 year collaboration that would essentially found a new field. The field, which would cross neuroscience, behaviorist psychology, engineering, and mathematics, was dubbed reinforcement learning, and their names, forever linked in bibliographies of AI, Bartow and Sutton. Sutton and Bartow would become synonymous with the definitive textbook of the field they co-authored, and indeed, almost a shorthand for the field of reinforcement learning itself. Point 25. I meet up with Bartow on the University of Massachusetts campus, where he's now emeritus. Happily retired, he says. Frankly, glad to be out of the maelstrom of hype and excitement about AI and reinforcement. I tell him I'm excited to talk about the history of reinforcement learning as a field, RL, as it is often called, and in particular its implications for safety, for decision-making, for human cognition. He interrupts me. So, how much time have you got? Most of the day, I tell him. That's what we take. The reward hypothesis. Bartow and Sutton took Harry Klopp's idea of organisms as maximizers and gave it a concrete, mathematical form. Imagine you are in an environment that contains rewards of some numerical value, which are available to you if you take certain actions and reach certain states. Your job is to get the most reward, the highest score that you can. The environment could be a maze, your actions could be moving north, south, east, or west, and your reward could come from reaching the exit, perhaps, minus a small time penalty. Or the environment could be a chessboard, your actions the moving of the pieces, and your reward 1 point for checkmating your opponent, and half a point for reaching a draw. Or perhaps the environment is the stock market, your actions are buying and selling, and your reward is measured in the dollar value of your portfolio. There is virtually no limit to the complexity of these scenarios. The environment could be a national economy, the actions could be issuing words of legislation or diplomacy, and the reward could be long-term GDP growth. As long as the rewards are what is known as scalar, they are commensurate, fungible, of a common currency. The reinforcement learning framework has proven to be so general, in fact, that it has led to an idea known as the reward hypothesis, that all of what we mean by goals and purposes can be well thought of as the maximization of the cumulative sum of the received scalar reward. 26. This is almost a philosophical thing, says Richard Sutton. But you kind of buy into this. 27. Of course, not everyone buys into this premise so readily. In sports, in board games and video games, in finance, there may indeed be such a scalar number, a single currency, literal or figurative, for measuring all outcomes, but can that really be applied to something as complex and multiform as human, or even animal, life? We often have to make decisions whose outcomes seem like apples and oranges. Do we work late, improving our standing with our boss, but testing the patience of our spouse? Do we prioritize a life of achievement, a life of adventure, a life of human connection, or a life of spiritual growth? Oxford University philosopher Ruth Chang, for instance, has spent decades arguing that nothing so characterizes the human condition as the incommensurability of the various motives and goals we have. We can't simply put major life choices on a scale and weigh out which one comes out best, or else there would be nothing to morality, but pure reason, no opportunity to make meaning, to forge an identity. 28. Sutton himself concedes that the reward hypothesis is probably ultimately wrong, but so simple we have to disprove it before considering anything more complicated. Even if we accept, provisionally, the framework of reward maximization and the commensurability of scalar rewards, we find that being a heterostatic maximizer is harder than it sounds. Indeed, the problem of reinforcement learning is fraught with difficulty both philosophical and mathematical. The first challenge is that our decisions are connected. Here reinforcement learning is subtly, but importantly, different from both unsupervised learning, which builds the vector word representations we explored in Chapter 1, and supervised learning, which is used for everything from the ImageNet contest to face recognition to recidivism risk assessment. In those settings, every decision stands alone. Your system is shown a picture, say, a chanterelle mushroom, and asked to categorize it. The system may get the answer right, it may get it wrong, its parameters may be fine-tuned a little bit in the event of a mistake, but in any case you simply pull another photo at random from your collection and move on. The data coming in as input are what statisticians call IID, independent and identically distributed. There is no causal connection between what we see, what we do, and what we see next. In reinforcement learning, in a maze, in a chess game, indeed in life, we don't have the luxury of making our decisions in a vacuum. Every decision we make sets the context in which our next decision will be made, and in fact, it may change that context permanently. If we develop our chess pieces a certain way, we are strongly constraining the types of positions we will encounter and the types of strategies that may be useful going forward. In a spatial world, whether virtual or real, it is intrinsic to locomotion that the actions we take, move north in the maze, turn to face our lover, spend the winter in Florida, sculpt the future input we receive, either temporarily or forever. If we sacrifice our queen, it is unavailable to us for the rest of the game. If we jump off the roof, we may never jump again. If we are unkind to someone, we may forever alter how that person behaves toward us, and we may never know how they might have behaved had we been kinder. The second challenge of reinforcement learning, relative to supervised and unsupervised learning, is that the rewards or punishments we get from the environment, owing to their very scalar quality, are terse. A language model trained to predict a missing word is told, after each guess, what the correct word was. An image classifier attempting to classify an image is immediately given the correct label for that image. It then updates itself explicitly in the direction of that correct answer. In contrast, a reinforcement learning system, trying its best to maximize some quantity in some environment, eventually comes to learn what score it achieved, but it may never know, win or lose, what the correct, or best actions should have been. When a rocket blows up, or a bridge collapses, or a pile of plates you're trying to carry topples, or the ball you kick fails to go into the net, the world is crystal clear about the result. But it's mum on exactly what you should have done differently. As Andrew Bartow puts it, reinforcement learning is less like learning with a teacher than learning with a critic. 29. The critic may be every bit as wise, but is far less helpful. The teacher would look over your shoulder as you work, correcting your mistakes instantly, and telling you or showing you exactly what you should be doing instead. The critic waits until your labor is done, then shouts boo from the back of a dark auditorium, leaving you clueless as to what exactly they didn't like, or what they'd have preferred. The critic may not even be withholding anything by way of insight or constructive feedback. they may not themselves be left with anything other than their degree of, in Thorndike's terms, satisfaction or annoyance. Third, not only is feedback terse and not especially constructive, it's delayed. We may make an unrecoverable blunder on the fifth move of a game, for instance, in which the coup de grace comes 100 moves later. The idiom that comes most to mind when someone experiences a failure or defeat, the disappointed parent, bankrupt business owner, apprehended thief, is where did I go wrong? In reinforcement learning, this is known as the credit assignment problem and had been vexing researchers since the mid-century. MIT's Marvin Minsky, for instance, wrote in his famous 1961 paper, Steps Toward Artificial Intelligence, in playing a complex game such as chess or checkers, or in writing a computer program, one has a definite success criterion, the game is won or lost. But in the course of play, each ultimate success, or failure, is associated with a vast number of internal decisions. If the run is successful, how can we assign credit for the success among the multitude of decisions? Minsky elaborates, driving home the point. Suppose that 1 million decisions are involved in a complex task, such as winning a chess game. Could we assign to each decision 1/millionth of the credit for the completed task, 30 after a car accident, several days into a cross-country road trip, we don't retrace our actions, all the way back to turning the key in the ignition and think, well, that's the last time I ever turn left out of the driveway. Nor, though, do we imagine, having been checkmated on move 89 of a game of chess, our blunder must have happened on move 88. So how do we determine the right lessons to take away from success and failure both? The reinforcement learning framework began opening up a vista on the fundamental problem of learning and behavior that would develop into an entire field, and would direct the course of artificial intelligence research through our present decade. It would also, just as Harry Klopp envisioned, give us a new set of questions to ask of the natural intelligence that surrounds us. The riddle of dopamine. If humans and other animals can be thought of as heterostatic reward maximizers, it stands to reason that those rewards operate by way of some mechanism in the brain. If there really is some kind of singular, scalar, reward that humans and animals are designed to maximize, might it be as simple as a chemical or a circuit in the brain? In the 1950s, a pair of researchers at McGill University in Montreal, James Olds and Peter Milner, appeared, tantalizingly, to have found its location. Olds and Milner were experimenting with placing electrodes in various places in the brains of rats, and giving the rats an opportunity to press a lever that would deliver electrical current through those electrodes to that particular part of the brain. Some areas of the brain, they discovered, seemed to have no effect on the rats' behavior. In other areas, the rats would appear to go out of their way to make sure the lever did not get pressed. But there were some areas, the so-called septal area in particular, where rats appeared to want almost nothing more than to press the lever that delivered current to that area. The rats pressed the lever as many as 5,000 times an hour, and for as long as 24 hours, without rest. 31, the control exercised over the animal's behavior by means of this reward is extreme, Olds and Milner wrote, possibly exceeding that exercised by any other reward previously used in animal experimentation. 32 The foundation had been laid for a study, not only of human and animal behavior through the lens of reward maximization, but of the actual molecular mechanisms of reward itself. At first these areas were dubbed reinforcing structures, but soon Olds began referring to them as pleasure centers. 33 Subsequent research showed that not just rats, but humans, too, would go out of their way to receive electrical current in similar parts of their brain. In time, studies began to establish that the areas of the brain in which this electrical stimulation was most compelling were those areas involving neurons that produced a neurotransmitter called 3,4-dihydroxyphenethylamine, better known by its abbreviated nickname, dopamine. 34 These cells were rare, much less than 1% of the brain, and they clustered in very specific areas. 35 A single one of these dopamine cells could be wired in some cases to millions of other neurons across a wide area of the brain. 36 In fact, they were almost uniquely broadly connected, with the most highly connected cells each having nearly 15 feet of axonal wiring within the brain. 37 At the same time, however, they were fairly limited in the range and complexity of their output. As NYU neuroscientist Paul Glimcher puts it, this means that they cannot say much to the rest of the brain, but what they say must be widely heard. 38 It sounded a lot, in other words, like a reward scalar in essence, like points on the brain scoreboard, dead simple, but widely broadcast and all important. Dopamine also appeared to be intimately involved in drugs of addiction, including cocaine, heroin, and alcohol. Could it be that dopamine was literally the molecular currency of reward in the brain? Work in the late 1970s appeared to suggest as much. A study in 1978, for instance, showed that when rats were given the dopamine-blocking drug pimozide before being taught that pressing a lever would give them food pellets, they showed no more interest in pressing the lever than rats who had never learned the food connection at all. Somehow the food reward just didn't seem to have an effect on the rats treated with pimozide. Pimozide, wrote the researchers, appears to selectively blunt the rewarding impact of food and other hedonic stimuli. 39 As neuroscientist Roy Wise wrote in 1982, it was as if all of life's pleasures, the pleasures of primary reinforcement and the pleasures of their associated stimuli, lose the ability to arouse the animal. 40 In fact, when given drugs known to block dopamine receptors, the rats stopped delivering electrical current to their brains as well. The drug, in the words of neuroscientist George Fouriezos, took the jolts out of the vaults. 41 It was as if everything, from food and water to sex to self-administered current, had lost its pleasurable effect. Over the 1980s, electrophysiology began advancing to the point that individual dopamine neurons could be monitored in real time. The German neurophysiologist Wolfram Schultz, at a lab in Freiburg, Switzerland, began studying the behavior of dopamine neurons in monkeys, as they reached into a box that was sometimes empty and other times contained tiny pieces of fruit or baked goods. Sure enough, wham, a burst of impulses occurred when the monkey's hand touched a morsel of food inside the box. 42 This seemed to confirm that scientists had, in fact, found the chemical of reward. But there was something strange. In cases where there was a visual or auditory cue of some kind that indicated when food had appeared in the box, the cue triggered a rush of dopamine activity. Then the monkeys would reach in and grab their food, while Schultz dutifully monitored the readings, and nothing happened. Just the calm background static of their normal baseline of activity. No spike. The dopamine neurons, he wrote, discharged a burst of impulses in response to the cue, but entirely failed to respond to the touch of food. 43. What in the world was going on? We couldn't figure out what it was, says Schultz. 44. He rifled through several hypotheses. Maybe the monkeys were simply satiated and didn't really want any more food. He tried starving them. It didn't work. They ate the food ravenously. But there was no dopamine spike. Schultz and his collaborators spent the late 80s and early 90s trying to find a plausible story for what they were seeing. 45. Over the course of repetition, the dopamine spike had moved from the food to the cue. But what did it mean? If the food had somehow stopped being rewarding, then why were the monkeys always so quick to grab and eat it? That didn't make sense, and so dopamine couldn't be directly representing reward. They ruled out a connection to working memory. They ruled out a connection to motion and a connection to touch. We could not pin it to something, Schultz tells me. You start to pin it to incentive, motivation, as a response to a stimulus that makes you move. We thought that initially, but then we found the concept far too fuzzy. His lab started to home in on the idea that it had something to do with surprise, or unpredictability. There was an idea from psychology called the Rescorla-Wagner model, which suggested that learning is critically dependent on surprise. 46. Perhaps dopamine had something to do with that link. Perhaps it somehow represented either surprise itself, or the learning process that surprise induced. That would explain why the food generated a dopamine spike when it was unexpected, but not when it was cued, and why, in those cases, it was the unexpected cue that prompted the spike. And that was okay, says Schultz. But that would not explain some of the data we had. 47. In particular, there was one further phenomenon Schultz observed, one that was even more mysterious than the first. He was doing a follow-up study, using a similar setup, but this time with levers and juice instead of boxes and food. Once the monkey learned that the cue reliably preceded the juice, however, Schultz tried something new. He gave it a false alarm. He triggered the cue. As usual, the monkey's dopamine activity spiked above the neuron's normal baseline hum. The monkey pressed the lever. No juice came. The monkey's dopamine neurons fell, briefly, but unmistakably, silent. Then I said, well, that is something different than surprise. 48. Dopamine was a riddle. It seemed so clearly, at first, to be the brain's currency of reward. It was clearly measuring something. If not reward, if not attention, not novelty, not surprise, then what? The policy and the value. Function. It's hard to be so smart that the next minute can't fool you. Leo Stein. 49. Over that same period in the 1980s, while Schultz was beginning his experiments on the dopamine system, on the other side of the Atlantic, Bartow and Sutton were starting to make mathematical progress on the reinforcement learning problem. The first big step was to decompose the problem. Learning how to take actions within an environment to maximize reward, they realized, involved two related but potentially independent subproblems, action and estimation. As you began to understand and ultimately master a domain, you learned two important things: how to take the right action in a given situation, and how to estimate the likely future rewards that a state of affairs might hold. A chess player looking at the board, as Bartow and Sutton came to realize, has two distinct hunches. She has a certain instinct for which moves suggest themselves to be played next, and what the opponent is likely to do in response. And she has another instinct for which player in this position is likely to win. These two dimensions of the reinforcement learning problem have come to be known by the technical terms of the policy, what to do when, and the value function, what rewards or punishments to expect. Either of these alone was, at least in theory, enough to solve the problem. If a chess player always knew the right move to play, then it didn't matter if they were lousy at predicting who would win. The reverse, however, was also true. If a chess player, say, always knew exactly who stood better in a given position, then it didn't matter if they weren't sure what to do. Given enough time, they could simply weigh the consequences of each move and choose the one that led to the most promising future. Policy-based approaches led to a system, be it animal, human, or machine, with highly trained muscle memory. The right behavior just flowed effortlessly. Value-based approaches, by contrast, led to a system with a highly trained spider sense. It could tell right away if a situation was threatening or promising. Either, alone, if fully developed, was enough. In practice, however, policy-based approaches and value-based approaches went hand in hand. Bartow and Sutton began to elaborate an idea known as the actor-critic architecture, where the actor half of the system would learn to take good actions, and the critic half would learn to predict future rewards. 50 in rough terms, the actor-critic architecture also neatly described their collaboration. Bartow was first and foremost interested in behavior. Sutton was first and foremost interested in prediction. 51 Going back all the way to his undergraduate thesis in 1978, Sutton had been preoccupied with creating, as he put it, a unified theory of expectation. 52 This fascination with how organisms form and refine their expectations followed him to Amherst in his work with Klopf and Bartow. As Sutton reasoned, developing good expectations, a good value function, meant reconciling your moment-to-moment expectations with the ultimate verdict that came from reality. The final score of the game, the end-of-quarter report, the successful moon landing, the late career encomia from admiring colleagues, the standing ovation, the smiling grandchildren. But if you actually had to wait until the end of a game to learn from it, then the credit assignment problem would indeed be virtually impossible. The logic, he says, is threefold. First, it may be impractical or impossible to remember everything we were thinking and doing at the end of a 90-minute soccer game in which we lost soundly. Do we really gather in the locker room and work backward through every single play? Every shift in our hopes and fears? Second, we want to be able to learn even without a final verdict. A chess game interrupted before its conclusion should still offer us something. If we were about to be checkmated or the position felt hopeless, then that still meant we needed to do something different, regardless of whether the loss or the punishment we felt we had coming ever actually arrived. Likewise, a game decided by a freak, improbable, unforeseeable event in the final seconds doesn't necessarily mean that our earlier expectations were necessarily wrong. Maybe we really were on track to victory. Judging entirely by the final outcome doesn't necessarily make sense, especially in situations affected to some degree by chance. Third, we ideally want to be learning not just after the fact, but as we go along. This is of particular and critical importance for human lives. Many of the most crucial junctures and most important goals of life, getting into college, say, or raising children, or retiring comfortably, we typically only get one shot at. And many mistakes, a falling grade point average, an expanding waistline, a deteriorating relationship, are such that we can realize things are heading off course and adjust long before it's too late. If it is trial and error by which we learn, it mercifully does not require the whole trial nor the whole error for us to do so. Each of these factors, as Sutton explains, makes a theory of expectations more tricky. So obviously we can try to ignore all these things, think of them as nuisances, but I think of them as clues, he says. These are hints from nature, about how we should proceed. 53 It was Sutton himself, as it turned out, who would be first to take those hints. The breakthrough that Sutton made in thinking about predictions is this. As you move forward toward an uncertain future, you maintain a kind of running expectation of how promising things seem. In a chess game, it might be the odds you give yourself to win the game. In a video game, it might be how much progress you expect to make or how many points you expect to rack up in total. These guesses fluctuate over time, and in general they get more accurate the closer you are to whatever it is you're trying to predict. The weekend weather forecast is almost always more accurate on Thursday than it was on Monday. Your ETA as you drive home from the airport will tend to be more accurate the closer you are to home. This means that, in general, as our expectation fluctuates, we get differences between our successive expectations, each of which is a learning opportunity. Sutton called these temporal differences, or TD errors. When one of these temporal differences happens, the later of the two estimates is the one more likely to be correct. And so maybe we don't need to wait until we get the eventual ground truth in order to learn something. Maybe we can learn from these fluctuations themselves. Anytime our expectation changes can be treated as an error in our previous estimate, and hence, an opportunity to learn, not from the ultimate truth, which has yet to arrive, but from the new estimate, made by our very slightly older and wiser self. As Sutton puts it, we are learning a guess from a guess. 54, he adds, as if parenthetically. Sounds a bit dangerous, doesn't it? By the end of the 1980s, this idea, Sutton called it the method of temporal differences, or TD learning, for short, had sharpened into an algorithm, which he called TD lambda, for precisely tuning predictions in the light of subsequent predictions. 55 Inspired by Sutton and Bartow's ideas, Cambridge PhD student Chris Watkins had devised a TD algorithm called Q-learning, which would turn these predictions into actions. 56 Promisingly, he showed that Q-learning would always converge, namely, as long as the system had the opportunity to try every action, from every state, as many times as necessary, it would always eventually develop the perfect value function, the perfect set of expectations for that environment, be it a maze, a chessboard, or something true to life. It was a significant theoretical milestone for the field, of course. Exactly how significant depended on whether you were the kind of person who emphasized the always, or the eventually. The theory looked good, but TD learning had yet to be truly tested in practice. That first real kicking of the tires would happen at IBM Research in New York. A young researcher named Gerald Tesoro, initially interested in computational models of classical conditioning, had been working, over the late 80s and early 90s, on using neural networks to play backgammon. The early results were promising. Then, in 1992, he plugged TD learning into his model, and it took off like a rocket. 57 It was learning guesses from guesses, steadily coming to learn what an advantageous position looked like. This is apparently the first application of this algorithm to a complex non-trivial task, Tesoro wrote. It is found that, with zero knowledge built in, the network is able to learn from scratch to play the entire game at a fairly strong intermediate level of performance, which is clearly better than conventional commercial programs, and which in fact surpasses comparable networks trained on a massive human expert dataset. This indicates that TD learning may work better in practice than one would expect based on current theory. By 1994, his program, dubbed TD Gammon, had reached, as he wrote, a truly staggering level of performance. The latest version of TD Gammon is now extremely close to the world's best human players. 58 The field had long known that it was possible for a programmer to write a system that played better than him or herself. Arthur Samuel had discovered as much with checkers in the 1950s. But this was something new, a program as good as any human player. And it was entirely self-taught, initialized from a random state, and tuned over countless games against itself. It was an enormous validation for TD learning. And it would offer a direct blueprint for success that would be used with surprisingly few changes by 21st century game mastering software like AlphaZero. Sutton and others in the burgeoning field of reinforcement learning had taken nature's hints. But now it was their turn to offer something back. In one of the most stunning moments in the field's history, the mathematical framework that had grown initially out of psychology and neuroscience was about to re-enter those fields in a big way. A neural substrate of prediction and reward. In the early 1990s, as Tesoro was fine-tuning his backgammon system, a young cognitive scientist named Peter Dyan, who had spent fertile time in Bartow's lab and had worked with Watkins on his convergence proof, found himself moving from one side of the field and the world to the other. From studying the mathematics of temporal difference at the University of Edinburgh, he landed with a group of neuroscientists at the Salk Institute in San Diego. Dyan and a fellow postdoc named Red Montague, working with Salk Institute neuroscientist Terry Sejnowski, had a hunch that not only did the framework of reinforcement learning explain how real human and animal brains might operate, but that it might literally be what brains were doing. We went after the role of a set of systems in your brain that report on value and reinforcement, says Montague. And we, at the time, just sort of thought, these things should be implementing a certain kind of algorithm. 59 Montague thought that these sorts of learning mechanisms might be one of the bedrock properties of almost every animal that learns. Dyan was coming from his work on temporal difference learning, which seemed like it might be a candidate for one of these universal algorithms. It worked on the whiteboard, that is, it converged. It worked in machines. TD Gammon was a stronger player than all but the very best human players alive. Perhaps it worked in brains, too. The two of them began speculating about how a neurological system for learning from temporal differences might work. Obviously we knew there must be a link to neuroscience. Diane explains to me over a conference table at Uber headquarters in San Francisco, where he's spending his sabbatical year from University College London. And then, he says, we came across these data from Wolfram Schultz. 60 Suddenly Diane hops up and begins scrolling dopamine response diagrams on the whiteboard excitedly. He points to the flat, background static, ho-hum response when the monkey gets the juice reward it fully expects after seeing the cure light. So this part of the signal is very transparent. And that's what you see in the Rescorla-Wagner rule. That's the beautiful aspect of what comes from older psychology. Then he points to the initial dopamine spike caused by the cue light itself. But it's this part of the signal which is confusing, he says. Because that is not expected from the psychological perspective. So at various times, you can see Wolfram sort of struggling with what that means. When Diane and Montague looked at the data from Schultz, the data that Schultz, along with the entire neurophysiology community, found so inscrutable, they knew exactly what it meant. It was a temporal difference. It was a sudden fluctuation in the monkey's expectation, in its value function, its prediction of how good a state of affairs it was in. A sudden spike above the brain's dopamine background chatter meant that suddenly the world seemed more promising than it had a moment ago. A sudden hush, on the other hand, meant that suddenly things seemed less promising than imagined. The normal background static meant that things, however good or bad they were as good or bad as expected. A spike in the dopamine system was not reward as such, but it was related to reward. It wasn't uncertainty, or surprise, or attention per se, but it was intimately, and for the first time legibly, related to all of them. It was a fluctuation in the monkey's expectation, indicating that an earlier prediction had been in error. It was its brain learning a guess from a guess. The algorithm that worked so well on paper, and so well in silicon, had just been found in the brain. Temporal difference learning didn't just resemble the function of dopamine. It was the function of dopamine. Schultz, Diane, and Montague published an explosive paper together in Science in 1997, announcing their discovery to the world. They had found, as they put it, a neural substrate of prediction and reward. 61 The effect, across neuroscience and computer science alike, was huge. An idea developed in a pure machine learning context, inspired by models of classical and operant conditioning from psychology, had suddenly come full circle. It wasn't just a model of how artificial intelligence might be structured. It appeared to offer a description of one of the universal principles for intelligence, period. It's thought that eyes evolved anywhere from sort of 40 to 50 separate times. Biology has discovered eyes over and over again, all kinds of different eyes. Montague explains point 62, I think it's the same thing in the learning domain. Learning algorithms are so profoundly important to understand how to take experience now, reorganize your internal structure, and produce actions in the future, that you should expect that these algorithms have been stumbled into by biology in many different contexts. And so you see reinforcement learning systems, reward systems, in bees, and sea slugs, and birds learning songs, and human beings, and rodents, etc. 63. Diane sees it the same way. It's no surprise that we come endowed with these sorts of things, he says. The idea that you would see it quite so transparently in the activity of these dopamine neurons. That was quite a revelation. 64 Visiting Wolfram Schultz's lab in Cambridge. At age 75, he is still as animated and energized by his work as ever. I ask him if this felt like a revelation at the time. Surprisingly, he says no. The revelation, in his view, is that the humble TD learning model, which described the activity in the brains of his monkeys as they fumbled for food, is, 20 years later, enabling the current contemporary breakthroughs of AI. That we've been able to take these universal ideas from nature and implement them synthetically, is what blows his mind. The revelation came, he says, when I realized that the TD model goes into what we now see, the Go programming, and this artificial intelligence, machine learning thing. That was a revelation, where I said, my God, what have I done? You know, understanding my data came from the Rescorla-Wagner model, from a prediction error, but the consequence, like, Jesus Christ. I mean, we knew Tesoro was programming backgammon with a TD model. Okay, I'm not a backgammon player, but I'm a Go player. Not a very good one, but I said, damn it, if they can program Go, which has been a problem before, it's a really good model. And I saw that before they programmed Go. I tell him I think it's remarkable to see such a clear and powerful synthesis of work across neurophysiology and machine learning, with such powerful implications for both fields. Absolutely, he says. Absolutely. That's the charm of it. You get everything together. Just makes sense. 65. The effect on neuroscience has been transformative. Point 66, as Princeton's Yoel Neave puts it, the potential advantages of understanding learning and action selection at the level of dopamine-dependent function of the basal ganglia cannot be exaggerated. Dopamine is implicated in a huge variety of disorders ranging from Parkinson's disease, through schizophrenia, major depression, attentional deficit hyperactive disorder etc., and ending in decision-making aberrations such as substance abuse and addiction. 67. It's true that there is much to be worked out, and what now seems like the canonical story may be overturned or complicated in time. Point 68, but it is clear, says Neave, that reinforcement learning has already left its permanent mark on the study of decision-making in the brain. 69, she recounts her first time attending the annual Society for Neuroscience meeting, a gathering of some 30,000 researchers across the field. I remember looking up reinforcement learning the first time I went, which was probably 2003, 2004. There were maybe 5 posters in the whole meeting. It's a whole week of meetings. Every day has 2 poster sessions, so one in the morning, one in the afternoon. Now, she says, every poster session has a whole subsection, a whole row, about this. It's really come a long way in 10, 15 years. 70, she adds. There were lots of studies kind of testing predictions of the theory in the brain and seeing, it seems like, gosh, these neurons read the textbook. They read the Sutton and Bartow textbook. They know exactly what they need to do. Happiness and error. If the TD learning model has revealed the function of dopamine in the brain, not as the brain's currency of reward, not its expectation of future rewards, but its error in its expectation of future rewards, then it leaves some questions open. In particular, it leaves open the connection to the subjective experience of pleasure and happiness. If elevated levels of dopamine signal something to the effect of things are going to be better than I thought they were going to be, then that feeling is, itself, pleasurable. And you can see how humans and animals alike would go out of their way to get that feeling, including by way of direct chemical and electrical stimulation of dopamine neurons. You can also begin to see how artificially elevating dopamine levels produces an inevitable crash. Thinking that things will be better than you thought they would be only works for so long. Eventually you realize they're not better than you thought they would be, and the dopamine chatter hushes, as it did in Wolfram Schultz's experiments with monkeys, when the juice cue light blinked, but no juice was present. It's possible, in effect, for dopamine to write checks that the environment can't cash. Those checks eventually, inevitably bounce. Then your value function must, inevitably, come back down to earth. This, of course, is the classic experience of dopamine-related drugs, cocaine being a prototypical example. The drug works in large part by inhibiting the brain's reuptake of dopamine, leading to a temporary flood of it. The TD story suggests that the brain interprets this as a pervasive sense that things are going to be great, but the dopamine is writing checks that the environmental rewards can't cash. Eventually the predicted greatness doesn't come, and the equal and opposite negative prediction error is sure to follow. It seemed like everything was going to be so great. We can chemically fool our brain's prediction mechanism, but not forever. As the writer David Lenson puts it, cocaine promises the greatest pleasure ever known in just a minute more, if the right image is presented to the eyes, if another dose is administered, if a sexual interaction is orchestrated in just the right way. But that future never comes. There is a physical pleasure to the drug, to be sure, but it is incidental, trivial, compared to what is always just about to happen. 71 Understanding cocaine as a drug of dopamine, and dopamine as a chemical of temporal difference, of fluctuations in our expectation, makes the story clear. By artificially dumping the brain's supply, one experiences not the bliss that things are great, but the giddy euphoria that things are surprisingly promising. If that promise isn't kept, the temporal difference error swings the other way, and our dopamine system goes silent. It was our high expectations that were in error. We were duped. The connection between dopamine and the subjective experiences of happiness and pleasure is still being worked out. The University of Michigan's Kent Berridge, for instance, has spent the better part of his career teasing apart the neuroscience of wanting from liking. 72 Meanwhile, University College London's Rob Rutledge has developed a mathematical model of happiness that explicitly involves dopamine. Rutledge, working with Peter Dyan and a group of collaborators at UCL, devised an experiment in which people would be making various bets and accumulating a sum of money while periodically being asked, "How happy are you right now?" 73 They modeled the task using the mathematical tools of reinforcement learning in order to tease apart how much money the subject had made so far, how much in total they anticipated making, and whether they had recently been pleasantly or unpleasantly surprised in adjusting either of these running counts up or down. The goal was to figure out the best mathematical correlate for their self-reported momentary happiness. Rutledge's findings were illuminating on a number of counts. The first was that happiness was fleeting. However happy it made you to receive £1 in a particular bet, 5 bets later, 92% of that impact had disappeared. Anything that happened more than 10 bets ago may as well never have happened. This meant that subjects' happiness had virtually nothing to do with how much money they had actually made. Happiness did seem at least partly determined by how much subjects expected to make, but what seemed most crucial, however, was the violation of those expectations. As Rutledge writes, momentary happiness is a state that reflects not how well things are going but instead whether things are going better than expected. 74 This sounds exactly like a temporal difference error, in other words, exactly like the role played by dopamine. Zooming out, we begin to get a neuroscientific and computational account of the well-known phenomena of what's called the hedonic treadmill. Namely, people have a stubborn and persistent return to their emotional baseline, regardless of changes in their long-term quality of life. 75 Lottery winners and paraplegics, famously, are emotionally back to more or less where they started not long after their respective dramatic life changes. 76 Dopamine and reinforcement learning offer clues as to why. If happiness comes not from things having gone well, not from things being about to go well, but from things going better than expected, then yes, for better or worse, as long as our expectations keep tuning themselves to reality, then a long-term state of being pleasantly surprised should be simply unsustainable. Unfortunately, the study rules out such simple life hacks as always maintain low expectations. As Rutledge says, lower expectations make it more likely that an outcome will exceed those expectations and have a positive impact on happiness. However, expectations also affect happiness even before we learn the outcome of a decision. If you have plans to meet a friend at your favorite restaurant, those positive expectations may increase your happiness as soon as you make the plan. 77 In the research paper, he and his co-authors note the possibility of an airline, for instance, claiming that there is a 50% chance of a 6-hour delay, then announcing that the delay will in fact be 1 hour. Lowering expectations increases the probability of positive outcomes. However, lower expectations reduce well-being before an outcome arrives, limiting the beneficial scope of this manipulation. 78 In other words, Rutledge says, you can't kind of, just lower your expectations and that solves everything. 79 The links between dopamine, TD errors, and happiness have caused some researchers to begin pondering whether there are ethical implications for the subjective happiness of reinforcement learning agents. Brian Tomasik of the Foundational Research Institute, which aims to understand and reduce suffering, has pondered at some length the question of whether reinforcement learning programs have moral standing. Does it matter how we treat them? His answer is a tentative and limited yes. To the degree that they are built on similar principles as animal and human brains, there may well be some non-zero ethical consideration that they are owed. 80 Present-day IL algorithms matter vastly less than animals, he notes. Still, I think IL agents do matter to a non-zero degree, and at large scales they may begin to add up to something significant. 81 Subsequent work by others has gone so far as to explicitly define the happiness of a reinforcement learning agent by its TD errors. 82 By this logic, they note, agents that know the world perfectly have zero expected happiness. Indeed, if dopaminergic, happiness comes in large part from being pleasantly surprised, from having opportunities to better learn what to expect, then complete mastery of any domain seems necessarily correlated with boredom, a point that has ethical implications not only for future ethics of IL agents, but of course, for humans too. It suggests, for one thing, an evolutionary and computational story about the hedonic treadmill. If our subjective happiness is intimately tied to being pleasantly surprised, and it's the nature of intelligence to work tirelessly to anticipate and mitigate surprise, then we can see how happiness of this kind becomes fleeting. We can also see the evolutionary advantage. An infant may be delighted at the mere ability to wave their arm on command. For an adult, this ability no longer carries, shall we say, the thrill it did in infancy. Though we may bemoan the restlessness this engenders in adults, the insatiability, this is all part of the curriculum of life. If basic motor skills were enough to thrill us indefinitely, we'd never make it to adulthood at all. As Andrew Bartow puts it, this fleetingness was something Klopf anticipated back in the early 1970s. His point was a homeostatic stabilization mechanism. It tries to reduce the discrepancy to zero, and when it's zero, it's happy, it stops. The kind of system he wanted was never happy. So it's this incessant exploration. 83 The connection between reinforcement learning, dopamine, happiness, and exploration, as well as addiction, is something we'll return to in Chapter 6. Beyond reinforcement. Reinforcement learning, rooted very consciously in the animal learning studies of the early 20th century, flourished in the abstract, mathematical world of machine learning in the 1970s and 80s, only to triumphantly burst back into animal behavior literature with a nearly perfect model that has become the accepted story for the role of dopamine in the brain. 84 This model, in turn, has given us deeper insight into human motivation and human happiness. Meanwhile, neuroscientific evidence, as recently as 2018, is beginning to suggest that the crazy hypothesis of Harry Klopf, that neurons are hedonists, motivated by their own individual Thorndikean laws of effect, may not be so far off after all. 85 I think that neuroscience is getting close to something that is very similar to what Klopf was proposing, says Bartow. With some pride on behalf of his late former mentor, to whom his and Sutton's textbook is dedicated. 86 Reinforcement learning also offers us a powerful, and perhaps even universal, definition of what intelligence is. 87 If intelligence is, as computer scientist John McCarthy famously said, the computational part of the ability to achieve goals in the world, 88 Then reinforcement learning offers a strikingly general toolbox for doing so. Indeed, it is likely that its core principles were stumbled into by evolution time and again, and it is likely that they will form the bedrock of whatever artificial intelligences the 21st century has in store. In some ways, though, a deeper understanding of the ability of animals and machines to achieve goals in the world has kicked the more profound philosophical can down the road. This theory, pointedly, does not tell us what we value, or what we ought to value. Dopamine, in this way, is every bit as mysterious now as when its role was lesser known. If it represents a scalar prediction error, it hides a vast realm of complexity in how that prediction is measured. If, behind door number 1, is not the Caribbean vacation we expected but, rather, a trip to view the aurora borealis, our dopamine will quickly and reliably indicate whether we are pleasantly or unpleasantly surprised by this. But how is the value of those alternatives actually being assessed? 89 Dopamine is mum on this point. Meanwhile, we take up another question. Reinforcement learning in its classical form takes for granted the structure of the rewards in the world and asks the question of how to arrive at the behavior, the policy, that maximally reaps them. But in many ways this obscures the more interesting, and more dire, matter that faces us at the brink of AI. We find ourselves rather more interested in the exact opposite of this question. Given the behavior we want from our machines, how do we structure the environments rewards to bring that behavior about? How do we get what we want when it is we who sit in the back of the audience, in the critic's chair, we who administer the food pellets, or their digital equivalent? This is the alignment problem, in the context of a reinforcement learner. Though the question has taken on a new urgency in the last 5 to 10 years, as we shall see, it is every bit as deeply rooted in the past as reinforcement learning itself. 5. Shaping. Nature has placed mankind under the governance of two sovereign masters, pain and pleasure. It is for them alone to point out what we ought to do, as well as to determine what we shall do. Jeremy Bentham 1. Design of reward functions is not often discussed, although it is perhaps the most difficult aspect of setting up an IL system. Maya Matarik 2. In 1943, B.F. Skinner was working on a secret wartime project, initially sponsored by, of all groups, the consumer food company General Mills. General Mills had given Skinner the top floor of its gold medal flour mill in Minneapolis to build a laboratory. The project was one of the more audacious ones entertained during that time. Skinner and his lab were going to teach pigeons how to peck at images of bomb targets, then put the birds, in groups of 3, inside of actual bombs to steer them as they dropped. My colleagues and I knew, said Skinner, that, in the eyes of the world, we were crazy. Skinner was aware that many would see the project as not only insane but cruel. To the first point, he noted that humans have a long and storied history of putting animals, often superhuman, senses to human purposes, the seeing-eye dog, the truffle-hunting pig, and so forth. To the second point, he argued, the ethical question of our right to convert a lower creature into an unwitting hero is a peacetime luxury, for Skinner had long been working on the study of reinforcement, and his famous Skinner boxes functioned like upgraded, mid-20th century versions of Thorndike's puzzle boxes. Their lights and levers and mechanical fruit dispensers, often repurposed from vending machines, allowed for a precise and quantitative study of reinforcement, and they would be used by generations of researchers to follow, not least including Wolfram Schultz in his study of dopamine in monkeys. With such tools at his disposal in the 1950s, Skinner began to study how animals learn to take actions to maximize their rewards, typically in the form of food, under a number of different conditions. He tested different types of what he called reinforcement schedules and observed their effects. For instance, he compared reinforcing by ratio, where a certain number of correct actions would result in a reward, against reinforcing by interval, where a correct action, after a certain time, would yield the reward. He also tested fixed against variable reinforcement, where the number of behaviors or length of time was either held constant or allowed to fluctuate. Skinner famously found that the fiercest and most repetitive or persistent behavior tended to come from variable ratio schedules, that is, when a reward would come after a certain number of behaviors, but the number would fluctuate. 5 These findings held implications for the understanding of gambling addiction, for instance, and tragically, they also undoubtedly led to the devising of ever more addictive gambling games. In his secret top-floor laboratory, though, Skinner had a different challenge before him, to figure out not which schedules of reinforcement ingrained simple behaviors most deeply, but rather how to engender fairly complex behavior merely by administering rewards. The difficulty became obvious when he and his colleagues one day tried to teach a pigeon how to bowl. They set up a miniature bowling alley, complete with wooden ball and toy pins, and intended to give the pigeon its first food reward as soon as it made a swipe at the ball. Unfortunately, nothing happened. The pigeon did no such thing. The experimenters waited and waited, and eventually ran out of patience. Then they took a different tack. As Skinner recounts, "We decided to reinforce any response which had the slightest resemblance to a swipe, perhaps, at first, merely the behavior of looking at the ball, and then to select responses which more closely approximated the final form. The result amazed us. In a few minutes, the ball was caroming off the walls of the box as if the pigeon had been a champion squash player. The result was so startling and striking that two of Skinner's researchers, the wife and husband team of Marion and Keller Breland, decided to give up their careers in academic psychology to start an animal training company. We wanted to try to make our living," said Marion, using Skinner's principles of the control of behavior. 6 Their friend Paul Meal, whom we met briefly in Chapter 3, bet them $10 they would fail. He lost that bet, and they proudly framed his check. 7 Their company, Animal Behavior Enterprises, would become the largest company of its kind in the world, training all manner of animals to perform on television and film, in commercials, and at theme parks like SeaWorld. More than a living, they made an empire. 8 Skinner, too, would come to think of this moment, at the miniature bowling alley inside the secret flour mill laboratory, as an epiphany that changed the arc of his career. The critical component, he saw, was the gradual shaping up of behavior by reinforcing crude approximations of the final topography instead of waiting for the complete response. 9 Project Pigeon, as it was known, was, however, ultimately something of a mixed success. The pigeons themselves worked marvelously. So marvelously, in fact, that they seemed to distract the committee from the government's Office of Scientific Research and Development. The spectacle of a living pigeon carrying out its assignment, no matter how beautifully, Skinner wrote, simply reminded the committee of how utterly fantastic our proposal was. 10 And unbeknownst to Skinner at the time, the government was hard at work on the Manhattan Project. A bomb with a blast radius so large that, in his words, it looked for a while as if the need for accurate bombing had been eliminated for all time. Nevertheless, the Pigeon Project ultimately found a home at the Naval Research Laboratory, as an effort called ORCON, short for Organic Control, where studies continued into the post-war 50s. Skinner felt vindicated that the concept had been shown to work, writing proudly in the late 1950s that the use of living organisms in guiding missiles is, it seems fair to say, no longer a crackpot idea. 11 This vindication, though nice, was however beside the point. The point was they had discovered shaping, a technique for instilling complex behaviors through simple rewards, namely by rewarding a series of successive approximations of that behavior. This makes it possible, Skinner wrote, to shape an animal's behavior almost as a sculptor shapes a lump of clay. 12 This idea, and this term, would become a critical one through the rest of Skinner's life and career. 13 It had implications, he saw, from the beginning, for business and for domestic life. As he wrote, some of these reinforcement schedules correspond to the contingencies established in industry in daily wages or in piecework pay. Others resemble the subtle but powerful contingencies of gambling devices, which are notorious for their ability to command sustained behavior. 14 He also felt the possible parenting ramifications were significant. A scientific analysis can, however, bring about a better understanding of personal relations. We are almost always reinforcing the behavior of others, whether we mean to or not. Skinner noted that parental attention is a powerful reinforcer, and that parents can, by being slow to respond to polite requests, unwittingly train their children to be annoying and pushy. The remedy, he said, is to respond more promptly and consistently to acceptable bids for attention, and less to those that are loud or impolite. 15 Perhaps, most prophetically, Skinner thought that with the principles emerging in his work, education in its broadest sense, of humans, of animals, might become a rigorous, objective field in which leaps forward could and would be made. Teaching, it is often said, is an art, as he put it, but we have increasing reason to hope that it may eventually become a science. 16 Skinner would be, perhaps, more right than he even anticipated. In the 21st century, when the term shaping is used, it is just as likely to be a machine learning researcher who is talking as a psychologist. The study of rewards, and in particular, how to strategically administer rewards to get the behavior you want, and not the behavior you don't, has indeed become a rigorous quantitative science, albeit perhaps not with the organic learner Skinner imagined. The problem of sparsity. There's a way to do it better, find it. Thomas Edison. 17 It was Scottish philosopher Alexander Bain who in 1855 appears to have coined the phrase trial and error to describe how humans and animals learn. 18 His other phrase, groping experiment, is equally memorable, but appears not to have stuck. At its most basic, reinforcement learning is a study of learning by trial and error, and the simplest algorithmic form this trial, or groping, if you prefer, takes is what's called epsilon greedy, written with the Greek letter as greedy. The Greek letter is often used by mathematicians to mean a little bit, and greedy is shorthand for be greedy, except for a smidgen of the time. An agent operating by greedy will, most of the time, 99%, let's say, take the action it believes will bring it the greatest total reward, based on its limited experience so far. But of the time, the other 1%, for instance, it tries something completely at random. In an Atari game, say, this would mean randomly mashing a button some percentage of the time, just to see what might happen. There are many different flavors of how to learn from this exploratory behavior, but the underlying idea is the same. Flail around, do more of what gets you rewarded and less of what gets you punished. You can do that by explicitly trying to understand how the world works, model-based RL. Or just by honing your instincts, model-free RL. You can do it by learning how much reward certain states or actions can bring, value learning. or by simply knowing which strategies tend on the whole to do better than which others, policy learning. Virtually all approaches, though, are built around the idea of first stumbling accidentally onto success, and then building up a tendency to do more and more of whatever appears to have worked. Some tasks, as it turns out, admit much more readily to this approach than others. In a game like Space Invaders, for instance, hordes of enemies descend toward you, and all you can do is move left, move right, and shoot. Randomly mashing the buttons will probably earn you at least a few kills, each of which is worth points, and those early points can be used to start the learning process, by which certain patterns of behavior get strengthened and better strategies developed. You may realize, for instance, that points only come after you've fired a shot, and so you'll begin firing more often, and in turn, scoring more. Such games are said to have dense rewards, which makes them relatively easy to learn. In other games, take chess, for instance, rewards aren't nearly as immediate, but they are nonetheless certain. A chess game is typically over, one way or another, after a few dozen moves, and the rules make it almost impossible to go more than a couple hundred. Even if you're clueless about the finer points of strategy, and are shoving pieces around the board at random, you'll at least know before long whether you won, lost, or drew. There are a number of situations, however, in which getting any reward at all would take a veritable miracle. Skinner, of course, discovered this firsthand in his attempts to reward a bird for bowling a tiny ball down a miniature bowling alley. The bird, clueless about what game it had been put into, might take years to happen upon the right behavior. Of course it, and Skinner, would have died of hunger long before then. The same thing is true for mechanical learners. Getting a humanoid robot to kick a soccer ball into a net, for example, might involve hundreds of thousands of precise torques on dozens of joints, all perfectly coordinated. It's hard to imagine a robot that initially moves its dozens of joints at random managing to even stay upright, let alone make meaningful contact with the ball, let alone send it into the net. Reinforcement learning researchers know this as the problem of sparse rewards, or more succinctly as the problem of sparsity. If the reward is defined explicitly in terms of the end goal, or something fairly close to it, then one must essentially wait until random button pressing, or random flailing around, produces the desired effect. The mathematics show that most reinforcement learning algorithms will, eventually, get there, but eventually, in practical terms, might arrive long after the sun has exploded. If you're trying to train a Go-playing program to defeat the world champion, and you give it 1 point every time the world champion resigns and 0 points otherwise, you are going to be waiting a very long time indeed. The problem of sparsity also has safety implications. If, in some future time, you're developing a super-intelligent AI with vast capabilities, driven by greedy reinforcement learning, and you decide you'll reward it with 1 point if it cures cancer and 0 otherwise, watch out, because it will have to try a lot of random things before it stumbles into that first reward. Many of them are likely to be ugly. When I sit down with Brown University's Michael Littman, who has spent his career working in reinforcement learning, I ask him whether his lifelong research interest in reinforcement has been useful as a parent. His mind instantly goes to the problem of sparsity. He remembers joking with his wife about using sparse rewards with their son. How about this? Until he can learn to speak Chinese, let's not feed him. That would be a good motivator. Let's see how that works. Littman laughs. My spouse is very grounded. She's like, no, we're not gonna play that game. 19 of course, Littman knows, as Skinner did, not to play that game. Indeed, the problem of sparsity has inspired the reinforcement learning community to hark back to Skinner's time, and they have drawn rather directly on his advice. Point 20 in particular, his ideas about shaping have led to 2 distinct but interwoven strands of thought, one about curriculum, the other about incentives. The importance of curriculum. The key insight of shaping, that in order to get complex behavior, we may first need to strategically reward simpler behavior, is every bit as applicable to humans, of course, as to animals. You have to walk before you can run, we say, an adage that describes more facets of the human experience than can be named or counted, in addition to being literally true. It is a striking and characteristic feature of human life that we spend our first decades moving through the world with literal and figurative training wheels, bowling, as it were, with literal and figurative bumpers. Many animals are simply thrown into the full complexity of life. A number of wild animals must be prepared to run full speed from predators, for instance, within hours of birth. In contrast, it takes us decades before we can operate heavy machinery, and it's not uncommon for us to be past our physical prime by the time we have to fend for ourselves. What separates 21st century humans from their cave-dwelling ancestors isn't raw intellectual power, but a good curriculum. Indeed, Skinner thought that we shouldn't be so quick to pass judgment on the mental capacities of animals. With the right curriculum, they might be able to astoundingly surpass what we think of their species as capable of, just as humans have. As Skinner put it, if an experimenter is simply waiting until a complicated set of behaviors arises to begin reinforcing the behavior, then it's hardly a test of whether that animal can or cannot perform the behavior. The ability of the experimenter rather than that of the organism is being tested. It is dangerous to assert that an organism of a given species or age cannot solve a problem. As the result of careful scheduling, pigeons, rats, and monkeys have done things during the past 5 years which members of their species have never done before. It is not that their forebears were incapable of such behavior, nature had simply never arranged effective sequences of schedules. Point 21. It can be hard to appreciate the extent to which our lives, and the world around us, has been sculpted into just such effective sequences of schedules. We have somehow come to think of being smoothly onboard and shown the ropes as natural, when, in fact, the opposite is the case. Nature simply is. There is no tutorial. The human world, by contrast, is elaborately architected to be learnable. Part of what makes great games great, for example, is the way that they shape our play. Consider one of the most famous and historically significant video games of all time, Nintendo's 1985 Super Mario Bros. One's very first time playing the game might be hard to recall, but a close look at the game's first 10 seconds reveals that it has been carefully, brilliantly designed to teach you how to play. You begin with an enemy Goomba approaching from the right. If you do nothing, you die. You have to teach the player in a natural way that they need to avoid them by jumping over them, says the game's designer, the legendary Shigeru Miyamoto. Point 22. This is the game's first and most important lesson, mushroom. Looking guys are bad, and you must jump. But Miyamoto had a problem. There are also good mushrooms, which you have to learn, not to dodge, but to seek. This gave us a real headache, he explains. We needed somehow to make sure the player understood that this was something really good. So now what? The good mushroom approaches you in an area where you have too little headroom to easily jump over it, you brace for impact, but instead of killing you, it makes you double in size. The mechanics of the game have been established, and now you are let loose. You think you are simply playing. But you are carefully, precisely, inconspicuously being trained. You learn the rule, then you learn the exception. You learn the basic mechanics, then you are given free rein. We should perhaps not be so surprised that the same principle of shaping, the instilling of complex behavior through successive approximations, applicable to Skinner's pigeons is applicable to human learners as well. And we should perhaps not be surprised to find that it's every bit as applicable when the learners are machines. It has, of course, been known since the inception of machine learning that some problems, some environments, some games are easier than others. But only gradually did it come to be appreciated that a system trained first on an easier form of a problem may be in a better position to learn a more difficult one than an agent trained from scratch. Point 23. In the 1980s, Richard Sutton and Andrew Bartow were working with their colleague Oliver Selfridge on using reinforcement learning to train a simulated cart on wheels to balance a pole on itself without tipping. The taller and heavier the pole, the easier it is to keep it upright, just as it is easier to balance, say, a baseball bat on one's hand than a ruler. They found that their cart system required fewer total attempts if it was first trained on a tall, heavy pole and then switched to a shorter, lighter one than if it was trained on the shorter, lighter pole from the beginning. Point 24. Researchers have periodically stumbled on the same insight in other contexts. UC San Diego linguist Jeffrey Ellman, for instance, was experimenting in the early 90s with getting neural networks to correctly predict the next word in a sentence. Discouragingly, several initial attempts failed. Put simply, he says, the network was unable to learn the complex grammar when trained from the outset with the full adult language. However, when the training data were selected such that simple sentences were presented first, the network succeeded not only in mastering these, but then going on to master the complex sentences as well. 25. This is a pleasing result, says Ellman, because the behavior of the network partially resembles that of children. Children do not begin by mastering the adult language in all its complexity. Rather, they begin with the simplest of structures and build incrementally until they achieve the adult language. In both cases, the use of a curriculum, an easier version of the problem, followed by a harder version, succeeded in cases where trying to learn the more difficult problem by itself could not. Keller and Marion Breland, in their work at Animal Behavior Enterprises, had seen the critical importance of a good curriculum in their efforts to train a pig to deposit large wooden coins in a piggy bank. They began with a single coin, right next to the bank, and gradually moved it farther and farther away from the bank, and also farther and farther from the pig. Point 26. More recently, the machine learning community has returned to this idea of working backward. A group of UC Berkeley roboticists in 2017 wanted to train a robotic arm to slide a washer onto a long bolt. Waiting for the robot to somehow stumble onto this behavior at random would have taken an eternity. But starting from the washer almost totally all the way down the bolt, they could teach the robot to push it down the last little bit. Then with the washer just barely on the bolt, the robot could learn to slide it all the way down. Then with the washer near the bolt in an easy orientation, the robot could learn to put the bolt through the hole. They were finally able to back their way up to a system capable of being handed the washer anywhere and any which way, and able to dexterously rotate and fasten it. Point 27. No less a game expert than legendary chess world champion Bobby Fischer used a similar strategy in his instructional book Bobby Fischer Teaches Chess. The book, intended for beginners, contains dozens of examples of checkmate in a single move, then progresses to 2-move checkmates, then 3 and 4-move mating combinations. Discussion of middle game and opening play, as well as longer-term strategies, is put off. For later books, Fischer focuses exclusively on teaching beginning players how to recognize opportunities to end the game. This particular curriculum has proven very successful, indeed. Some of today's grandmasters endorse it as the perfect first chess book for a new player. 28, and it has become the best-selling chess book of all time. Point 29. The natural next step, it would seem, is treating the construction of a good, learnable curriculum as itself a machine learning problem, and seeing if it might be possible to automate the curriculum design process. Recent research has looked into ways to automatically identify tasks of appropriate difficulty and examples that can maximally promote learning in the network. The early results in this vein are promising, and work is ongoing. Point 30. Perhaps the single most impressive achievement in automated curriculum design, however, is DeepMind's board game dominating work with AlphaGo and its successors AlphaGo Zero and AlphaZero. AlphaGo always has an opponent at just the right level, explains lead researcher David Silver. 31. It starts off extremely naive. It starts off with completely random play. And yet at every step of the learning process, it has an opponent, a sparring partner, if you like, that's exactly calibrated to its current level of performance. And who, exactly, is this perfect sparring partner, always calibrated to be at just the right difficulty? The answer is simple, elegant, and, in hindsight, obvious. It plays against itself. The delicate matter of incentives. Whether dealing with monkeys, rats, or human beings, it is hardly controversial to state that most organisms seek information concerning what activities are rewarded, and then seek to do, or at least pretend to do, those things, often to the virtual exclusion of activities not rewarded. Stephen Kerr. 32. If the reward system is so designed that it is irrational to be moral, this does not necessarily mean that immorality will result. But is this not asking for trouble? Stephen Kerr. 33. It's the reward system, stupid. The Editors, Academy of Management Executive. 34. The second approach to overcoming sparsity is, rather than using a curriculum and beginning first with a simplified version of the problem, instead to use the normal full-scale version of the problem while adding some bonus rewards that serve to point the learner in the right direction or encourage behaviors that correlate with success. These are known in the field as pseudo-rewards, or shaping rewards, but it's simplest just to think of them as incentives. Skinner gave his pigeon a little bit of food for looking at and approaching the ball, activities that necessarily preceded the swipe he was ultimately looking for. The same idea applies in machine learning settings. For instance, the true reward of a house-cleaning robot might be a spotless house, but you can give it some incentives for each bit of dirt it vacuums up. Or your delivery drone might ultimately be trying to arrive at some destination, but you can give it a little bit of reward for making progress in the right direction. This is often enormously helpful at giving an agent that would otherwise be flailing at random until it accomplished its goal by pure chance a sense of whether it is getting hotter or colder, whether it's generally behaving in the right way and altering its behavior in the right direction. Often we break a problem down into discrete steps in order to make it psychologically easier to stay motivated. Imagining a completed PhD dissertation or book manuscript years from now makes it hard to judge the quality of an individual day's work. Imagining all the weight we hope to lose by next year can make the costs and benefits of a particular cupcake or second helping feel diffuse. As parents, as teachers, as coaches, we know that a well-timed high five or good job can help get a 2T through the tough slog of constant practice, even when mastery feels impossibly distant. Of course, anyone who has worked with humans, or even has simply been one, knows that to create incentives is to play with fire. They must be very carefully designed indeed, or trouble often awaits. Point 35. As management expert Stephen Kerr famously put it in his classic 1975 paper, as soon as you begin to think about adding additional reward, you are in immediate danger of the folly of rewarding A, while hoping for B. 36. Kerr's analysis of incentives gone wrong has become a landmark paper in management science, and Kerr has spent much of his career working with businesses from General Electric to Goldman Sachs on how to think more carefully about incentives. Amazingly enough, when asked where his inspiration came from, Kerr cited both machine learning and B.F. Skinner. The fact that machines can be programmed to learn, and that a chess-playing machine can be programmed to never make the same mistake twice, was very fascinating to me, Kerr says. I was immediately intrigued with the possibility that a machine could become a better chess player than the actual programmer. 37. As for Skinner, Kerr concedes, in regard to the folly article, obviously B.F. Skinner got there before me. I never claimed otherwise. I remember reading Skinner saying he would scream at his rats, "Why don't you behave?" after they wouldn't do what he wanted or expected. Skinner probably would turn over in his grave if he thought people were reading my article without having read his work. Obviously, Skinner did the work, but I was able to help bottle it in the right package for business applications. Blaming the rat was a great learning lesson. What the folly is really about is that it is not always the employee's fault. Management is responsible for all too many employee dysfunctionalities. Indeed, for Skinner, one could almost never blame the rat or the employee. Our behavior, he felt, was almost fully determined by our incentives and our rewards. A television interviewer at one point asked Skinner, where does that leave free will? Skinner replied, it leaves it in the position of a fiction. 38. The free will argument aside, problems of incentive pervade not just animal psychology, and not just corporate management. Some of the most memorable, in fact, come from those ruthless and creative reward maximizers we call children. University of Toronto economist Joshua Gans wanted to enlist the help of his older daughter in potty training her younger brother. So he did what any good economist would do. He offered her an incentive. Anytime she helped her brother go to the bathroom, she would get a piece of candy. The daughter immediately found a loophole that her father, the economics professor, had overlooked. I realized that the more that goes in, the more comes out, she says. So I was just feeding my brother buckets and buckets of water. Gans affirms, it didn't really work out too well. 39. Princeton cognitive scientist Tom Griffiths had an eerily similar situation happen with his own daughter. She really liked cleaning things. He tells me, she would get excited about it. We got her own little brush and pan. There were some, chips on the floor, and she got her brush and pan and cleaned them up, and I said to her, wow. Great job. Good cleaning. Well done. 40. With the right praise, Griffiths would manage to both foster motor skill development in his daughter and get some help in keeping the house clean, a double parenting win. Or was it? His daughter found the loophole in seconds. She looked up at us and smiled, he says, and then dumped the chips out of the pan, back onto the floor, and cleaned them up again to try and get more praise. For Griffiths, whose research bridges the gap between psychology and machine learning, the implication was obvious. It was exactly the kind of thing that makes me think about some of the challenges that you have in building reward-motivated AI systems. You have to think really carefully about how you design the reward function. Griffiths thinks about reinforcement learning all the time in the context of parenting. As a parent, you are designing the reward function for your kids, right? In terms of the things that you praise and the things that you give them certain kinds of feedback about. No one really thinks rigorously about what's the reward function that you explicitly want to design for your kids. Griffiths views parenthood as a kind of proof of concept for the alignment problem. The story of human civilization, he notes, has always been about how to instill values in strange, alien, human-level intelligences who will inevitably inherit the reins of society from us, namely, our kids. The parallel goes even deeper than that, though, and careful attention to both AI and parenting shows the surprising degree to which each can inform the other. Our children may be no more intelligent than we, but even young children can outsmart our rules and incentives, in part, because of how motivated they are to do so. In the case of reinforcement learning systems, they are slaves of a kind to their rewards, but they're the kinds of slaves that have an immense amount of computing power and a potentially inexhaustible number of trial and error attempts to find any and all possible loopholes to whatever incentives we design. Machine learning researchers have learned this lesson the hard way. And they have also learned a thing or two about how to deal with it. Cycle-proofing your rewards, the shaping theorem. Astroteller, currently the captain of moonshots at X, the alphabet company formerly known as Google X, has in recent years overseen everything from Google's self-driving car project, subsequently spun off into Waymo, to its augmented reality project Google Glass, and its research lab Google Brain. But in 1998, he was focused on a different problem, soccer. With his friend and fellow student David Andre, Teller worked to enter the annual RoboCup soccer competition with a virtual soccer playing program they dubbed Darwin United. 41 Reward shaping is part of what enabled them to teach the program how to play. But there was an issue. In soccer, possession of the ball is part of what good offense and good defense looks like, and is certainly better than wandering around the field aimlessly. And so Andre and Teller provided a reward, worth a tiny fraction of a goal, to their robot for taking possession of the ball. To their astonishment, they found their program vibrating next to the ball, racking up these points, and doing little else. 42 That same year, a team of Danish researchers at the Niels Bohr Institute in Copenhagen, Jette Randolph and Preben Alstom, were trying to get a reinforcement learning system to learn how to ride a simulated bicycle. The system would have to manage the complicated task of staying upright, while making progress toward a distant goal. This seemed like the perfect application for adding some shaping rewards. Because it would be unlikely that a system wobbling all over the place would randomly arrive at the goal, the team decided to add a small reward, a handful of points anytime the bicycle made progress toward the goal. To their astonishment, the agent drove in circles with a radius of 20 to 50 meters around the starting point. 43 They were rewarding progress toward the goal, but forgot to penalize movement away from the goal. Their system had found a loophole, and was ruthlessly, if dizzyingly, exploiting it. These heterogeneous reinforcement functions, they wrote, have to be designed with great care. These cautionary tales, in the late 1990s, were much on the minds of UC Berkeley's Stuart Russell and his then PhD student, and subsequently VP and chief scientist at Baidu, Andrew Ng. These sorts of exploitative loops seemed like a constant danger. 44 Ng was ambitious. He recalls, when I started working on robotics, I asked a lot of people, what's the hardest control problem you know of? And back then the most common answer I heard was getting a computer to fly a helicopter. And so I said, let's work on that. 45 Indeed, he would do his PhD thesis on using reinforcement learning to fly an actual, unsimulated, 9-foot-long, 100-pound, $70,000, Yamaha R50 helicopter. 46 The stakes were wildly high. Erratic or unpredictable behavior in the real world could destroy the helicopter entirely, to say nothing of what might happen if an unsuspecting person found themselves in its path. The critical question was this: given a difficult-to-learn reward function that described what they actually wanted the helicopter to do, what sorts of pseudo-reward incentives, if any, could they add such that the training process would be easier, but the best way to maximize that modified reward would also be the optimal solution to the real problem? To use Kerr's terms, what sorts of A's could they reward that would still result in the hoped-for B? In Ng's description, a very simple pattern of extra rewards often suffices to render straightforward an otherwise intractable problem. However, a difficulty with reward shaping is that by modifying the reward function, it is changing the original problem M to some new problem M, and asking our algorithms to solve M in the hope that solutions can be more easily or more quickly found there than in the original problem. But it is not always clear that solutions or policies found for the modified problem M will also be good for the original problem M. 47. What freedom do we have in specifying the reward function, Ng writes, such that the optimal policy remains unchanged? 48. As it turned out, the critical insight was hiding in the story of the bicycle. In order to prevent the bike from riding in circles, endlessly racking up rewards, you had to also subtract progress away from the goal. Russell, who had trained first as a physicist, made a connection between the rewards problem and conservation of energy. The key thing, Russell explains, is just making the shaping into what we call in physics a conservative field. 49 Pseudo-rewards were like potential energy, a function only of where you were, not what path you'd taken to get there. This also meant that returning to where you'd started, no matter what journey you'd been on, was net zero. This idea was intuitive enough in the bicycle problem. If you rewarded progress toward the goal, you necessarily needed to penalize progress away from the goal. Said another way, the incentive points should always reflect how close the bike was to the goal, and nothing about the route it had followed. But the concept of treating the incentives like potential energy turned out to be far deeper and more general. It was a necessary and sufficient condition for making sure that the agent you trained on the shaped reward didn't have its behavior come unglued from the real problem. As a general rule, says Russell, it is better to design performance measures according to what one actually wants in the environment, rather than according to how one thinks the agent should behave. 50 Put differently, the key insight is that we should strive to reward states of the world, not actions of our agent. These states typically represent progress toward the ultimate goal, whether that progress is represented in physical distance or in something more conceptual like completed subgoals, chapters of a book, say, or portions of a mechanical assembly. Though it isn't a magic bullet to all problems of human incentives, the shift in focus from actions to states does invite new ways of thinking about some of the incentive structures we, wittingly and unwittingly, design for others. Given a child who is dumping out the kitchen trash in order to double the rewards of sweeping it up, we can make our rewards into a conservative field by making sure we scold them in precisely equal measure for dumping the trash out, so that the net gain of further repetitions is zero. It might be easier, though, to shift to praising the state rather than the actions. Instead of rewarding the act of cleaning up itself, we might say, wow, look how clean that floor is. Of course, there is more to the art and science of rewards than the avoidance of cycles, though it's a start. Ng and Russell conclude their work on a cautious, rather than triumphant, note. We believe, they write, the task of finding good shaping functions will be a problem of increasing importance. 51. Evolution as reward. Designer. I said unto him, be fruitful and multiply. But not in those words. Woody Allen. 52. From a Darwinian perspective, what people want is reasonably clear, something along the lines of propagating and securing their genetic lineage. What people actually want, moment to moment, looks an awful lot more heterogeneous and short-sighted. Orgasms, chocolate, a new car, respect. It seems, then, that we are biologically wired and culturally induced to want specific, concrete things in the short term that generally steer our behavior in ways that are ultimately in line with these evolutionary goals, which would otherwise be too distant or ill-defined to consciously aim at. 53 Sound familiar? Understanding the nature and role of shaping, first in behavioral psychology, then in machine learning, hasn't just taught us how to design better agents. Perhaps its most surprising contribution is to the way we think about evolution. When Brown University's Michael Littman was a graduate student in the late 1980s, he was hired for a time at Belcour, a research and development group formerly part of AT&T, located in New Jersey. There he quickly found a mentor and a friend in Belcour's Dave Ackley. Littman asked him about working on the question of behavior, of taking actions and making decisions that ramify over time. As Littman recounts, he was like, "Oh, that's a thing. It's called reinforcement learning. I've looked at it a little bit. Here's a paper." And he gave me Rich Sutton's 1988 CD paper. 54 Littman began to read about temporal difference learning and was fascinated. He asked Ackley where he could learn more. And he's like, "Well, invite Rich to give a talk." And I was like, "What? That's a thing that you can do. You can read a paper and there's a person's name on it, and then you can turn them into a human being." I didn't think of it as a community, I thought of it as a literature. But no, it was a bunch of people, and they knew each other, and Dave was like, "I can invite him." And so he invited him. Sutton came to Belcour, and both Ackley and Littman caught the reinforcement learning bug. They were interested in the question of how evolution shapes our reward function to give rise to behaviors in the short term that are useful to the overall survival of an organism or a species in the long term. The organism's reward function itself, so long as it accomplishes this, might otherwise seem very random. Ackley and Littman wanted to see what might shake out if they simply let reward functions evolve and mutate and allowed simulated virtual entities to die or to reproduce. 55 They created a two-dimensional virtual world in which simulated organisms, or agents, could move around a landscape, eat, be preyed on, and reproduce. Each organism's genetic code contained the agent's reward function, how much it liked food, how much it disliked being near predators, and so forth. During its lifetime, it would use reinforcement learning to learn how to take actions to maximize these rewards. When an organism reproduced, its reward function would be passed on to its descendants, along with some random mutations. Ackley and Littman seeded an initial world population with a bunch of randomly generated agents. And then, says Littman, we just ran it for 7 million time steps, which was a lot at the time. The computers were slower then. What happens? As Littman summarizes, weird things happen. 56 At a high level, most of the successful individual agents' reward functions ended up being fairly comprehensible. Food was typically viewed as good. Predators were typically viewed as bad. But a closer look revealed some bizarre quirks. Some agents, for instance, learned only to approach food if it was north of them, for instance, but not if it was south of them. It didn't love food in all directions, says Littman. There were these weird holes in the reward function. And if we fixed those holes, then the agents became so good at eating that they ate themselves to death. The virtual landscape Ackley and Littman had built contained areas with trees, where the agents could hide to avoid predators. The agents learned to just generally enjoy hanging out around trees. The agents that gravitated toward trees ended up surviving, because when the predators showed up, they had a ready place to hide. However, there was a problem. Their hardwired reward system, honed by their evolution, told them that hanging out around trees was good. Gradually their learning process would learn that going toward trees would be good according to this reward system, and venturing far from trees would be bad. As they learned over their lifetimes to optimize their behavior for this, and got better and better at latching onto tree areas and never leaving, they reached a point of what Ackley dubbed tree senility. They never left the trees, ran out of food, and starved to death. However, because this tree senility always managed to set in after the agents had reached their reproductive age, it was never selected against by evolution, and huge societies of tree-loving agents flourished. For Littman, there was a deeper message than the strangeness and arbitrariness of evolution. It's an interesting case study of, sure, it has a reward function, but it's not the reward function in isolation that's meaningful. It's the interaction between the reward function and the behavior that it engenders. In particular, the tree senile agents were born with a reward function that was optimal for them, provided they weren't overly proficient at acting to maximize that reward. Once they grew more capable and more adept, they maxed out their reward function to their peril, and ultimately, their doom. One doesn't have to squint too hard to see a cautionary tale here for Homo sapiens. A heuristic like, always eat as much sugar and fat as you possibly can, is optimal as long as there isn't all that much sugar and fat in your environment and you aren't especially good at getting it. Once that dynamic changes, a reward function that served you and your ancestors for tens of thousands of years suddenly leads you off the rails. For Andrew Barto, there are clues in thinking about evolution that are useful for us as we now play the role of the reward designer. Evolution has provided our reward function, and so that is really quite important with regard to how we design reward functions for artificial systems, he says. That's what happened in nature. Evolution came up with these reward signals to encourage us to do things that led to our reproductive success. 57, as Barto notes. So, an interesting thing is that evolution didn't give us reproductive success as a reward signal. They gave us rewards for predictors. We optimize our behavior to maximize the things we find rewarding, but in the background and at a larger scale, evolution is shaping the things we find rewarding in the first place. So, it's a two-level optimization, says Barto. I'm very interested in that. In recent years, Barto has worked with the University of Michigan's Satinder Singh and Richard Lewis, and then PhD student Jonathan Sorg to investigate the question of the optimal reward problem. 58. If you have goal X, it might be that your best but isn't simply to tell your agent to do X. Should the artificial agent's goals be the same as the agent designer's goals? They write. This is a question seldom asked. 59. Consider a game, they say, in which all that exists is an agent, a fishing pole, some worms, and a pond full of fish. 60. Let's say the agent's overall evolutionary fitness is best served by eating as many calories as possible. Ideally, they would learn to pick up worms, refrain from eating them, and use them to catch fish, but this is rather complicated. A clever agent with a long lifespan is best served by a distaste for eating worms, so that they more quickly begin learning to fish. For an agent with a shorter attention span, on the other hand, or a shorter lifespan, trying to learn how to fish will be a fruitless waste of time, and so they are better served if they happen to find worms delicious. Perhaps most interesting is the case of an agent that is clever enough to learn to fish and will get to live just long enough to learn how, but not long enough to properly benefit from making that investment. They should be made allergic to fish, as it turns out, so that they have no choice but to eat worms. Subtle changes in the lifespan, or resources, or design of an agent can have wild and abrupt effects in the structure of the optimal reward. The answer as to what set of rewards will be ideal for a particular agent in a particular environment doesn't appear to admit to any easy generalizations. Research in this vein continues, but learning to more sharply distinguish between what you want and what you reward is an important component of the solution. Point 61. More recently, psychologists and cognitive scientists are taking these tools and turning them back around to ask a fascinating question, not about machines, but about humans. How should you design the best reward function, they ask, when the computationally limited, impatient, short-sighted agent learning to optimize it is yourself? How should we train ourselves? The theory and practice of reward shaping in machine learning not only gives us a way to make our autonomous helicopters maneuver appropriately, but contributes two distinct things to our understanding of human life and human intelligence. 1. It shows us a reason, sparsity, why some problems or tasks are more difficult than others to solve or accomplish. 2. It gives us a theory, incentivize the state, not the action, for how to make tough problems easier without introducing perverse incentives. The potential use for these insights in human life is enormous. The economic costs alone are vast. A recent report estimated the impact of British workers procrastinating on the job at £76 billion a year, to say nothing of the less easily calculated toll on our well-being and on the quality and fullness of our lives. Point 62. If we are living through a time of soaring video game addiction and real-world procrastination, maybe it's not the individual procrastinators' fault. As Skinner put it, I could have shouted at the subjects of my experiments, behave, damn you, behave as you ought. Eventually I realized that the subjects were always right. They always behaved as they ought. 63. If they weren't learning something, it was the fault of the experimenter not shaping their task properly. So maybe it's not a lack of willpower on our part, but rather that, as the best-selling 2011 book by Jane McGonigal put it, reality is broken. McGonigal, a game designer by trade, has spent her career designing games to help people, including herself, overcome challenges in their lives. For her, the incredibly addictive and compelling quality of most games, computer games in particular, is how clear they always make it what you need to do, and how achievable whatever that is always seems. The first thing is whenever you show up in one of these online games, there are lots and lots of different characters who are willing to trust you with a world-saving mission right away. But not just any mission, it's a mission that is perfectly matched with your current level in the game. Right? So you can do it. They never give you a challenge you can't achieve. But it is on the verge of what you're capable of, so you have to try hard. Point 64. In other words, what makes games so hyper-compelling is how well-shaped they are. The levels are a perfect curriculum. The points are perfect pseudo-rewards. They are Skinnerian masterpieces. Reinforcement learning not only gives us the vocabulary to understand and express what makes the game so riveting, it also gives us a way to empirically confirm those intuitions. A game with a clear curriculum from its easiest levels to its hardest, as well as clear pseudo-rewards that mark the path forward and foster exploration and the development of skills, should be easier for an algorithm to learn. It's not hard to imagine game studios in the coming years using automated test players for their levels, highlighting the sticking points where real human players are likely to give up or quit. The problem, of course, is that it is so much easier to shape these virtual environments than the real one. As McGonigal diagnoses, now, the problem with collaborative online environments like World of Warcraft is that it's so satisfying to be on the verge of an epic win all the time. We decide to spend all our time in these game worlds. It's just better than reality. For McGonigal, the solution isn't to wean ourselves off of these perfectly reward-shaped environments, but the reverse. We have to start making the real world work more like a game. McGonigal herself has led something of a movement in this regard, including using games to overcome obstacles, including suicidal depression from a protracted recovery from concussion. In her own life. Point 65, I said to myself after 34 days of depression, and I will never forget this moment. I said, I'm either going to kill myself, or I'm going to turn this into a game. 66, so she created pseudo-rewards. Calling her sister was worth a few points. Walking around the block was worth a few points. It was a start. This is a field known as gamification. 67, and in the last 10 years, thanks to insights from reinforcement learning, it has gone from something of an art to something of a science. Point 68. One of the people who has thought harder about this problem than anyone in the world, both in his research and his personal life, is cognitive scientist Falk, leader of the Max Planck Institute for Intelligent Systems. Leader's research focuses on what he calls rationality enhancement. He studies the cognitive science of how people think and make decisions, and unlike most researchers, he has a keen interest in not only understanding human cognition, but in devising effective tools and interventions to make humans think better. His earliest human subject was, of course, himself. Growing up, Leader found it frustrating that his schooling, though it gave him plenty to think about, never touched on thinking itself. I always felt that what I really wanted to learn was to think well, and how to make good decisions, he explains. Nobody could teach me that. They could just teach me declarative facts about the world, and it wasn't very useful. I really wanted to learn how to think. 69. Over time, this matured into a quest for personal betterment, but also something bigger, the drive to understand the principles of human reasoning and make tools for improving it. Part of my research, he explains, is discovering these optimal strategies for thinking and decision making so that we can actually build a scientifically based curriculum for good thinking. Leader is interested in gamification and more specifically, what he calls optimal gamification. Given a goal, what is the best possible incentive structure to facilitate reaching it? 70. This has much of the flavor of optimal reward design, as discussed above, but in this case the agents being designed for humans rather than algorithms. Leader, working with Tom Griffiths, established some ground rules for what optimal gamification would look like. They knew from Andrew Ng and Stuart Russell's work that one of the cardinal rules is to reward states, not actions. Therefore the points assigned to taking an action must reflect how much better the resulting state of affairs is, and what's more, as leader notes, the points have to be assigned in such a way that when you undo something, you lose as many points as you earned when you did it. This is what Randolph and Alstom learned the hard way with their bicycling robot, what David Andre and Astro Teller learned the hard way with their vibrating soccer robot, and what Tom Griffiths himself learned the hard way when his daughter dumped the dustpan onto the kitchen floor. Ing and Russell's paper had suggested that shaping rewards could enable an agent with a limited ability to look ahead and forecast the effects of its actions to behave as if it was more farsighted than it really was. Point 71. This idea intrigued Leader, in part because humans are so notoriously impulsive and short-term focused in many of their decisions. He and Griffiths ran an experiment where they put human subjects in the role of an airline route planner. Flying to certain cities was profitable for that leg, but might put the plane in a position where few other profitable routes existed, and the reverse was true, too. It might be worth flying one leg at a loss in order to reap rewards elsewhere. They tried adding additional immediate rewards, or penalties, to the sticker price of a given leg from A to B that would reflect the downstream cost, or benefits of moving the plane to that location. As expected, this enabled people to more readily make better and more profitable decisions. There was only one downside: incorporated the long-term costs and benefits of a choice into the sticker price. Users no longer needed to think ahead. This made their decisions more accurate, but was somewhat enfeebling. People no longer needed to think very hard, and so they didn't. If you are to act in an environment where myopic decision-making works, says Leader, people will learn to rely on that system more and more. 72. This left open an intriguing possibility. Could use optimal gamification, not to obviate the need for planning, but to make people better at it. The incentives in this case are almost completely different. Instead of the interface creating an easy problem where long-term costs are taken into account, causing higher quality decisions, but perhaps encouraging lethargy or complacency in subjects, making them more dependent on the interface, prices could be adjusted to create a curriculum. The subject could be slowly taught how to think ahead, starting with very simple illustrations of the basic idea, and slowly building in complexity as the subject got better at it. The interface, instead of functioning as a crutch, could use a different set of incentives to do the opposite, teaching people to plan further ahead in time, Leader explains, so they can succeed in environments where immediate reward is misaligned with long-term value. Leader's final experiment was not with flight planning, but with a more familiar setting, procrastination. He and Griffiths created a deliberately onerous task, to write essays on a series of 5 topics, some of them longer and more difficult than others, and put it on Mechanical Turk, where people would elect to work on it for a payment, $20, upon completion of all the pieces of writing by a deadline set for 10 days later. Of everyone who signed up, 40% never even started. This was particularly ironic, because when the task was initially described to them, they had a chance to decline to participate, and still receive 15 cents. 73. Leader and Griffiths also experimented with incentives that gave subjects points, which had no cash value but were visually encouraging. For each essay completed, each essay was worth the same number of points. It didn't help. Lastly, they offered a third group of participants optimal incentives, point values that precisely reflected how difficult or unpleasant each topic was and how much closer they would be to earning their $20 when they had finished it. 100 words on North Korea's economic policy, for instance, was worth about 3 times as many points as 50 words on their favorite TV show. Here, a full 85% of participants finished all 5 essays. Point 74. Leader thinks of systems like these as cognitive prostheses, 75, and they are more than just his research interest. They are a crucial part of how his own research even gets done. As a PhD student, Leader found himself in a scaled-up version of the horrible essay writing task. I think one of the worst situations is to get no information about your level of progress, he says. The official system is, you are a PhD student, and then you have a PhD, and that's it. So, 5 years of no feedback. PhD students in general are a group with high rates of anxiety and depression, and for whom procrastination is nearly an epidemic. Point 76. They are, in effect, pigeons in Skinner's bowling alley, the cap and gown-shaped food pellet waiting for them after they bowl a perfect strike some 5 years hence. Such a system, we know, doesn't work for animals, and it doesn't work for reinforcement learning algorithms, either. That wouldn't do. Leader needed something else. He charted his 5-year course. I broke this down into a few hundred levels. He assigned himself virtual citations, when he did work he felt might result in real citations some several years hence. He used the same optimal gamification calculation that assigned his subjects' essays a point value to compute the proper point values for each subtask of his doctorate. He even used punishment to override some of his habits, in the form of a wristband from the company Pavlok. It gives you electric shocks whenever you indulge in some habit that you don't want to indulge in, Leader explains. My main bad habits were related to how I use my computer. Like, I'm going to YouTube when I feel bad. Since my time tracking software would immediately communicate to my Pavlok what I was doing, it could then immediately shock me. Amusingly, this failed to curb his habit of visiting YouTube when he needed some distraction, but it did instill the habit of instantly closing the page when he did. Being, in effect, both the experimenter and the subject in his own behavioral training experiment gave Leader a unique vantage onto the question of reward shaping. Such training was, at once, the process by which he approached his research, and the central question of that research. The results are encouraging, and Leader, now running his own research laboratory, has the doctoral robes to prove it. Beyond extrinsic reinforcement. For Skinner, not only was individual free will left uncomfortably in the position of a fiction, but essentially the entire story of human civilization was the story of reward structures. Skinner himself was curiously upbeat about this, writing the utopian novel Walden 2 about a perfect behaviorist society. And yet anyone who's been around children, or animals, might have the nagging suspicion that reward maximization really isn't the whole story of why we do what we do. We play games of our own invention, for no discernible prize. We turn over rocks, or climb mountains, just to see what we might discover. We explore. We are playful and curious. We are, in short, motivated as much by internal as by external rewards. As it happens, this, too, is becoming ever more well appreciated in the world of machine learning. 6. Curiosity. If the untrained infant's mind is to become an intelligent one, it must acquire both discipline and initiative. So far we have been considering only discipline. Alan Turing 1. In the spring of 2008, graduate student Mark Belmer was walking on the beach in Barbados with University of Alberta computer scientist Michael Bowling. Bowling had an idea. At that time, reinforcement learning research was typically done with each researcher making their own bespoke game from scratch, then hand-tailoring a system to succeed at that particular game point. What if instead, Bowling mused, someone built a single environment that everyone could use, with not just one game in it, but a vast library of them, and what if, instead of fake, made-up games, it used real games, namely, classic 1970s and 80s video games from the Atari 2600. Belmer recalls, I said, this is the stupidest idea I've ever heard. 3. He continues, fast forward about 3 years, and well, I decided it wasn't such a stupid idea. In fact, Belmer found he liked the idea so much that Bowling became his doctoral advisor, and the idea became his dissertation. The ambition of the project was somewhat insane, not only in the amount of work it would require to build this video game bestiary, which they dubbed the Arcade Learning Environment, ALE, but also in the implicit gauntlet that it threw down to the rest of the field. Point for the idea was for researchers to compete against one another by fielding a single learning system that could play not just one, but all 60 of the games. The field wasn't anywhere close. A big part of the problem was that the bespoke game environments, then being used, often described the world to the agent in terms that were sanitized and filtered, using inputs that were high-level and useful. In the case of the wheeled cart trying to balance a pole, the system would be given as input the location of the cart, its velocity, the current angle of tilt of the pole's velocity, and so forth. In the case of the two-dimensional grid world environment with trees, food, and predators, the system would be told the agent's location, its health and hunger, whether there was a predator nearby, where the nearest food was, and so forth. These pieces of information are known as features. What the ALE offered, by contrast, was something more overwhelming and less immediately usable, the pixels on the screen. That was it. Every game was different, not only in its rules, but in the way the pixels on the screen mapped to usable information. A learning system thrown into a new game was going to have to figure out everything from scratch. These pixels over here appear to blink when I score points. Those pixels over there appear shortly before I die. These pixels in the middle move left whenever I hit the left arrow button. Oh, maybe they're me. Either researchers were going to have to find extremely general ways of extracting useful patterns on the screen for their system to keep track of, such that they were helpful in all 60 games, or else all of that understanding and meaning making was going to have to be done by the system on the fly. This was the problem of feature construction. Belmer began experimenting by plugging a bunch of feature construction algorithms into standard reinforcement learning systems and throwing them at the games. The results weren't impressive. To his surprise, however, it was easy to get them published, if only because his peer reviewers were so impressed by how much work had gone into making the Atari environment. The funny thing is, he says, at the time the reviewers would tell me, well, you've done this amazing thing with Atari. I cannot possibly reject your paper. It was so big, it didn't matter how bad or good the results were. People just said, wow. You've actually done this. He and his colleagues had built, in effect, a kind of mountain. It was now up to the field to figure out a way to scale it. Belmer finished his PhD in 2013 and moved from Edmonton to London to join DeepMind. 5 there. A team led by Volodymyr Menai was working excitedly on the idea of taking the same AlexNet-style deep neural networks that had been so decisive in the ImageNet competition the year before and applying them to the problem of reinforcement learning. If deep networks could look at tens of thousands of raw pixels and figure out whether they were a bagel, a banjo, or a butterfly, maybe they could do whatever feature construction was needed to render an Atari screen intelligible. He recalls, the group said, hey, we have these convolutional networks. They've been phenomenal at doing image classification. What if we replace your feature construction mechanism, which is still a bit of a kludge, by just a convolutional neural network? Belmer, again, wasn't buying it. I was actually a disbeliever for a very long time. The idea of doing perceptual IL was very, very strange. And, you know, there was a healthy dose of skepticism as to what you could do with neural networks. But on this matter, too, Belmer would soon come around. Simply plugging deep learning into a classic IL algorithm and running it on 7 of the Atari games, Menai was able to beat every previous IL benchmark in 6 of them. Not only that, in 3 of the games, their program appeared to be as good as a human player. They submitted a workshop paper in late 2013, marking their progress. 6. It was just sort of a proof of concept paper, says Belmer, that convolutional nets could do this. Really, he says, it was bringing the deep learning part to solve what reinforcement learning researchers hadn't been able to do in ages, which is to generate these features on the fly. Then you can do it for any game, it doesn't matter. And then this. Belmer pauses slightly. This took off. Deep IL gets superhuman. In February 2015, a paper appeared on the cover of Nature, running with the headline, Learning Curve. Self-taught AI software attains human performance in video games. 7 DeepMind's hybrid of classic reinforcement learning with neural networks had shown itself capable of human-level play, and far beyond, at not just a couple Atari games, but dozens of them. The deep learning revolution had come to reinforcement learning, minting the new field of deep IL, and the results were astonishing. The model, called a Deep Q network, or DQN for short, was playing video pinball and achieving scores at 25 times the level of a professional human games tester. In boxing it was 17 times better than human performance. In Breakout, it was 13 times better. A nearly full-page chart chronicled this stunning pattern of dominance across a wide array of different games, all using a single generic model, with no fine-tuning or adjustment from one game to the next. At the bottom of the chart, however, there were a few stubborn games that refused to yield to DQN, games that didn't fit this pattern of glory. One in particular, at the very bottom of the list, stood out. The outlier was Montezuma's Revenge, a 1984 game in which you play an explorer named Panama Joe who must find his way through a temple filled with ropes, ladders, and deadly, very vaguely Aztec traps. I did no research whatsoever into Montezuma or the culture, admits creator Robert Yeager, just 16 years old when he sold his demo to Parker Brothers, and really just thought it was a colorful theme and a cool name. 8 on Montezuma's Revenge, the mighty DQN achieved a high score of 0%, yes, that's 0%, of the human benchmark. What was going on here? For one thing, the game makes it extremely easy to die. Almost any sort of mistake, hitting an enemy, jumping down from too high up, walking through a barrier, is certain death. The DQN system used epsilon greedy exploration, which involves learning about which actions produce reward by simply hitting buttons at random a certain fraction of the time. In Montezuma's Revenge, this is almost always suicide. The second and more important problem is that Montezuma's Revenge has incredibly sparse rewards. It takes a huge number of things to go exactly right before the player gets any points at all. In games like Breakout or Space Invaders, even the most confused and bewildered newcomer, jamming buttons at random, quickly realizes that they are at least doing something right. This is enough to start the learning process, in DQN's case, registering the points scored and slowly beginning to take similar actions in similar situations more of the time. In Montezuma's Revenge, by contrast, very few events offer any kind of feedback other than death. On the first screen, for example, you have 4 chasms to leap, 3 ladders to climb, a conveyor belt to run against, a rope to grab, and a rolling skull to hop over, all before you can collect the first item, which rewards you with 100 measly points, and anachronistic, the first 5 notes of La Cucaracha. In an environment with so few rewards, a randomly exploring algorithm can't get a toehold. It's incredibly unlikely that by essentially wiggling the joystick and mashing buttons, it will manage to do all of the necessary steps to get that first reward. Until it does, it has no idea that it's even on the right track. 91 solution to this problem of sparsity, as we've seen, is shaping additional incentive rewards to nudge the algorithm in the right direction. But we've also seen how tricky this can be to do correctly without creating a loophole that the algorithm can exploit. Rewarding Panama Joe for every second he doesn't die, for instance, might just lead to an agent learning never to leave the safety of the initial platform at all. It would be a machine version of what animal researchers call learned helplessness. 10 as the celebrated aphorist Ashley Brilliant put it, if you're careful enough, nothing bad or good will ever happen to you. 11 other intuitive ideas run aground as well. Rewarding Panama Joe for successfully jumping over a rolling skull, let's say, might lead the agent to play a kind of double dutch over the skull instead of venturing farther into the temple. Rewarding him for successfully jumping onto or off a rope would, similarly, incentivize an infinite loop of Tarzan-like swinging. None of this is what we want. Moreover, though, this kind of shaping will typically vary from game to game, and require the hand of a human overseer with inside knowledge of how that particular game works. That feels a bit like cheating. The whole idea behind the arcade learning environment, and the thrilling achievement of DQN, was that of a single algorithm, able to master dozens of completely different game environments from scratch, guided by nothing but the image on the screen and the in-game score. So what was the answer? How might a generic trial-and-error algorithm, like DQN, be modified in the face of such a foreboding game as Montezuma's Revenge? There was a tantalizing clue, hiding in plain sight. Humans clearly can learn how to play Montezuma's Revenge without any additional shaping. Rewards. Human players instinctively want to climb the ladder, reach the distant platform, get to that second screen. We want to know what's on the other side of the locked door, to see how big the temple really is and what, if anything, lies beyond. Not because we intuit that it will bring us points, but out of something more pure and more fundamental, because we simply want to know what will happen. Perhaps, then, what was needed to conquer a game like Montezuma's Revenge was not augmenting the game's sparse rewards with additional incentives, but rather a different approach altogether. Maybe, instead of an ever more elaborate system of carrots and sticks, the answer was the opposite, to develop an agent that was intrinsically rather than extrinsically motivated. 12 An agent that would essentially cross the road, not because there was reward in it, but just to get to the other side. An agent that was, we might say, curious. The last several years have seen a grand revival of scientific interest in the topic of curiosity, and some unlikely collaborations between machine learning researchers and psychologists who specialize in the cognition of children to better understand curiosity from a rigorous, fundamental perspective. What is it, exactly? Why do we have it? How might we instill it, not just in our children, but in our machines? And why might it be increasingly critical that we do? Curiosity as a scientific subject. Desire to know why and how. Curiosity is a lust of the mind that by a perseverance of delight in the continual and indefatigable generation of knowledge exceedeth the short vehemence of any carnal pleasure. Thomas Hobbes 13. Curiosity is the beginning of all science. Herbert Simon 14. The godfather of curiosity research in psychology is the psychologist Daniel Belyne. Belyne's very first publication, in 1949, was an attempt to define what exactly we mean when we say that something is interesting, or that a person or animal is interested in something. 15, as he put it. My first interest is interest. 16 A whole subfield gradually began to open up. What did animals learn without any rewards hinging on their learning it? As Belyne noted, the history of psychology is largely a story of people and animals being compelled to do things, to fill out a survey, or answer oral questions, to press levers in order to eat. In this way, however, the field had essentially created its own methodological blind spot. How would it even begin to approach the question of how organisms act on their own? It seemed almost a contradiction in terms. It has, in some ways, been a misfortune for psychology that human beings are so obliging and compliant, he wrote. 17 The ease with which artificial and extraneous motivations can be induced in human beings has prevented us from studying the motivational factors that take control when these are lacking. Within psychology, the research agenda of training animals with punishments and rewards was so dominant by the mid-20th century that it seemed for a time that this could explain everything about the behavior of intelligent organisms. But there were certain data, here and there, that refused to fit. The University of Wisconsin's Harry Harlow had, by 1950, begun documenting the way rhesus monkeys would play with physical puzzles made from a combination of locks and latches, and he coined the term intrinsic motivation to describe it. 18 Sometimes this intrinsic motivation not only took hold in the absence of extrinsic rewards, but actually overpowered them. A hungry rat might, amazingly, decide to forego a bit of food, or cross an electrified fence, to explore an unfamiliar space. Monkeys were willing to press levers not just for cookies and juice, but simply to look out a window. 19 There was little room in the strict Skinnerian world of extrinsic rewards and punishments for such behaviors, and there was no easy story to explain them. And yet this intrinsic motivation, as Berline saw, was every bit as central to human nature as the drives for, say, food and sex, despite being unduly neglected by psychology for many years. 20 Indeed, the severest punishment our society allows, short of death, solitary confinement, is, in effect, the infliction of boredom on people. In his landmark 1960 book Conflict, Arousal, and Curiosity, Berline notes that a proper study of curiosity first began to emerge in the late 1940s. It is no coincidence, he argues, that information theory and neuroscience also came into their own at the same time. 21 A proper understanding of curiosity appears only to be possible at the interdisciplinary junction of all three. 22 Berline appeared to be just as strongly motivated by curiosity in his own life as he was motivated by it as a subject of study. He knew at least 10 languages, and was fluent in 6 or 7 of them, and was an accomplished pianist, as well as a jogger and traveler. At the time of his early death at 52, he was on a quest to ride every subway in the world. Despite a prodigious and prolific output of articles and papers, he rarely worked on nights or weekends. There was too much else to do. 23 His ideas, in particular the agenda of reaching out to both neuroscience and information theory for clues, would inspire succeeding generations of psychologists for the latter half of the 20th century, and in the 21st they would come full circle. Starting at the end of the 2000s and continuing through the deep learning boom of the 2010s, it was the mathematicians and information theorists and computer scientists, stuck on the problem of intrinsic motivation in cases like Montezuma's Revenge, who would be turning to his ideas for help. At a broad level, he argued, humans' intrinsic motivation seemed to entail 3 related but distinct drives: for novelty, for surprise, and for mastery. Each of these, in turn, has offered tantalizing ideas about motivation and learning that seem just as applicable, in this decade, to machines as to ourselves. Novelty. The question that researchers have usually been designed to answer is, what response will this animal make to this stimulus? As soon as the experimental situation is made more complex, a new question arises: to which stimulus will this animal respond? Daniel Berline 24 When I'm caught between 2 evils, I generally like to take the one I've never tried. Mae West 25 One of the concepts at the heart of human curiosity, of our intrinsic motivation, is novelty. In the absence of strong compelling incentives, we don't act randomly, as simple reinforcement learners using epsilon greedy exploration do. Rather, we are quite robustly, reliably, and predictably drawn toward new things. In the mid-1960s, Robert Vance of Case Western noticed that human infants as young as 2 months old would reliably spend less time looking at magazine pictures if they'd already been shown those pictures before. 26 What Vance came to appreciate was that long before infants have the motor skills to explore the world physically, they are still capable of exploring the world visually, and are very clearly drawn to do so. This behavior, known as preferential looking, has become a cornerstone result in developmental psychology, one of the most striking characteristics of infant behavior. Infants' preference for looking at new things is so strong, in fact, that psychologists began to realize that they could use it as a test of infants' visual discrimination, and even their memory. 27 Could an infant tell the difference between 2 similar images? Between 2 similar shades of the same color? Could an infant recall having seen something an hour, a day, a week ago? The inbuilt attraction to novel images held the answer. If the infant's gaze lingered, it suggested that the infant could tell that a similar image was nonetheless different in some way. If the infant, after a week without seeing an image, didn't look at it much when it was shown again, the infant must be able at some level to remember having seen it the week before. In most cases, the results revealed that infants were more cognitively capable earlier than had been previously assumed. The visual novelty drive became, indeed, one of the most powerful tools in psychologists' toolkit, unlocking a host of deeper insights into the capacities of the infant mind. 28 It didn't take long for the reinforcement learning community to latch onto this idea of an intrinsic novelty preference, and to see what could be done with it in the computational domain. 29 One of the most straightforward ideas would be simply to count how many times a learning agent has been in a particular situation before, and then to have it prefer, all things being equal, to do the thing it had done the fewest times before. Richard Sutton, for instance, in 1990 suggested adding such an exploration bonus to the agent's reward if it took an action it had never taken before, or one it had not tried in a long time. 30 There is a quite obvious fly in the ointment here, however. What does it mean to count the number of times we took this action in this situation? As Berline put it in 1960, the word new is used commonly in everyday speech, and most people seem to understand it without much difficulty. But when we ask what exactly it means to say that a stimulus pattern is novel and how novel it is, we face a whole succession of snares and dilemmas. 31 For simple environments, like solving a maze, or for very, very simple games, it is of course possible to simply keep a list of every single situation you encounter, and add a tally mark each time you return. Tracing a path through a maze in pencil essentially keeps this record on the maze itself. This approach, keeping a giant table of every situation you've been in, what you did, and what happened, is known as tabular RL, and unfortunately it's known for being totally infeasible in anything but a very small environment. Tic-tac-toe, for instance, is about as simple as a board game gets, and yet it has thousands of unique board positions. 32 The total count of possible positions in the game of Go is a 170-digit number. All the computer memory in the world put together wouldn't come close to storing that table. Beyond these pragmatic issues, however, the deeper and more philosophical question, in more complex environments, is what it means to be in the same situation in the first place. In an Atari game, for instance, there are so many different ways that the pixels can appear that dutifully keeping track of every single screen you've ever momentarily encountered and slightly favoring novel ones is simply not helpful for generating interesting behavior. For games of reasonable complexity, you may be unlikely to ever see exactly the same set of pixels more than once. From that perspective, almost every situation is novel, almost every action untried. Even if you could store such a table, it wouldn't be much of a guide. When in the course of everyday human decision-making, someone says to us that they've never been in that situation before, we don't normally take them to mean at this exact latitude and longitude at this exact nanosecond with this exact sun-dappled pattern hitting my retina and this exact sequence of thoughts in my mind, or else the statement would be effectively true by definition and robbed of all meaning. What we mean to refer to are the sometimes ineffable key features of the situation, and we judge its novelty by those. In an Atari game, what we'd want would be some way to gauge whether the situation we are in, as represented by the pixels on the screen, was meaningfully similar to one we'd been in before. We'd want to be able to make connections across situations that share some deeper, non-trivial similarity. At DeepMind in London, Mark Belmer was interested in thinking about how this venerated but impractical idea of counting how many times you'd seen something before, known, appropriately, as the count-based approach, could be extended to more complex settings. In an Atari game like Frogger or Freeway, where you're trying to cross a busy road, ideally each time you successfully cross, it should increment a kind of count of how many times you've done so, even if the traffic itself was always in some new, random pattern at the time. Belmer and his colleagues were playing around with a mathematical idea called density models, and it seemed to show some promise. Point 33. The basic idea was to use unsupervised learning to make a model that could predict missing parts of an image from the surrounding context. This is not unlike Word2Vec and similar language models, designed to predict missing words in a passage of text. They could feed this density model all of the screenshots that the agent had seen thus far, and then use its predictions to assign a numerical probability score representing how predictable a new screen was, given what it had seen already. The higher the probability, the more familiar; the lower the probability, the more novel. It was an intriguing idea, but it was an open question how something like this might actually work in practice. They began to do some experiments with an early 1980s Atari game called Q*Bert, in which you hop around a pyramid made of square tiles, turning each of them to a different color until you've gotten them all, before moving on to a brand new, differently colored stage where you do the same. They had a randomly initialized, blank slate DQN agent play Q*Bert from scratch, while they watched a meter on the left-hand side of the screen that gauged the novelty as measured by the density model of what the agent was seeing and experiencing. At first, just as it is with us, everything was new. The meter was pegged at the maximum value. Every image on the screen registered as almost totally novel. They trained the agent for several hours, allowing it to gradually get more adept at earning points, in the case of Q*Bert, 25 points for every tile it flipped. They checked back in and watched it play. The now somewhat experienced agent hops around, picking up points. The green bar of the novelty meter, technically the inverse log probability, barely flickers up from the bottom. The agent has seen it all before. Belmer found the training run, in which the agent managed to complete the game's first level for the very first time. He watched it in replay, wondering what would happen. Satisfyingly, as the agent begins to get close, that green bar starts creeping up again. Now, says Belmer, as the agent is getting towards the end of the level, it starts to say, hey, these situations are novel. I haven't really been in this state before. This seems very new to me. And you have this very nice progression, as we're getting closer and closer to finishing the game, this signal is going up. 34. The agent hops down to the final tile, completing the level for the very first time. Suddenly, the whole screen flashes and strobes. The board resets to the next stage, with the pyramid of cyan tiles gone, and a totally new pyramid, this one bright orange, in its place. And look at this. Belmer says. The green bar shoots all the way up. The novelty signal is practically off the charts. Immediately the agent knows, I have never been here before. This density model was capturing, or so it seemed, a faithful notion of novelty in diverse, highly complex environments that were too big and too rich to actually count directly. We looked at these results and we thought, there has to be something we can do with this. Now the question was, could they use this model? They would dub it the pseudocount to motivate an agent to seek these novel states. 35. What would happen if you actually rewarded the agent, not just for scoring points, but simply for seeing something new? And would that, in turn, make for better agents, able to make faster progress than those trained only to maximize reward and occasionally mash buttons at random? It was clear what the payoff would be if they succeeded. We got really excited, he says, about trying to crack Montezuma's revenge. The temple in which Panama Joe finds himself trapped has 24 chambers. After the equivalent of playing the game day and night, without sleeping, for 3 weeks, the DQN agent that had shown itself capable of superhuman performance at dozens of other Atari titles had only made it to the second room, barely out of the starting blocks. There was a whole temple out there to explore, full of dangers and bereft of points. Maybe an agent directly rewarded for seeing things it had never seen before was just the kind of agent likely to get somewhere no agent had ever been. Belmer and his group wagered that an agent given access to these novelty signals, if it treated them as supplementary rewards to the in-game points, would be far more motivated and more successful at playing the game. They tried it, and let it train for an equal amount of time as the original DQN agent, 100 million frames, or nearly 3 weeks of 24/7 play. The difference was shocking. The same DQN agent, trained with novelty-based rewards, was dramatically faster at getting the first key, and ultimately made it through not 2, but 15 of the temple's chambers. Not only is the novelty-driven agent getting more points, it appears also to be exhibiting a different kind of behavior, a qualitative, as well as quantitative difference. All that, preferential looking, can be harnessed to make it succeed in exploring terrain where rewards alone aren't enough. And something about the novelty-driven agent just seems more relatable, more human, even. It is no mere joystick wiggler when rewards are scarce. It has a drive. Immediately, Belmer says, the pseudo-count agent goes out and explores this world. The pleasure of surprise. The mechanism of epistemic curiosity works through the equivalent of conceptual conflict, and its function is an eminently motivational one. Daniel Beline, 36. It is not that children are little scientists, but that scientists are big children. Alison Gopnik, 37. The other high-level concept integral to curiosity, along with novelty, is surprise. 38. A curious child cares not only that things are at some level new, but also that things have something to teach them. A baseball with purple polka dots on it, let's say, is intriguing for a moment, but if it otherwise behaves exactly like a standard baseball, the intrigue will be short-lived. Rather, we maintain our interest in things that seem to defy our expectations, that behave unpredictably, that dare us to try to understand what will happen next. One of the researchers on the forefront of understanding the role of surprise in human curiosity is MIT's Laura Schultz. In a 2007 study, she had children play with a kind of jack-in-the-box toy, where levers would raise various puppets up through the lid of the box. 39 The researchers would briefly take the toy away, and then return with both the familiar box and a new, differently colored box. They would set them both in front of the child and walk away, waiting to see which one the child reached for. Now, everything we've known before about play and curiosity in children, Schultz explains, says, well, if 4-year-olds have been playing with one box for a while, then if you bring out a new box, they should go right for the new box. They should go immediately to play with the new box, because the basic idea about curiosity would be it's about perceptual novelty, perceptual salience. This is something they haven't seen. 40 But there was more to it than that, Schultz found. In some trials, the demonstration of the first box was made deliberately ambiguous. The box had 2 levers, and if they were pressed simultaneously, 2 different puppets would just as simultaneously rise up out of the lid. It wasn't clear what raising one of those levers alone, or the other, would do. Was one of the levers responsible for both puppets and the other ineffectual? Was each lever responsible for the puppet closest to it? Or the one on the opposite side? In these ambiguous cases, the 4-year-olds didn't immediately switch from the familiar toy to a novel one when given the chance. Instead, they persevered, reaching back for the 2-lever box in order to figure out exactly how it worked. We often seem to be curious, says Schultz, about things that aren't particularly novel. They just puzzle us. 41 So a picture began to emerge that surprise, uncertainty, the ability to resolve ambiguity, to gain information, was every bit a driver of children's intrinsic motivation as novelty. This idea has led to a second vein of research, every bit as rich, spanning both cognition and computing. Schultz, working with Rutgers psychologist Elizabeth Bonowitz and a group of collaborators, did a further study using weighted blocks. Prior research had shown that around age 6, children begin to have theories about how best to balance blocks of different sizes and shapes. Some children at that age assume, incorrectly, that blocks can always be balanced halfway between their 2 ends, even if the object is asymmetrical, while others theorize, correctly, that blocks are balanced at their center of mass, at a point closer to whichever is the thicker side. This led the researchers to use magnets to create blocks that could be made, ingeniously, to violate the assumptions of either group. When children played with blocks that behaved as they expected, their standard novelty bias crept in and led them to abandon the blocks in favor of another, newer toy when offered the chance. But the children for whom the blocks appeared to violate their theory of how blocks should balance, regardless of whether their theory was actually correct, stayed riveted and continued playing with them, even when another toy was on offer. 42 4 and 5-year-olds, who tended to lack a concrete theory about how best to balance the blocks whatsoever, almost invariably preferred a new toy when it was available. No matter what the block's behavior, it seemed the younger children didn't know enough, or have strong enough beliefs or predictions, to be surprised. Other research following in this vein, for instance, a 2015 study by Amy Stahl and Lisa Fagenson of Johns Hopkins, has shown further that the way infants play with a toy is also related to the way in which a toy is surprising. 43 If a toy car is shown appearing to mysteriously float in midair, infants will play with it by lifting it up and dropping it. If, however, the car is shown appearing to mysteriously pass through a solid wall, the infant will play with it by banging it on the table. And in each case, the infant will choose to stay engaged with the surprising toy when offered a chance to try a new one. A control group who doesn't get to see the toy defy their expectations reliably prefers the new toy. Already by the age of 11 months, say Stahl and Fagenson, infants use violations of prior expectations as special opportunities for learning. It's easy to look at a baby and see a blank slate, says Fagenson. But actually, babies have rich, sophisticated expectations about the world, maybe more than people give them credit for. Babies, she argues, use what they already know about the world to motivate, or drive further learning, to figure out what they should learn more about. 44 This idea, in computational terms, of an agent motivated not only by rewards, but by trying to understand and predict the environment, is as old as reinforcement learning itself. And it has just as suddenly sprung into fruition. Daniel Bernstein had seen some of the earliest experiments with machine learning in the 1950s, and mused about the use of surprise, or misprediction, as a reinforcer. Further research may well be aimed at devising a problem-solving machine that will improve its technique in the light of its experience, he wrote. The reduction of mismatch, or conflict, would then have to be the reinforcing agent, causing the immediately preceding operations to move up in the machine's order of precedence. 45 German AI researcher Jürgen Schmidt-Huber has since 1990 been exploring the idea of agents that get reward from learning how their environment works. That is, from improving their ability to make predictions. They may be viewed as simple artificial scientists, or artists, he explains, with an intrinsic desire to build a better model of the world and of what can be done with it. 46 For Schmidt-Huber, just as it was for Bernstein in the 60s, this idea of learning has its mathematical roots in information theory and, to Schmidt-Huber's mind in particular, the notion of data compression, that a more readily understood world is more concisely compressible. In fact, for Schmidt-Huber the idea that we go through the world striving to better compress our representation of the world offers a formal theory of creativity and fun. He explains, you just need to have a computational resource, and before learning a pattern, you need so many computational resources, and afterwards you need less. And the difference, that's where you're saving. And your lazy brain likes to save things. And, he snaps his fingers. That's the fun. 47 Like Bernstein, Schmidt-Huber is fascinated not by what people do in order to solve problems posed to them directly, how to win a game, or escape a maze, for instance, but rather, what people do specifically in those times when there isn't anything explicit to do. Infants, he thinks, are the perfect examples of this. Even when there is no immediate need to satisfy thirst or other built-in primitive drives, the baby does not run idle. Instead, it actively conducts experiments. What sensory feedback do I get if I move my eyes, or my fingers, or my tongue just like that? 48. As Schmidhuber notes, there is a fundamental tension at the heart of curiosity, almost a tug-of-war, as we explore an environment and our available behaviors within it, whether that's the microcosm of an Atari game, the real-world great outdoors, or the nuances of human society. We simultaneously delight in the things that surprise us while at the same time we become harder and harder to surprise. It's almost as if the mind comprises two different learning systems, set at cross purposes to each other. One does its best not to be surprised. The other does its best to surprise it. 49. Why not, then, attempt to model this tension directly? A group from UC Berkeley, led by PhD student Deepak Pathak, set out in 2017 to build just such an agent. Pathak created an agent composed of two different modules, one designed to predict the outcome of a given action, rewarded when the reality matches its prediction, and the other designed to take maximally surprising actions, rewarded every time the predictor is wrong. 50. In Super Mario Bros., if you've just hit the jump button, you can expect to see Mario slightly higher on the screen in a moment, for instance. Though only if you've tried it a few times already. If you've hit the down arrow, you can expect to see Mario crouch, but you may not be expecting that this will make Mario disappear down saw pipes into a massive subterranean underworld. The crucial idea was to incentivize the agent to explore the game by making such surprises as delightful for the agent as they are for us, namely, by making these prediction errors into rewards. Doing anything whose outcome was surprising could be made just as good, and that action just as strongly reinforced, as an action that explicitly garnered points. Pathak and his group looked at the kind of behavior that such a surprise reward might engender. Using a 3D maze environment, built with the engine of classic 90s first-person shooter Doom, they placed their agent farther and farther away from a rewarding goal state in a number of mazes. The agents trained only on the explicit reward of discovering the goal had a tendency to simply give up, if they couldn't find it by random joystick wiggling and button mashing. The agents with surprise-based rewards explored the maze for its own sake. What's around this corner? What does that distant room look like up close? As a result, these curious agents found their way to the goal in much more vast and complex mazes than the agents without this intrinsic drive. Pathak's Berkeley group teamed up with a group of researchers from OpenAI, and together they continued to explore this idea of using prediction error as a reward signal. Surprisingly, they found that a dramatic simplification of this architecture, replacing the network designed specifically to predict controllable aspects of the future with one designed to predict random features of the image on screen, worked just as well and in some cases even better. 51. The researchers at OpenAI, led by Yuri Berder and Harrison Edwards, worked to refine this idea, which they dubbed random network distillation, or R&D. 52. It wasn't long before they began to set their sights on Montezuma's revenge. They turned their R&D agent loose in the temple. Spurred by the intrinsic reward of surprise, it consistently managed to explore, on average, 20 to 22 of the temple's 24 rooms. And in just one of their trial runs, the agent does something unprecedented. It makes it all the way to the 24th and final room, in the temple's bottom left corner, and escapes the temple. 53. Panama, Joe steps through the final door, and finds himself in front of a background of uniform, blue filled with gems. He seems to fall through the sky. It's the closest thing Montezuma's revenge offers to transcendence. The gems are worth 1,000 points each, and it's very surprising. 54. Beyond rewards. It is becoming increasingly clear, then, that intrinsic motivation, conceived as novelty or surprise or some other related scheme, is an incredibly helpful drive for a system to have in order to augment the external rewards that come from the environment, particularly in cases where those external rewards are scarce or hard to come by. Of course, from this perspective it is tempting to ask what might happen if we take this idea of algorithmic curiosity to its logical conclusion and have reinforcement learning agents that, paradoxically, don't care about external rewards at all. What might such an agent look like? What might it do? Almost anyone who studies intrinsic motivation has wondered the same thing, and a picture is starting to emerge. Mark Bellmer and his colleagues at DeepMind have continued to pursue the idea of extending count-based novelty bonuses into more complex domains, and in follow-up work they have investigated what they call pushing the limits of intrinsic motivation. 55. They amplified their agent's novelty reward some 10 to 100-fold, and observed qualitative, as well as quantitative shifts in behavior. Expectedly enough, the agent's behavior exhibited a kind of restlessness. Unlike pursuit of the in-game score, which often leads to a fairly stable and consistent set of best practices, for the maximally curious agent, the only reward is from this exploratory behavior, and those rewards aren't stable. They disappear as parts of the game environment become more familiar. 56. So the agent keeps restlessly chasing after them rather than settling into a pattern. What was less expected was how well the agent did at the game, having been divorced from the game score. The agents with hyperinflated novelty bonuses actually achieved state-of-the-art scores in 4 different games. Curiosity bred competence. Amazingly, the novelty rewards alone, with no access to the in-game score whatsoever, were sufficient to play many Atari games competently, as measured by the score to which they didn't have access. Of course, it must be said that games, good games, anyway, are designed to appeal to intrinsically motivated humans. The points, after all, are just more pixels, in a corner of the screen, about which human players can decide to care, or not. So at that level it makes sense that curiosity, and a drive for exploration, would prove to be a decent proxy for maximizing score, at least in most games. In Super Mario Bros., for instance, points are awarded for grabbing coins, breaking blocks, and jumping on enemies, but the point of the game is to move Mario forward to the right, where an unpredictable landscape awaits. In this sense, an intrinsically motivated agent is probably more aligned with the game's intended mode of play than one driven to rack up these, ultimately meaningless, points. Pathak's group at Berkeley and Berder and Edwards' group at OpenAI have continued to pursue these questions as well, teaming up on a large-scale, systematic study of learning with no extrinsic rewards whatsoever. 57. One of their most striking findings was that in most cases, it's not necessary to explicitly tell the agent whether it has died. If you're trying to maximize extrinsic score, this is very useful indeed, as it's both a final verdict on the score you did get, as well as an indicator that you can expect 0 additional points from that moment onward, which is usually a disincentive to meet that same fate a second time. With a purely curiosity-driven agent, death simply means starting the game again from the beginning, which is very boring. The beginning of the game, being the most familiar part, is neither novel nor surprising. This is all the disincentive, it turns out, that the agent needs. 58. They also found an intriguing exception to the pattern of intrinsically motivated agents proving surprisingly adept at point scoring. The exception was Pong. An agent motivated purely by intrinsic rewards, one that cares nothing whatsoever about the score, plays the game not to score on the opponent, but rather to deliberately extend rallies as long as possible. The reset, after a point is scored, is essentially the same as the reset that occurs upon death in other games. Returning to the well-worn starting position is simply boring compared to the atypical and unusual positions that arise in a long rally. The team was intrigued to see what might happen if such an agent was given the chance to play against a copy of itself. How would curiosity versus curiosity unfold in a zero-sum game? The answer, a non-zero-sum collaboration emerges, as both sides pursue the shared goal of moving away from the game's well-trodden starting state. In other words, they rally and never stop. In fact, the researchers write, the game rallies eventually get so long that they break our Atari emulator. The screen starts to glitch out, with spots of color flickering in random patches. The surprise-seeking agents, of course, are delighted. 59. The idea of unplugging the game score and creating an agent motivated only intrinsically may seem at some level like an odd experiment. The field of reinforcement learning has since its inception been orchestrated around the maximization of external reward. Why give up the one thing by which behavior is being measured? The University of Michigan Satinder Singh, working with Michigan psychologist Richard Lewis and UMass Amherst's Andrew Bartow, explored this question philosophically, asking, where do rewards come from? 60. They note that the evaluation of how good or bad some state of affairs is done in the brain, not in the environment. This view makes it clear, they write, that reward signals are always generated within the animal, for example, by its dopamine system. Therefore, all rewards are internal. 61. To play an Atari game using nothing but the pixels on the screen, of which you can make whatever you want, rather than mainlining some fiat reward signal, is, after all, exactly what it is actually like to play video games. One of the most critically acclaimed computer games of the 2000s, Portal, involves the game's AI repeatedly promising the player a cake for completing the game. Partway through, however, the player discovers ominous graffiti containing what would become the game's most memorable catchphrase, the cake is a lie. Indeed, no cake is offered at the game's end. Of course, this famous betrayal is undercut not only by the fact that it would have been a digital representation of cake at best, but because we aren't playing the game under the illusion that there will be anything in it for us other than the pleasure of making progress, furthering the plot, and exploring the world of the game. We don't use the flashing lights on the screen as data that we can leverage to gain real rewards in that environment. The flashing lights, and whatever reaction they provoke in us, are all the reward there is. And that seems, judging by the number of hours we devote to video games, to be more than enough. Boredom and addiction. As it happens, intrinsic motivation in RL is not only the source of these virtuous behaviors, in which one recognizes at least a glimmer of the human desire to know, to explore, to see what happens. It also holds a mirror image of human pathologies, both boredom and addiction. I ask Deepak Pathak if the notion of boredom makes sense. Is it possible for an agent to get bored? Absolutely, he says. In the first level of Super Mario Bros., there is a chasm that his agent almost never figures out how to cross, because it requires the agent holding down the jump button for 15 frames in a row. Long sequences of precise actions are much more difficult to learn than shorter or more flexible patterns. 62. As a result, the agent reaches the edge of the cliff and just tries to turn around. So it just cannot cross it, Pathak says. So it's like a dead end, the end of the world. But the game is built so that there is no way to backtrack. The agent is stuck and learns to do nothing at all. There's a more general ennui, too, that Pathak has observed. After his Super Mario Bros. Agent has played the game long enough, it just starts to stay in the beginning. Because there is no reward anywhere, everywhere error is very, very low, so it just learns to not go anywhere. The agent simply loiters at the very start of the game, unmotivated to do anything at all. There is at least an iota of pathos here. A human who has grown bored with a game can stop playing, and usually will. We can swap the old game out for a new one, or just turn off the screen and move on to something different altogether. In contrast, the agent is, almost cruelly, trapped inside a game it no longer has any drive to play. Ever since there have been video games, there has been a subfield of study into the question of what makes them fun, and what makes one game more fun than another. There are obvious economic, as well as psychological stakes in this. 63. It occurs to me that reinforcement learning has furnished us with a practical benchmark for not just how difficult a game is, how long it takes the agent to become proficient, but also how long the agent plays before losing interest and disengaging, or whether it elects to spend its time playing that game over another. It may well be the case that video games of the coming decades are heavily focus grouped by intrinsically motivated RL agents. Cognitive scientist Douglas Hofstadter, in his 1979 Pulitzer Prize winning book Gödel, Escher, Bach, imagined the future of advanced game playing programs, envisioning a link between game playing competence, motivation, and intelligence. Question: will there be chess programs that can beat anyone? Speculation: no. There may be programs that can beat anyone at chess, but they will not be exclusively chess programs. They will be programs of general intelligence, and they will be just as temperamental as people. Do you want to play chess? No, I'm bored with chess. Let's talk about poetry. The quote looks hilariously dated now, and of course we know, with the benefit of hindsight, that it would be less than 20 years before IBM's Deep Blue chess machine emerged victorious in 1997 over human world champion Garry Kasparov. Deep Blue was, indeed, exclusively a chess program. It was customized at the level of its hardware to do chess, and chess only. It was certainly not generally intelligent, nor did it yearn to think about literature rather than chess. But perhaps there is a kernel of something nonetheless fundamentally true here. Contemporary state-of-the-art reinforcement learning systems really are general, at least in the domain of board and video games, in a way that Deep Blue was not. DQN could play dozens of Atari games with equal felicity. AlphaZero is just as adept at chess as it is at shogi and Go. What's more, artificial general intelligence, AGI, of the kind that can learn to operate fluidly in the real world may indeed require the sorts of intrinsic motivation architectures that can make it bored of a game it's played too much. At the other side of the spectrum from boredom is addiction, not a disengagement, but its dark reverse, a pathological degree of repetition or perseverance. Here, too, reinforcement learning has come to exhibit behaviors that are in some cases uncannily, uncomfortably human. Researchers who study intrinsic motivation talk about what they call the exit. In one version of the game, however, there is a television screen on one of the walls of the maze. Furthermore, the agent is given the ability to press a button that changes the channel on the television. What would happen? What happened is that the instant the agent comes within view of the TV screen, its exploration of the maze comes to a screeching halt. The agent centers the screen in its view and starts flipping through channels. Now it sees a video of an airplane in flight. Now it sees cute puppies. Now it sees a man seated at a computer. Now cars in downtown traffic. The agent keeps changing channels, awash in novelty and surprise. It never budges again. Visual information isn't the only source of randomness that can have these dangerous effects. So can something as simple as flipping a coin. This had almost a decade earlier weighed on the mind of DeepMind researcher Laurent Orso, the first hire onto their safety team, and who is now part of their foundation's research group. Long before the arrival of intrinsically motivated Atari-playing agents that could be turned instantaneously into couch potatoes, Orso was thinking about a much more powerful agent, transfixed by a coin. Orso was thinking about a hypothetical agent he called the knowledge-seeking agent, an agent whose goal is to gather as much information about the unknown world as possible. 64 Orso's agent was based on a theoretical framework called AIXI, which imagines an agent capable of infinite computation. Such a mentally omnipotent agent could never exist in reality, of course, but it acts as a kind of reference point. If you could think forever before taking an action, which one would you take? Amazingly, a number of conceptions of an infinitely resourceful knowledge-seeking agent fell into complete degeneracy at the sight of a coin, preferring to observe coin flips rather than explore a more informative part of their environment, also notes. The reason for this is that these agents mistake stochastic outcomes for complex information. 65b. F. Skinner, when he wasn't training pigeons, was fascinated by gambling addiction. The house always wins, on average, and psychology, all the way back to Thorndike, had been based on the idea that you do something more when it's on balance good for you, and less when it's bad. From this view, something like gambling addiction was impossible. And yet there it was, a presence in the real world, daring the behaviorists to make sense of it. Gamblers appear to violate the law of effect, Skinner wrote, because they continue to play even though their net reward is negative. Hence it is argued that they must be gambling for other reasons. 66 We now appear to have a pretty good candidate for what those other reasons might be. Gambling addiction may